looking at our own minds, sort of the biological stuff, or the neurobiological, the neuroscience, looking at the signals in our brain, uh, helped you understand the problem and the approach of effective computing. So
Originally, I was a computer architect, and I was building hardware and computer designs, and I wanted to build ones that work like the brain. So I've been studying the brain as long as I've been studying how to build computers.
have you figured out anything yet?
Very little. It's so amazing. You know, they used to think like, oh, if you remove this chunk of the brain and you find this function goes away, well, that's the part of the brain that did it. And then later they realize if you remove this other chunk of the brain, that function comes back. And oh no, we really don't understand it. Brains are so interesting and changing all the time and able to change in ways that will probably continue to surprise us. When we were measuring stress, you may know the story where we found an unusual big skin conductance pattern on one wrist in one of our kids with autism. And in trying to figure out how on earth you could be stressed on one wrist and not the other, like how can you get sweaty on one wrist, right? When you get stressed with that sympathetic fight or flight response, like you kind of should like sweat more in some places than others, but not more on one wrist than the other. That didn't make any sense. We learned that what had actually happened was a part of his brain had unusual electrical activity, and that caused an unusually large sweat response on one wrist and not the other. And since then, we've learned that seizures cause this unusual electrical activity. And depending where the seizure is, if it's in one place and it's staying there, you can have a big electrical response we can pick up with a wearable at one part of the body. You can also have a seizure that spreads over the whole brain, generalized grand mal seizure, and that response spreads and we can pick it up pretty much anywhere. As we learned this and then later built Embrace that's now FDA cleared for seizure detection, we have also built relationships with some of the most amazing doctors in the world who not only help people with unusual brain activity or epilepsy, but some of them are also surgeons and they're going in and they're implanting electrodes, not just to momentarily read the strange patterns of brain activity that we'd like to see return to normal, but also to read out continuously what's happening in some of these deep regions of the brain during most of life when these patients are not seizing. Most of the time they're not seizing. Most of the time they're fine. And so we are now working on mapping those deep brain regions that you can't even usually get with EEG scalp electrodes because the changes deep inside don't reach the surface. But interesting, when some of those regions are activated, we see a big skin conductance response. Who would have thunk it, right? Like nothing here, but something here. In fact, right after seizures that we think are the most dangerous ones that precede what's called SUDEP, sudden unexpected death in epilepsy, there's a period where the brain waves go flat and it looks like the person's brain has stopped, but it hasn't. The activity has gone deep into a region that can make the cortical activity look flat, like a quick shutdown signal here. It can unfortunately cause breathing to stop if it progresses long enough. Before that happens, we see a big skin conductance response in the data that we have. The longer this flattening, the bigger our response here. So we have been trying to learn, initially like, why are we getting a big response here when there's nothing here? Well, it turns out there's something much deeper. So we can now go inside the brains of some of these individuals, fabulous people who usually aren't seizing, and get this data and start to map it. So that's active research that we're doing right now with top medical partners.
So this wearable sensor that's looking at skin conductance can capture sort of the ripples of the complexity of what's going on in our brain. So this little device, you have a hope that you can start to get the signal from the interesting things happening in the brain.
Yeah, we've already published the strong correlations between the size of this response and the flattening that happens afterwards. And unfortunately, also in a real SUDEP case where the patient died because we don't know why. We don't know if somebody was there, it would have definitely prevented it. But we know that most SUDEPs happen when the person's alone. And in this case...
What's a SUDEP? I'm sorry.
A SUDEP is an acronym, SUDEP, okay. And it stands for the number 2 cause of years of life lost, actually, among all neurological disorders. Stroke is number 1, SUIT-UP is number 2, but most people haven't heard of it. Actually, I'll plug my TED Talk. It's on the front page of TED right now, that talks about this. And we hope to change that. I hope everybody who's heard of SIDS and stroke will now hear of SUIT-UP, because we think in most cases it's preventable if people take their meds and aren't alone when they have a seizure. Not guaranteed to be preventable. There are some exceptions, but we think most cases probably are.
So you have this Embrace now in the version 2 wristband, right? For epilepsy management. That's the one that's FDA approved?
Yes.
And which is kind of
FDA cleared, they say. Yeah.
Sorry.
No, that's okay. It essentially means it's approved for marketing.
Got it. Just a side note, how difficult is that to do? It's essentially getting FDA approval for computer science technology.
It's so agonizing. It's much harder than publishing multiple papers in top medical journals. Yeah, we published peer-reviewed top medical journal, neurology, best results, and that's not good enough for the FDA.
Is that system, so if we look at the peer review of medical journals, there's flaws, there's strengths. Is the FDA approval process, how does it compare to the peer review process? Does it have its strength?
I would take peer review over FDA any day.
But is that a good thing? Is that a good thing for FDA? You're saying, does it stop some amazing technology from getting through?
Yeah, it does. The FDA performs a very important good role in keeping people safe. They keep things, they put you through tons of safety testing, and that's wonderful, and that's great. I'm all in favor of the safety testing. Sometimes they put you through additional testing that they don't have to explain why they put you through it, and you don't understand why you're going through it, and it doesn't make sense. And that's very frustrating. And maybe they have really good reasons, and they just it would do people a service to articulate those reasons.
Be more transparent.
Be more transparent.
So as part of Empatica, you have sensors. So what kind of problems can we crack? What kind of things, from seizures to autism, to, I think I've heard you mention depression. What kind of things can we alleviate? Can we detect? What's your hope of how we can make the world a better place with this wearable tech?
I would really like to see my, fellow brilliant researchers step back and say, what are the really hard problems that we don't know how to solve that come from people maybe we don't even see in our normal life because they're living in the poorer places. They're stuck on the bus. They can't even afford the Uber or the Lyft or the data plan or all these other wonderful things we have that we keep improving on. Meanwhile, there's all these folks left behind in the world, and they're struggling with horrible diseases, with depression, with epilepsy, with diabetes, with just awful stuff that maybe a little more time and attention hanging out with them and learning what are their challenges in life, what are their needs, how do we help them have job skills, how do we help them have a hope and a future and a chance to have the great life that so many of us building technology have. And then how would that reshape the kinds of AI that we build? How would that reshape the new apps that we build, or maybe we need to focus on how to make things more low cost and green instead of $1,000 phones. I mean, come on, why can't we be thinking more about things that do more with less for these folks? Quality of life is not related to the cost of your phone. It's not something that, it's been shown that about $75,000 of income and happiness is the same. Okay. However, I can tell you get a lot of happiness from helping other people. You get a lot more than $75,000 buys. So how do we connect up the people who have real needs with the people who have the ability to build the future and build the kind of future that truly improves the lives of all the people that are currently being left behind?
So let me return just briefly on a point, maybe in the movie Her. Mm-hmm. So do you think if we look farther into the future, you said so much of the benefit from making our technology more empathetic to us human beings would make them better tools, empower us, make our lives better. Well, if we look farther into the future, do you think we'll ever create an AI system that we can fall in love with and loves us back on a level that is similar to human interaction, like in the movie Her or beyond?
I think we can simulate it in ways that could, sustain engagement for a while. Would it be as good as another person? I don't think so. For if you're used to like good people, now if you've just grown up with nothing but abuse and you can't stand human beings, can we do something that helps you there, that gives you something through a machine? Yeah, but that's a pretty low bar, right? If you've only encountered pretty awful people. If you've encountered wonderful, amazing people, we're nowhere near building anything like that. And I would not bet on building it. I would bet instead on building the kinds of AI that helps kind of raise all boats, that helps all people be better people, helps all people figure out if they're getting sick tomorrow, and helps give them what they need to stay well tomorrow. That's the kind of AI I want to build that improves human lives, not the kind of AI that just walks on the Tonight Show and people go, wow, look how smart that is. Really? And then it goes back in a box,
So on that point,
As a small aside, as you're talking about the biology, let me comment that this is what I do. This is what I do with my life. This is why I will never accomplish anything. Is I spend much of the morning trying to do research on how many computations the brain performs and how much energy it uses versus the state of the art CPUs and GPUs. Arriving at about 20 quadrillion, so that's 2 to the 10 to the 16 computations, so synaptic firings per second that the brain does, and that's about 1 million times faster than the let's say the 20 thread state of the art Intel CPU, the 10th generation, and then there's similar calculation for the GPU, and all ended up also trying to compute that it takes 10 watts to run the brain and then what does that mean in terms of calories per day, kilocalories? That's about for an average human brain, that's 250 to 300 calories a day. And so it ended up being a calculation where you're doing about 20 quadrillion calculations that are fueled by something like, depending on your diet, 3 bananas. So 3 bananas results in a computation that's about 1 million times more powerful than the current state-of-the-art computers.
Now let's take that one step further. There's some assumptions built in there. The assumption is that, one, what the brain is doing is just computation. 2, the relevant computations are synaptic firings, and that there's nothing other than synaptic firings that we have to factor. So I'm forgetting his name right now. There's a very famous neuroscientist at Stanford, just passed away recently, who did a lot of the pioneering work on glial cells and showed that his assessment, glial cells did a huge amount of the thinking, not just neurons. And it opened up this entirely different field of like what the brain is and what consciousness is. You look at Damasio's work on embodied cognition and how much of what we would consider consciousness or feeling is happening outside of the nervous system completely, happening in endocrine process involving lots of other cells and signal communication. You talk to somebody like Penrose, who you've had on the show, and even though the Penrose-Hammerhoff conjecture is probably not right, is there something like that might be the case, where we're actually having to look at stuff happening at the level of quantum computation at microtubules? I'm not arguing for any of those. I'm arguing that we don't know how big the unknown set is.
Well, at the very least, this has become like an infomercial for the human brain. But wait, there's more. At the very least, the 3 bananas buys you 1 million times.
At the very least.
At the very least.
Impressive.
And then you could have, and then the synaptic firings we're referring to is strictly the electrical signals. That could be the mechanical transmission of information. There's chemical transmission of information. There's all kinds of other stuff going on. And then there's memory that's built in. That's also all tied in. Not to mention, which I'm learning more and more about, it's not just about the neurons. It's also about the immune system that's somehow helping with the computation. So it's the entirety and the entire body is helping with the computation. So the 3 bananas,
It could buy you a lot.
It could buy you a lot. Maybe briefly, if you could paint a picture of the kind of methods of neuroimaging, maybe the history, which you were a part of, from statistical parametric mapping. I mean, just what's out there that's interesting for people maybe outside the field, that to understand of what are the actual methodologies of looking inside the human brain.
Right. Well, you can answer that question from two perspectives. Basically, it's the modality. What kind of signal are you measuring? And they can range from, and let's limit ourselves to sort of imaging-based, non-invasive techniques. So you've essentially got brain scanners, and brain scanners can either measure the structural attributes, the amount of water, or the amount of fat, or the amount of iron in different parts of the brain. You can make lots of inferences about the structure of the organ of the sort that you might abduce from an X-ray, but a very nuanced X-ray that is looking at this kind of property or that kind of property. So looking at the anatomy non-invasively would be the first sort of neuroimaging that people might want to employ. Then you move on to the kinds of measurements that reflect dynamic function, and the most prevalent of those fall into two camps. You've got these metabolic, sometimes hemodynamic, blood-related signals. Mm-hmm. So these metabolic and or hemodynamic signals are basically proxies for elevated activity and message passing and neuronal dynamics in particular parts of the brain. Characteristically, though, the time constants of these hemodynamic or metabolic responses to neural activity are much longer than the neural activity itself.
And this is referring, forgive me for the dumb questions, but this would be referring to blood, like the flow of blood.
Absolutely.
Absolutely. It seems like there's a ton of blood vessels in the brain.
Yep.
So, but what's the interaction between the flow of blood and the function of the neurons? Is there an interplay there? Or
Yep. And that interplay accounts for the several careers of world-renowned scientists. Yes, absolutely. So this is known as neurovascular coupling. It's exactly what you said. It's how does the neural activity, the neuronal infrastructure, the actual message passing that we think underlies our capacity to perceive and act, how is that coupled to the vascular responses that supply the energy for that neural processing? So there's a delicate web of large vessels, arteries and veins, that gets progressively finer and finer in detail until it perfuses at a microscopic level the machinery where little neurons lie. So coming back to this sort of onion perspective, we were talking before using the onion as a metaphor for a deep hierarchical structure, but also I think it's just an anatomically quite a useful metaphor. All the action, all the heavy lifting in terms of neural computation is done on the surface of the brain, and then the interior of the brain is constituted by fatty wires, essentially axonal processes that are enshrouded by myelin sheaths, and these give when you dissect them, they look fatty and white, and so it's called white matter, as opposed to the actual neuropil, which does the computation, constituted largely by neurons, and that's known as grey matter. So the grey matter is a surface or a skin that sits on top of this big ball. Now we are talking magic soup, but it's a big ball of connections like spaghetti, yes. Very carefully structured with sparse connectivity that preserves this deep hierarchical structure. But all the action takes place on the surface, on the cortex of the onion. And that means that you have to supply the right amount of blood flow, the right amount of nutrient, which is rapidly absorbed and used by neural cells that don't have the same capacity that your leg muscles would have to basically spend their energy budget and then claim it back later. So one peculiar thing about cerebral metabolism, brain metabolism, is it really needs to be driven in the moment, which means you basically have to turn on the taps. So if there's lots of neural activity in one part of the brain, a little patch of a few millimeters, even less possibly, you really do have to water that piece of the garden now and quickly. And that, by quickly, I mean within a couple of seconds.
So that contains a lot of So, hence, the imaging could tell you a story of what's happening in the brain.
Absolutely. But it is slightly compromised in terms of the resolution. So the deployment of these little micro vessels that water the garden to enable the activity to the neural activity to play out. The spatial resolution is in order of a few millimeters, and crucially, the temporal resolution is the order of a few seconds. So you can't get right down and dirty into the actual spatial and temporal scale of neuronal activity in and of itself. To do that, you'd have to turn to the other big imaging modality, which is the recording of electromagnetic signals as they're generated in real time. So here, the temporal bandwidth, if you like, or the low limit on the temporal resolution is incredibly small. You're talking about, nanoseconds, milliseconds. And then you can get into the phasic fast responses that is in and of itself the neural activity, and start to see the succession or cascade of hierarchical recurrent message passing evoked by a particular stimulus. But the problem is you're looking at electromagnetic signals that have passed through an enormous amount of magic soup or spaghetti of connectivity and through the scalp and the skull, and it's become spatially very diffuse. So it's very difficult to know where you are. So you've got this sort of catch-22. You can either use an imaging modality that tells you within millimeters which part of the brain is activated, but you don't know when, or you've got these electromagnetic EEG, MEG setups that tell you to within a few milliseconds when something has responded, but you don't know where. So you've got these two complementary measures, either indirect via the blood flow or direct via the electromagnetic signals caused by neural activity. These are the two big imaging devices. And then the second level of responding to your question, what are the, from the outside, what are the big ways of using this technology? So once you've chosen the kind of neuroimaging that you want to use to answer your set questions, and sometimes it would have to be both, then you've got a whole raft of analyses, time series analyses usually, that you can bring to bear in order to answer your questions or address your hypothesis about those data. And interestingly, they both fall into the same two camps we were talking about before. This dialectic between specialization and integration, differentiation and integration. So it's the cartography, the blobology analyses.
I apologize. I probably shouldn't interrupt so much, but just heard a fun word.
Blobology.
Blobology.
No, it's a neologism, which means the study of blobs. So nothing more.
Are you being witty and humorous, or is there an actual? Does the word blobology ever appear in a textbook somewhere?
It would appear in a popular book. It would not appear in a worthy specialist journal.
Yeah,
but it's the fond word for the study of literally little blobs on brain maps showing activations. So the kind of thing that you'd see in the newspapers on ABC or BBC reporting the latest finding from brain imaging. Interestingly, though, the maths involved in that stream of analysis does actually call upon the mathematics of blobs. So seriously, they're actually called Euler characteristics, and they have a lot of fancy names in mathematics.
We'll talk about your ideas in free energy principle. I mean, there's echoes of blobs there when you consider sort of entities, so mathematically speaking.
Yes,
so
absolutely. Yeah.
So anyway,
circumscribed, well-defined.
Yes.
You entities of, from the free energy point of view, entities of anything, but from the point of view of the analysis, the cartography of the brain, these are the entities that constitute the evidence for this functional segregation. You have segregated this function in this blob, and it is not outside of the blob. And that's basically if you were a map maker of America, and you did not know its structure, the first thing you were doing, constituting or creating a map, would be to identify the cities, for example, or the mountains, or the rivers. All of these uniquely spatially localizable features, possibly topological features, have to be placed somewhere, because that requires a mathematics of identify what does a city look like on a satellite image, or what does a river look like, or what does a mountain look like. What would it, what data features would evidence that particular that particular thing that you wanted to put on the map. And they normally are characterized in terms of literally these blobs, or these sort of, another way of looking at this is a certain statistical measure of the degree of activation crosses a threshold. And in crossing that threshold, in the spatially restricted part of the brain, it creates a blob. And that's basically what statistical parametric mapping does. It's basically mathematically finessed blobology.
Okay, so you kind of described these two methodologies for. One is temporally noisy, one is spatially noisy, and you kind of have to play and figure out what can be useful. How much of the human brain do we understand from the low level of neuronal communication to the functional level to the highest level, maybe the psychiatric disorder level?
Well, we're certainly in a better position than we were last century. How far we've got to go, I think, is almost an unanswerable question. So you'd have to set the parameters, what constitutes understanding, what level of understanding do you want? I think we've made enormous progress in terms of broad brush principles. Whether that affords a detailed cartography of the functional anatomy of the brain and what it does, and right down to the microcircuitry in the neurons, that's probably out of reach at the present time.
So the cartography, so mapping the brain. Do you think mapping of the brain, the detailed, perfect imaging of it, does that get us closer to understanding of the mind, of the brain? So how far does it get us if we have that perfect cartography of the brain?
I think there are lower bounds on that. It's a really interesting question. And it would determine the sort of scientific career you'd pursue if you believe that knowing every dendritic connection, every sort of microscopic synaptic structure right down to the molecular level was going to give you the right kind of information to understand the computational anatomy. Then you'd choose to be a microscopist, and you would study little cubic millimeters of brain for the rest of your life. If, on the other hand, you were interested in holistic functions and a sort of functional anatomy of the sort that a neuropsychologist would understand, you'd study brain lesions and strokes, just looking at the whole person. So again, it comes back to at what level do you want understanding? I think there are principled reasons not to go too far. If you commit to a view of the brain as a machine that's performing a form of inference and representing things, there are that understanding, that level of understanding is necessarily cast in terms of probability densities and ensemble densities, distributions. And what that tells you is that you don't really want to look at the atoms to understand the thermodynamics of probabilistic descriptions of how the brain works. So I personally wouldn't look at the molecules or indeed the single neurons in the same way if I wanted to understand the thermodynamics of some non-equilibrium steady state of a gas or an active material. I wouldn't spend my life looking at the individual molecules that constitute that ensemble. I'd look at their collective behavior. On the other hand, if you go too coarse grain, you're going to miss some basic canonical principles of connectivity and architectures. I'm thinking here, it's a bit colloquial, but there's current excitement about high field magnetic resonance imaging at 7 Tesla. Why? Well, it gives us for the first time the opportunity to look at the brain in action at the level of a few millimeters that distinguish between different layers of the cortex that may be very important in terms of evincing generic principles of canonical microcircuitry that are replicated throughout the brain that may tell us something fundamental about message passing in the brain and these density dynamics or neuronal or ensemble population dynamics that underwrite our brain function. So somewhere between a millimeter and a meter.
Lingering for a bit on the big questions, if you allow me, what to you is the most beautiful or surprising characteristic of the human brain?
I think its hierarchical and recursive aspect, its recurrent aspect.
Of the structure or of the actual representational power of the brain?
Well, I think one speaks to the other. I was actually answering in a dull-minded way from the point of view of purely its anatomy and its structural aspects. I mean, there are many marvelous organs in the body. Let's take your liver, for example. Without it, you wouldn't be around for very long. And it does some beautiful and delicate biochemistry and homeostasis, and evolved with a finesse that would easily parallel the brain, but it doesn't have a beautiful anatomy. It has a simple anatomy, which is attractive in a minimalist sense, but it doesn't have that crafted structure of sparse connectivity and that recurrence and that specialization that the brain has.
So you said a lot of interesting terms here. So the recurrence, the sparsity, but you also started by saying hierarchical.
Mm-hmm.
So I've never thought of our brain as hierarchical.
Uh-huh.
Sort of, I always thought it's just like a giant mess, interconnected mess where it's very difficult to figure anything out. But in what sense do you see the brain as hierarchical?
Well, I see it's not a magic soup. It's, which, of course, is what I used to think when I was, before I studied medicine and the like. So a lot of those terms imply each other. So hierarchies, if you just think about the nature of a hierarchy, how would you actually build one? And what you would have to do is basically carefully remove the right connections that destroy the completely connected soups that you might have in mind. So a hierarchy is in and of itself defined by a sparse and particular connectivity structure. And I'm not committing to any particular form of hierarchy.
But your sense is there is some.
Oh, absolutely, yeah. In virtue of the fact that there is a sparsity of connectivity, not necessarily of a qualitative sort, but certainly of a quantitative sort. So it is demonstrably so, and that the far further apart two parts of the brain are, the less likely that they are to be wired, to possess axonal processes, neuronal processes that directly communicate one message or messages from one part of that brain to the other part of the brain. So we know there's a sparse connectivity, and furthermore, on the basis of anatomical connectivity and tracer studies, we know that that sparsity underwrites a hierarchical and very structured sort of connectivity that might be best understood like a little bit like an onion. That there is a concentric, sometimes referred to as centripetal by people like Marcel Mesulem, hierarchical organization to the brain. So you can think of the brain as, in a rough sense, like an onion, and all the sensory information and all the afferent outgoing messages that supply commands to your muscles or to your secretory organs come from the surface. So there's a massive exchange interface with the world out there on the surface. And then underneath there's a little layer that sits and looks at the exchange on the surface. And then underneath that there's a layer right the way down to the very center, to the deepest part of the onion. That's what I mean by a hierarchical organization. There's a discernible structure defined by the sparsity of connections that lends the architecture a hierarchical structure that tells one a lot about the kinds of representations and messages. So coming back to your earlier question, is this about the representational capacity or is it about the anatomy? Well, one underwrites the other. If one just simply thinks of the brain as a a message passing machine, a process that is in the service of doing something, then the circuitry and the connectivity that shape that message passing also dictate its function.
So it'd be great if you can sort of comment. I got a chance recently to spend a day at a company called Neuralink that uses brain-computer interfaces, and their dream is to, well, there's a bunch of sort of dreams, but one of them is to understand the brain by sort of, getting in there past the so-called sort of factory wall, getting in there and be able to listen, communicate both directions. What are your thoughts about this, the future of this kind of technology of brain-computer interfaces, to be able to now have a window or direct contact within the brain to be able to measure some of the signals, to be able to send signals, to understand some of the functionality of the brain?
Ambivalent. My sense is ambivalent. So it's a mixture of good and bad, and I acknowledge that freely. So the good bits, if you just look at the legacy of that kind of reciprocal but invasive brain stimulation, I didn't paint a complete picture when I was talking about the ways we understand the brain prior to neuroimaging. It wasn't just lesion deficit studies. Some of the early work, in fact, literally 100 yards from where we're sitting at the Institute of Neurology, was done by stimulating the brain of, say, dogs, and looking at how they responded, either with their muscles or with their salivation, and imputing what that part of the brain must be doing. That if I stimulate it, then and I evoke this kind of response, then that tells me quite a lot about the functional specialization. So there's a long history of brain stimulation, which continues to enjoy a lot of attention nowadays.
Positive attention?
Oh, yes, absolutely. Deep brain stimulation for Parkinson's disease is now a standard treatment, and also a wonderful vehicle to try and understand the neuronal dynamics that underlie movement disorders like Parkinson's disease. Even interest in magnetic stimulation, stimulating with magnetic fields, and will it work in people who are depressed, for example? Quite a crude level of understanding what you're doing, but there is historical evidence that these kinds of brute force interventions do change things. They, it's a little bit like banging the TV when the valves aren't working properly, but it works. There is a long history. Brain-computer interfacing, or BCI, I think is a beautiful example of that. It's sort of carved out its own niche and its own aspirations, and there have been enormous advances within limits. Advances in terms of our ability to understand how the embodied brain, engages with the world. I'm thinking here of sensory substitution, the augmenting our sensory capacities by giving ourselves extra ways of sensing and sampling the world, ranging from sort of trying to replace lost visual signals through to giving people completely new signals. So one of the, I think, most engaging examples of this is equipping people with a sense of magnetic fields. Mm-hmm. So you can actually give them magnetic sensors that enable them to feel, should we say, tactile pressure around their tummy, where they are in relation to the magnetic field of the Earth.
That's incredible.
And after a few weeks, they take it for granted. They integrate it, they imbibe, they assimilate this new sensory information into the way that they literally feel their world, but now equipped with this sense of magnetic direction. So that tells you something about the brain's plastic potential to remodel and its plastic capacity to suddenly try to explain the sensory data at hand by augmenting the sensory sphere and the kinds of things that you can measure. Clearly, that's purely for entertainment and understanding the nature and the power of our brains. I would imagine that most BCI is pitched at solving clinical and human problems such as locked-in syndrome, such as paraplegia, or replacing lost sensory capacities like blindness and deafness. So then we come to the more the negative part of my ambivalence, the other side of it. So I don't want to be deflationary, because much of my deflationary comments is probably largely out of ignorance than anything else. But generally speaking, the bandwidth and the bit rates that you get from brain-computer interfaces as we currently know them, we're talking about bits per second. Yeah. So that would be like me only being able to communicate with any world or with you using very, very, very slow Morse code. And it is not even within an order of magnitude near what we actually need for an inactive realization of what people aspire to when they think about sort of curing people with paraplegia or replacing sight, despite heroic efforts. So one has to ask, is there a lower bound on the kinds of recurrent information exchange between a brain and some augmented or artificial interface? And then we come back to, interestingly, what I was talking about before, which is, if you're talking about function in terms of inference, and I presume we'll get to that later on in terms of the free energy principle, but at the moment, there may be fundamental reasons to assume that is the case. We're talking about ensemble activity. We're talking about basically, for example, let's paint the challenge facing brain-computer interfacing in terms of controlling another system that is highly and deeply structured, very relevant to our lives, very non-linear, that rests upon the kind of non-equilibrium steady states and dynamics that the brain does, the weather. All right? So,
good example, yeah.
Imagine you had some very aggressive satellites that could produce signals that could perturb some little parts of the weather system. And then what you're asking now is, can I meaningfully get into the weather and change it meaningfully and make the weather respond in a way that I want it to? Mm-hmm. You're talking about chaos control on a scale which is almost unimaginable. So there may be fundamental reasons why BCI, as you might read about it in a science fiction novel, aspirational BCI may never actually work, in the sense that to really be integrated and be part of the system is a requirement that requires you to have evolved with that system. That you have to be part of a very delicately structured, deeply structured, dynamic ensemble activity that is not like rewiring a broken computer or plugging in a peripheral interface adapter. It is much more like getting into the weather patterns, or come back to your magic soup, getting into the active matter and meaningfully relate that to the outside world. So I think there are enormous challenges there.
So I think the example of the weather is a brilliant one. And I think you paint a really interesting picture. And it wasn't as negative as I thought. It's essentially saying that it might be incredibly challenging, including the low bound of the bandwidth and so on. So just to full disclosure, I come from the machine learning world. So my natural thought is the hardest part is the engineering challenge of controlling the weather, of getting those satellites up and running and so on. And once they are, then the rest is fundamentally the same approaches that allow you to win in the game of Go will allow you to potentially play in this soup, in this chaos. Mm-hmm. So I have a hope that sort of machine learning methods will help us play in this soup. But perhaps you're right that it is biology in the brain is just an incredible system that may be almost impossible to get in. But for me, what seems impossible is the incredible mess of blood vessels that you also described. Without, we also value the brain. You can't make any mistakes. You can't damage things. So to me, that engineering challenge seems nearly impossible. One of the things I was really impressed by at Neuralink is just talking to brilliant neurosurgeons and the roboticists that it made me realize that even though it seems impossible, if anyone can do it, it's some of these world-class engineers that are trying to take it on. So I think the conclusion of our discussion here is of this part is basically that the problem is really hard, but hopefully not impossible.
Absolutely.
So if it's okay, you've done a lot of amazing work in a lot of directions. So let's look at one aspect of that, of looking into the brain and trying to study this onion structure. What can we learn about the brain by imaging it, which is one way to sort of look at the anatomy of it. Mm-hmm. Broadly speaking, what are the methods of imaging, but even bigger, what can we learn about it?
Right. So, well, most imaging, human neuroimaging that you might see, in science journals, that speaks to the way the brain works, measures brain activity over time. So, that's the first thing to say, that we're effectively looking at fluctuations in neuronal responses, usually in response to some sensory input or some instruction, some task. Not necessarily. There's a lot of interest in just looking at the brain in terms of resting state, endogenous or intrinsic activity. But crucially, at every point, looking at these fluctuations, either induced or intrinsic in the neural activity, and understanding them at two levels. So normally people would recourse to two principles of brain organization that are complementary. One, functional specialization or segregation. So what does that mean? It simply means that there are certain parts of the brain that may be specialized for certain kinds of processing. For example, visual motion, our ability to recognize or to perceive movement in the visual world. And furthermore, that specialized processing may be spatially or anatomically segregated, leading to functional segregation, which means that if I were to compare your brain activity during a period of static viewing a static image, and then compare that to the responses, the fluctuations in the brain when you were exposed to a moving image, say a flying bird, we would expect to see restricted, segregated differences in activity. And those are basically the hot spots that you see in statistical parametric maps that test for the significance of the responses that are circumscribed. So now basically we're talking about, some people have perhaps unkindly called a neocartography. This is a phrenology augmented by modern day neuroimaging, basically finding blobs or bumps on the brain that do this or do that, and trying to understand the cartography of that functional specialization.
So how much is there that's such a beautiful sort of ideal to strive for. We humans, scientists, would like to hope that there's a beautiful structure to this, where, like you said, there's segregated regions that are responsible for the different function. How much hope is there to find such regions in terms of looking at the progress of studying the brain?
Oh, I think enormous progress has been made in the past 20 or 30 years. So this is beyond incremental. At the advent of brain imaging, the very notion of functional segregation was just a hypothesis based upon a century, if not more, of careful neuropsychology, looking at people who had lost via insult or traumatic brain injury particular parts of the brain, and then saying, well, they can't do this or they can't do that. For example, losing the visual cortex and not being able to see, or losing particular parts of the visual cortex, or regions known as V5, or the middle temporal region, MT, and noticing that they selectively could not see moving things. And so that created the hypothesis that perhaps movement processing, visual movement processing, was located in this functionally segregated area. And you could then go and put invasive electrodes in animal models and say, yes, indeed, we can excite activity here, we can form receptive fields that are sensitive to or defined in terms of visual motion. But at no point could you exclude the possibility that everywhere else in the brain was also very interested in visual motion.
By the way, I apologize to interrupt, but it's a tiny little tangent. You said animal models. Just out of curiosity, from your perspective, how different is the human brain versus the other animals in terms of our ability to study the brain?
Well, clearly, the far further away you go from a human brain, the greater the difference is, but not as remarkable as you might think. So people will choose their level of approximation to the human brain depending upon the kinds of questions that they want to answer. So if you're talking about sort of canonical principles of microcircuitry, it might be perfectly okay to look at a mouse. Indeed, you could even look at flies, worms. If, on the other hand, you wanted to look at the finer details of organization of visual cortex and V1, V2, these are designated sort of patches of cortex that may do different things, indeed do. You probably want to use a primate that looked a little bit more like a human, because there are lots of ethical issues in terms of the use of non-human primates to to answer questions about human anatomy. But I think most people assume that most of the important principles are conserved in a continuous way, from right from, well, yes, worms right through the way through to you and me.
So now returning to, so that was the early sort of ideas of studying the functional regions of the brain by if there's some damage to it, to try to infer that there's that part of the brain might be somewhat responsible for this type of function. So where does that lead us? What are the next steps beyond that?
Right. Well, just actually just reverse a bit, come back to your sort of notion that the brain is a magic soup. That was actually a very prominent idea at one point. Notions such as Lashley's law of mass action, inherited from the observation that for certain animals, if you just took out spoonfuls of the brain, it didn't matter where you took these spoonfuls out, they always showed the same kinds of deficits. So, it was very difficult to infer functional specialization purely on the basis of lesion deficit studies. But once we had the opportunity to look at the brain lighting up in its sort of excitement, neuronal excitement, when looking at this versus that, one was able to say, yes, indeed, these functionally specialized responses are very restricted, and they're here or they're over there. If I do this, then this part of the brain lights up. And that became doable in the early 90s. In fact, shortly before, with the advent of positron emission tomography, and then functional magnetic resonance imaging came along in the early 90s. And since that time, there has been an explosion of discovery, refinement, confirmation. There are people who believe that it's all in the anatomy. If you understand the anatomy, then you understand the function at some level. And many, many hypotheses were predicated on a deep understanding of the anatomy and the connectivity, but they were all confirmed and taken much further with neuroimaging. So that's what I meant by we've made an enormous amount of progress in this century, indeed, and in relation to the previous century, by looking at these functionally selective responses. But that wasn't the whole story. So there's this sort of near phrenology, but finding bumps and hot spots in the brain that did this or that. The bigger question was, of course, the functional integration, how all of these regionally specific responses were orchestrated, how they were distributed, how did they relate to distributed processing and indeed representations in the brain. So then you turn to the more challenging issue of the integration, the connectivity. And then we come back to this beautiful, sparse, recurrent, hierarchical connectivity that seems characteristic of the brain and probably not many other organs.
But nevertheless, we come back to this challenge of trying to figure out how everything is integrated. But what's your feeling? What's the general consensus? Have we moved away from the magic soup view of the brain?
Yes.
So there is a deep structure to it.
Yes.
That, and then maybe a further question. You said some people believe that the structure is most of it, that you can really get at the core of the function by just deeply understanding the structure.
Yes.
Where do you sit on that?
I think it's got some mileage to it. Yes. Yeah. Yeah.
So it's a worthy pursuit of going, of studying through imaging and all the different methods to actually study.
Absolutely.
The structure.
Yeah.
On that topic, you kind of mentioned information. Just to get a sense, I imagine something that there's still mystery and disagreement on is how does the brain carry information and signal? Like, what in your sense is the basic mechanism of communication in the brain?
Well, I guess I'm old-fashioned in that I consider the networks that we use in deep learning research to be a reasonable approximation to the mechanisms that carry information in the brain. So the usual way of articulating that is to say, what really matters is a rate code. What matters is how quickly is an individual neuron spiking. What's the frequency at which it's spiking? Is it
the timing of the spiking?
Yeah. Is it firing fast or slow? Let's put a number on that. And that number is enough to capture what neurons are doing. There's still uncertainty about whether that's an adequate description of how information is transmitted within the brain. There are studies that suggest that the precise timing of spikes matters. There are studies that suggest that there are computations that go on within the dendritic tree, within a neuron, that are quite rich and structured and that really don't equate to anything that we're doing in our artificial neural networks. Having said that, I feel like we're getting somewhere by sticking to this high level of abstraction.
Just the rate, and by the way, we're talking about the electrical signal. I remember reading some vague paper somewhere recently where the mechanical signal, like the vibrations or something of the neurons, also communicates information.
I haven't seen that, but
so there's somebody was arguing that the electrical signal. This is in a Nature paper, something like that, where the electrical signal is actually a side effect of the mechanical signal. But I don't think they changed the story. but it's almost an interesting idea that there could be a deeper. It's always like in physics with quantum mechanics. There's always a deeper story that could be underlying the whole thing. But you think it's basically the rate of spiking that gets us. That's like the lowest hanging fruit that can get us really far.
This is a classical view. I mean, this is not the only way in which this stance would be controversial is in the sense that there are members of the neuroscience community who are interested in alternatives, but this is really a very mainstream view. The way that neurons communicate is that neurotransmitters arrive they wash up on a neuron. The neuron has receptors for those transmitters. The meeting of the transmitter with these receptors changes the voltage of the neuron, and if enough voltage change occurs, then a spike occurs, right? One of these like discrete events, and it's that spike that is conducted down the axon and leads to neurotransmitter release. This is just like neuroscience 101. This is like the way the brain is supposed to work. Now, what we do when we build artificial neural networks of the kind that are now popular in the AI community is that we don't worry about those individual spikes. We just worry about the frequency at which those spikes are being generated. And we consider, people talk about that as the activity of a neuron. And, so the activity of units in a deep learning system is, broadly analogous to the spike rate of a neuron. There are people who believe that there are other forms of communication in the brain. In fact, I've been involved in some research recently that suggests that the voltage fluctuations that occur in populations of neurons that aren't, that are sort of below the level of spike production may be important for communication. But I'm still pretty old school in the sense that I think that the things that we're building in AI research constitute reasonable models of how a brain would work.
Let me ask, just for fun, a crazy question, because I can. Do you think it's possible we're completely wrong about the way this basic mechanism of neuronal communication, that the information is stored in some very different kind of way in the brain?
Oh, heck yes. I mean, I wouldn't be a scientist if I didn't think there was any chance we were wrong. But I mean, if you look at the history of deep learning research as it's been applied to neuroscience, of course, the vast majority of deep learning research these days isn't about neuroscience. But if you go back to the 1980s, there's sort of an unbroken chain of research in which a particular strategy is taken, which is, hey, let's train a deep learning system. Let's train a multi-layer neural network on this task that we trained our rat on, or our monkey on, or this human being on, and then let's look at what the units deep in the system are doing, and let's ask whether what they're doing resembles what we know about what neurons deep in the brain are doing. And over and over and over and over, that strategy works in the sense that the learning algorithms that we have access to, which typically center on backpropagation, they give rise to, patterns of activity, patterns of response, patterns of like neuronal behavior in these artificial models that look hauntingly similar to what you see in the brain. And is that a coincidence?
At a certain point, it starts looking like such coincidence is unlikely to not be deeply meaningful. Yeah.
The circumstantial evidence is overwhelming, but it could.
But you're always open to a total flipping of the table. Yeah,
of course.
How much of the human brain do you think we understand?
I think we're at a weird moment in the history of neuroscience, in the sense that I feel like we understand a lot about the brain at a very high level, but a very, very coarse level.
When you say high level, what are you thinking? Are you thinking functional? Are you thinking structurally?
Yeah. So, in other words, what is the brain for? What kinds of computation does the brain do? What kinds of behaviors would we have to explain if we were going to look down at the mechanistic level? And at that level, I feel like we understand much, much more about the brain than we did when I was in high school. But it's almost like we're seeing it through a fog. It's only at a very coarse level. We don't really understand what the neuronal mechanisms are that underlie these computations. We've gotten better at saying, what are the functions that the brain is computing that we would have to understand, if we were going to get down to the neuronal level. And at the other end of the spectrum, we in the last few years, incredible progress has been made in terms of technologies that allow us to see, actually literally see in some cases, what's going on at the single unit level, even the dendritic level. And then there's this yawning gap in between.
Oh, that's interesting. So at the high level, so that's almost like cognitive science level.
Yeah.
And then at the neuronal level, that's neurobiology and neuroscience.
Yeah.
Just studying single neurons, the synaptic connections and all the dopamine, all the kind of neurotransmitters.
One blanket statement I should probably make is that as I've gotten older, I have become more and more reluctant to make a distinction between psychology and neuroscience. To me, the point of neuroscience is to study what the brain is for. If you're a nephrologist and you want to learn about the kidney, you start by saying, what is this thing for? Well, it seems to be for taking blood on one side that has metabolites in it that shouldn't be there, sucking them out of the blood while leaving the good stuff behind, and then excreting that in the form of urine. That's what the kidney is for. It's like obvious. So the rest of the work is deciding how it does that. And this, it seems to me, is the right approach to take to the brain. You say, well, what is the brain for? The brain, as far as I can tell, is for producing behavior. It's for going from perceptual inputs to behavioral outputs. And the behavioral outputs should be adaptive. So that's what psychology is about. It's about understanding the structure of that function. And then the rest of neuroscience is about figuring out how those operations are actually carried out at a mechanistic level.
That's really interesting. But so unlike the kidney, the brain, the gap between the electrical signal and behavior. So you truly see neuroscience as the science of that touches behavior, how the brain generates behavior, or how the brain converts raw visual information into understand. Like you basically see cognitive science, psychology, and neuroscience as all one science.
Yeah. It's
a
a personal statement.
Is that a hopeful or a realistic statement? So certainly you will be correct in your feeling in some number of years, but that number of years could be 200, 300 years from now.
Oh, well,
Is that aspirational or is that pragmatic engineering feeling that you have?
It's both, in the sense that this is what I hope and expect will bear fruit over the coming decades. But it's also pragmatic in the sense that I'm not sure what we're doing in either psychology or neuroscience if that's not the framing. I don't know what it means to understand the brain if part of the enterprise is not about understanding the behavior that's being produced.
I mean, yeah, but I would compare it to maybe astronomers looking at the movement of the planets and the stars, and without any interest of the underlying physics, right? And I would argue that there, at least in the early days, there is some value to just tracing the movement of the planets and the stars without thinking about the physics too much, because it's such a big leap to start thinking about the physics before you even understand even the basic structural elements of.
Oh, I agree with that. I agree.
But you're saying in the end, the goal should be to deeply understand.
Well, right. And I think, so I thought about this a lot when I was in grad school, because a lot of what I studied in grad school was psychology. And I found myself a little bit confused about what it meant to, it seems like what we were talking about a lot of the time were virtual causal mechanisms. Like, attentional selection then selects some object in the environment, and that is then passed on to the motor, information about that is passed on to the motor system. But these are virtual mechanisms. These are, they're metaphors. There's no reduction going on in that conversation to some physical mechanism that, which is really what it would take to fully understand, how behavior is arising. The causal mechanisms are definitely neurons interacting. I'm willing to say that at this point in history. So in psychology, at least for me personally, there was this strange insecurity about trafficking in these metaphors, which were supposed to explain the function of the mind. If you can't ground them in physical mechanisms, then what is the explanatory validity of these explanations? And I managed to soothe my own nerves by thinking about the history of genetics research. So I'm very far from being an expert on the history of this field, but I know enough to say that Mendelian genetics preceded Watson and Crick, and so there was a significant period of time during which people were productively investigating the structure of inheritance using what was essentially a metaphor, the notion of a gene, and genes do this and genes do that. But, where are the genes? They're sort of an explanatory thing that we made up. And we ascribe to them these causal properties. Oh, there's a dominant, there's the recessive, and then they recombine it. And then later there was a kind of blank there that was filled in with a physical mechanism. That connection was made. But it was worth having that metaphor, because that gave us a good sense of what kind of causal mechanism we were looking for. Right?
And the fundamental metaphor of cognition, you said, is the interaction of neurons. Is that what is the metaphor?
No. The metaphor, the metaphors we use in cognitive psychology are things like attention, the way that memory works. I retrieve something from memory, right? A memory retrieval occurs. What is that? That's not a physical mechanism that I can examine in its own right. But but it's still worth having that metaphorical level, right?
Yeah. So I misunderstood actually. So the higher level abstractions is the metaphor that's most useful.
Yes.
But what about? So how does that connect to the idea that arises from interaction of neurons? Well, even is the interaction of neurons also not a metaphor to you? Is it literally? Like that's no longer a metaphor. That's already the lowest level of abstractions that could actually be directly studied.
Well, I'm hesitating because I think what I want to say could end up being controversial. So what I want to say is, yes, the interactions of neurons, that's not metaphorical. That's a physical fact. Yeah. That's where the causal interactions actually occur. Now, I suppose you could say, well, even that is metaphorical relative to the quantum events that underlie. I don't want to go down that rabbit hole.
It's always turtles on top of turtles. Yeah,
but turtles all the way down. There's a reduction that you can do. You can say these psychological phenomena can be explained through a very different kind of causal mechanism, which has to do with neurotransmitter release, and so what we're really trying to do in neuroscience writ large, as I say, which for me includes psychology, is to take these psychological phenomena and map them onto neural events. I think remaining forever at the level of description that is natural for psychology, for me personally, would be disappointing. I want to understand how mental activity arises from neural activity. But the converse is also true. Studying neural activity without any sense of what you're trying to explain, to me feels like at best groping around. I
apologize for the romanticized question, but what idea in the space of neuroscience, in the space of the human brain, is to you the most beautiful, mysterious, surprising?
What had always fascinated me, even when I was a pretty young kid, I think, was the paradox that lies in the fact that the brain is so mysterious and seems so distant. But at the same time, it's responsible for the full transparency of everyday life. The brain is literally what makes everything obvious and familiar, and there's always one in the room with you.
Yeah.
I used to teach when I taught at Princeton. I used to teach a cognitive neuroscience course, And the very last thing I would say to the students was, you know, people often, when people think of scientific inspiration, the metaphor is often, well, look to the stars. You know, the stars will inspire you to wonder at the universe and you know, think about your place in it and how things work. And I'm all for looking at the stars, but I've always been much more inspired, and kind of my sense of wonder comes from not from the distant, mysterious stars, but from the extremely intimately close brain.
Yeah.
There's something just endlessly fascinating to me about that.
Just like you said, the one is close and yet distant in terms of our understanding of it. Are you also captivated by the fact that this very conversation is happening because two brains are communicating?
Yes, exactly.
I guess what I mean is the subjective nature of the experience. If we can take a small tangent into the mystical of it, the consciousness, or when you're saying you're captivated by the idea of the brain, are you talking about specifically the mechanism of cognition, or are you also just like, at least for me, it's almost like paralyzing the beauty and the mystery of the fact that it creates the entirety of the experience, not just the reasoning capability, but the experience.
Well, I definitely resonate with that latter thought. And I often find discussions of artificial intelligence to be disappointingly narrow. You know, speaking as someone who has always had an interest in art.
Right. I was just going to go there because it sounds like somebody who has an interest in art.
Yeah. I mean, there are many layers to, you know, to full bore human experience. And in some ways it's not enough to say, oh, well, don't worry. You know, we're talking about cognition, but we'll add emotion, you know?
Yeah.
There's an incredible scope to what humans go through in every moment, and yes, so that's part of what fascinates me, is that our brains are producing that, but at the same time, it's so mysterious to us how. You know, like we literally, like our brains are literally in our heads producing this experience, and yet there's it's so mysterious to us, and the scientific challenge of getting at the actual explanation for that is so overwhelming. That's just, I don't know, that certain people have fixations on particular questions, and that's just always been mine.
Yeah, I would say the poetry of that is fascinating, and I'm really interested in natural language as well. And when you look at artificial intelligence community, it always saddens me how much, when you try to create a benchmark for the community to gather around, how much of the magic of language is lost when you create that benchmark. That there's something we talk about experience, the music of the language, the wit, something that makes a rich experience, something that would be required to pass the spirit of the Turing test, is lost in these benchmarks. And I wonder how to get it back in, because it's very difficult. The moment you try to do like real good, rigorous science, you lose some of that magic. When you try to study cognition in a rigorous scientific way, it feels like you're losing some of the magic. The seeing cognition in a mechanistic way that AI at this stage in our history look at.
I agree with you, but at the same time, one thing that I found really exciting about that first wave of deep learning models in cognition was there was the fact that the people who were building these models were focused on the richness and complexity of human cognition. So an early debate in cognitive science, which I sort of witnessed as a grad student, was about something that sounds very dry, which is the formation of the past tense. But there were these two camps. One said, well, the mind encodes certain rules, and it also has a list of exceptions, because of course, the rule is add ed, but that's not always what you do. So you have to have a list of exceptions. And then there were the connectionists who, evolved into the deep learning people, who said, well, if you look carefully at the data, if you actually look at corpora, like language corpora, it turns out to be very rich, because yes, there are most verbs that, and you just tack on ed, and then there are exceptions, but there are rules that there's the exceptions aren't just random. There are certain clues to which verbs should be exceptional, and then there are also exceptions to the exceptions. And there was a word that was kind of deployed in order to capture this, which was quasi-regular. In other words, there are rules, but it's messy, and there's structure even among the exceptions, and it would be, you could try to write down this structure in some sort of closed form, but really the right way to understand how the brain is handling all this, and by the way, producing all of this, is to build a deep neural network and train it on this data and see how it ends up representing all of this richness. So the way that deep learning was deployed in cognitive psychology was the spirit of it. It was about that richness. And that's something that I always found very, very compelling. Still do.
Is there something especially interesting and profound to you in terms of our current deep learning neural network, artificial neural network approaches, and whatever we do understand about the biological neural networks in our brain? There's quite a few differences. Are some of them to you either interesting or perhaps profound in terms of the gap we might want to try to close in trying to create a human level intelligence?
What I would say here is something that a lot of people are saying, which is that one seeming limitation of the systems that we're building now is that they lack the kind of flexibility, the readiness to sort of turn on a dime when the context calls for it, that is so characteristic of human behavior. So,
is that connected to you which aspect of the neural networks in our brain is that connected to? Is that closer to the cognitive science level of, now again, see, like my natural inclination is to separate it into three disciplines of neuroscience, cognitive science, and psychology. And you've already kind of shut that down by saying you're kind of see them as separate, but just to look at those layers, I guess, is there something about the lowest layer of the way the neurons interact that is profound to you in terms of its difference to the artificial neural networks? Or is all the key differences at a higher level of abstraction?
One thing I often think about is that
you were involved with Google Brain since its start in 2011 with Jeff Dean. It started with Disbelief, the proprietary machine learning library, and turned into TensorFlow in 2014, the open source library. So what were the early days of Google Brain like? What were the goals, the missions? How do you even proceed forward once there's so much possibilities before you?
It was interesting back then, when I started, or when you were even just talking about it. The idea of deep learning was interesting and intriguing in some ways. It hadn't yet taken off, but it held some promise. It had shown some very promising and early results. I think the idea where Andrew and Jeff had started was, what if we can take this, what people are doing in research, and scale it to what Google has in terms of the compute power, and also put that kind of data together? What does it mean? And so far the results had been, if you scale the compute, scale the data, it does better. And would that work? And so that was the first year or two. Can we prove that out, right? And with Disbelief, when we started the first year, we got some early wins, which is always great.
What were the wins like? What was the wins where you were
there's some promise to this. This is going to be good.
I think the two early wins were, one was speech, that we collaborated very closely with the speech research team who was also getting interested in this. And the other one was on images, where we, the cat paper, as we call it, that was covered by a lot of folks.
And the birth of Google Brain was around neural networks. It was deep learning from the very beginning. That was the whole mission.
Yep.
So what would, in terms of scale, what was the sort of dream of what this could become? Like, were there echoes of this open source TensorFlow community that might be brought in? Was there a sense of TPUs? Was there a sense of like machine learning is now going to be at the core of the entire company, is going to grow into that direction?
Yeah, I think so. So that was interesting. And like, if I think back to 2012 or 2011, and first was, can we scale it? In the year or so, we had started scaling it to hundreds and thousands of machines. In fact, we had some runs even going to 10,000 machines, and all of those shows great promise. In terms of machine learning at Google, the good thing was Google's been doing machine learning for a long time. Deep learning was new, but as we scaled this up, we showed that yes, that was possible, and it was going to impact lots of things. Like, we started seeing real products wanting to use this. Again, speech was the first. There were image things that photos came out of, and then many other products as well. So that was exciting. As we went into with that a couple of years, externally also academia started to, there was lots of push on, okay, deep learning's interesting, we should be doing more, and so on. And so by 2014, we were looking at, okay, this is a big thing. It's going to grow. And not just internally, externally as well. Yes, maybe Google's ahead of where everybody is, but there's a lot to do. So a lot of this started to make sense and come together.
So what are the differences and similarities between the human brain and a computer with the microprocessor at its core? Let's start with the philosophical question, perhaps.
Well, since people don't actually understand how human brains work, I think that's true.
I think that's true.
So it's hard to compare them. Computers are, there's really two things. There's memory and there's computation, right? And to date, almost all computer architectures are global memory, which is a thing, right? And then computation, where you pull data in, you do relatively simple operations on it and write data back.
So it's decoupled in modern computers. Right. And you think in the human brain, everything's a mess that's combined together.
What people observe is there's, some number of layers of neurons which have local and global connections, and information is stored in some distributed fashion. And people build things called neural networks in computers, where the information is distributed in some kind of fashion. There's a mathematics behind it. I don't know that the understanding of that is super deep. The computations we run on those are straightforward computations. I don't believe anybody has said a neuron does this computation. So to date, it's hard to compare them.
Because the ideal life form idea is mine that I really think about a lot.
I think about it on a technical side, by the way. Like, I when I heard you say that, because I've been thinking, I was like, whoa, that's interesting. That
they might be alive. Because I don't know what the fuck they are, but when someone has an idea for, an invention, a toaster, and then they think about this, all it needs is like these heating elements and a spring, and then it pops when it's done, so I have a timer, and then they build this thing. Now all of a sudden it's alive. It's like you manifested it in a physical form. A toaster's not the best example, but a car, an airplane, you're thinking about a thing, like an idea comes into your head. And you could say, oh, well, it's just creativity. It's a part of being a person. It's how we invented tools and how, we became better hunters. All those things are true. I'm not saying that there's some magic to what I'm saying, but there's also a possibility that we're simplifying something by saying that it's just creativity, that it's just a natural human inclination to invent things. But why? Is it possible that ideas like creativity, like we are the only animal other than there's a few species that create things like bees make beehives, but they're very uniform. Some animals use tools, like, chimps will use like sticks to get termites and things like that. But there's something about what we do it makes you wonder, because we look at just look at this room that we're in. Look at all these electronics. Look at all this crazy shit that human beings have invented and then built upon others' inventions, improved and innovated. These all came out of ideas. Like the idea, it germinates in someone's head. It bounces around. They write it down. They share it with others. The other people who have similar ideas or ideas that are complementary, they work together and they change the world.
And the new thing in that is the ideas, not the people. It's like we think we found the ideas, but it's more like the ideas found us.
Find you. Yeah, they're literally in the air.
Yeah.
They come to you. I always felt like that with bits. Like when I come up with a bit, that's why I'm always telling people about the Stephen Pressfield book, The War of Art, because he talks about respecting the muse and the idea that your ideas come when you sit down and you do the work, or you sit down like a professional and you talk to the muse. Like, come tell me what to do. Like if the muse was a real thing, as if the muse is like some mystical creature that comes and delivers you ideas. Even if that's not real, that's how it works.
Yeah.
It does work like that. If you do treat it like it's a muse and you treat it with the respect and you treat it like a professional, the ideas do come to you.
I never thought about what he's doing. He's just sitting there waiting for the idea that's trying to breed to find him.
Yeah.
That's a trippy thing.
If you show up,
trippy.
If you show up and put in the time and focus your energy on that, the ideas, they will arrive. They will arrive. And that's the same with writing comedy. Like there's been many, many times where I'll come home from the comedy store and I just sit down and I start writing and I got nothing. There's nothing there. I'm just writing. It's all bullshit. Nothing's good. It's just like, and then all of a sudden, bam, there's the idea. And then all of a sudden I can't stop. And then, a couple hours later and I'm like, whoa. And then the next night I'm on stage and I'm like, how about that? Yeah. Boom! It gets this big laugh. I'm like, holy shit. And I know that came out of the discipline to sit down and call the muse.
I mean, the cool thing is the ideas have found you to like, oh, I'm going to use this dude. Like he seems to have a podcast that's popular. I'm going to breed inside his brain and spread it to others. It's the same as...
or an inventor. I'm going to use this guy who's like desperately seeking some sort of a product to bring to market. Some guy who wants to invent things, is thinking about inventing things all the time. Like these ideas, they weasel their way into your head. And it seems to me also that the frequency that your mind operates under has to be correct. Because one of the things about creativity seems to be, if you think about yourself a lot, if you're really into yourself or your image or you're selfish, those ideas they don't find you.
Yeah, it's funny.
The
it stifles the creative. It stifles the opportunity that the idea has to finding.
Yes, which is one of the reasons why joke thieves, people that steal jokes, are terrible writers. There's never like really good writers who are also joke thieves. It's just joke thieves, and then when they have to write on their own, if they get exposed, they become terrible comedians. They're a shadow of what they were when they were stealing other people's ideas. Because the thing that would make you steal a person's idea is that ego part, the wanting to claim it for yourself, the wanting to be the man. Or the woman. I want to be the person who gets out there and says it, and everybody's gonna love me for it. Like you can't think like that and be creative. It requires a humility and it requires a detachment from self in order to create. Like when I'm writing, I'm blank. I'm just staring. I'm just the part of my mind that's active is not like me. It's like this weird core function part where I'm not aware of my personality. I'm not aware of anything. Yeah. I'm just trying to put it together in a way that I know works.
Yeah, just being there, being present. That's what Pressfield is. Just, I'm a big believer just sitting there, even staring at a blank page.
You have to.
Putting in the time.
Yeah. And sometimes it's not that way. Sometimes it's an inspiration. Like sometimes I'll be sitting there at dinner and I'll be like, I'll be right. I got an idea. And my wife's really cool about that. I'm like, I have an idea. And I blah, blah, blah. I have to just run out of the room real quick and I write it down on my phone and then I can come back, because those are like little gifts that you get sometimes from the universe out of nowhere. And some people rely only on those gifts, and I've talked to comics about it, like, I can't come up with my best ideas when I don't write. And I'm like, no, I do too. I come up with great ideas when I don't write, but I also write. Like, you can do both of those things. They're not mutually exclusive.
Can we just pause on that just for me, from a human factors perspective and also an AI perspective? How difficult, so there's when there's two people, there's also a third person that's the AI part. There's some level of automation, like autopilot maybe even.
That's correct.
Maybe you can kind of talk about the psychology of, like you said, making decisions really quick, 80%. How do you deal with another brain working with you? And then also the automation. Is there an interesting interplay that you get to learn? And also, as that changed throughout your career, I imagine it gotten better in terms of the automation, or perhaps not.
Well, I can tell you. So that let's.
Sorry, there's a bunch of
start
questions
this.
in
No,
there.
this is good. This is good, and this is I'm enjoying this because now we actually get to talk about something other than a Tic Tac. So, so let's start with the A6. The A6 was really an analog airplane that was built in the '60s. All right, and there's been studies done on the crew coordination, which is the interaction between the pilot and the bombardier navigator. So we would fly low at night in the mountains. So I was stationed up in Whidbey Island, Washington. So you've got the Cascades and incredible amount of time. And we would get in the simulators because unlike normally people think terrain following, and there's the radars, the 111, the B1 has a system like this, but the radar can see and it'll fly. It basically flies a straight line. So it goes up and over mountains and back down and up and over mountains, where the A6 was really manual. So you do this low-level routes where you're gonna fly in the mountains at night. You're gonna be at 500 to 1,000 feet above the ground, ripping through like fog layers because you don't need to see outside. You're literally flying a little TV screen and a radar.
What are you looking at most of the time? So you just as a screen.
It's this really primitive. If you look at it now, what we did, you'd think, wow, that was crazy, but it was really fun. So
Is it similar to like the FLIR stuff?
No.
This
thing is totally radar based. Now the airplane had a FLIR ball. It's target recognition and multi-sensor. It was called a tram.
You're looking at like basically like dots of hard objects.
No, actually what it is the bombardier navigator had a radar and he was getting raw feed off of a pulse radar in front. Okay, so it's just basically mapping the mountain. So if you look at a mountain on a radar and you're coming up on it, the front side is going to give you a really bright return, and then the back side it's just going to be a giant shadow because you can't see on the other side. So the bombardier navigators would do that, and they would have charts, and they could shade their charts, knowing that hey, if we turn a little bit left here, we can get in this valley, we can sneak up this valley, and then go around the back side of the mountain, which is what the airplane would do.
And sorry to interrupt. I'm going to just keep asking dumb questions. I apologize. But the pilot, can you at a high level say what the pilot does versus the bombardier?
Yes. So
you're actually just control.
I'm flying the jet. I have the throttles, the stick, and literally. I have it's about probably a 4-inch or 6-inch wide by maybe 4 inches, 5 inches high. It looks like it's literally a CRT. That's how old it is. A CRT screen. And what the radar would do is the bombardier navigator is looking at his radar and he's looking out about 12 and a half miles in front of the airplane. So he has the range really scoped down because the radar can see a lot further. He's looking at about 12 and a half miles when we're in the terrain mode where we're dodging mountains and stuff. And what the pilot has is they're called range bins, and there's 8 of them. So the very far range bin is the 12 and a half mile, and the closest range bin, it's a thing, and it'll be like between like a half a mile or a quarter mile to 3/4 of a mile. And the next one might be 3/4 of a mile to 2 miles. And then it just keeps going out like that. So if there's a mountain in front, let's say we're on a flat plane and there's a mountain out in the distance at 15 miles and we're just driving right at it. So when we get to the point where it hits 12 and a half miles where the radar is going to see it on his scope, my range bin for that would pop up and it would show like a big bump, like a mountain. Mm-hmm. And then as I got closer to it, the next range bin would pop up and show it. Mm-hmm. And I could see that bump was moving towards me. And then if I turned a little bit, to go over here, I'd see the mountain go over to the right-hand side and I could do that. But it wasn't like a video game. It's literally like, if you think of the original Ataris.
Yeah. But you build up, I imagine, that you start to get a really deep sense of like the actual 3D environment based on that little Atari style display.
You're exactly right. And you have to, you have to train. So there's been studies. As a matter of fact, a lot of the basis, and people will probably argue with me, but it's true. There were studies done watching A6 crews in our simulators. We called it the WIST, the Weapons Systems Trainer. And it was not even a motion. It just kind of sat there, and you could fly these things, and they had terrain that they would inject into the system. But the crew coordination. So my first fleet bombardier navigator, who I'll name him. His name's Chris Sato. He's works at Apple, pretty high up, MIT grad. Awesome. I think computer engineering. He's scary smart. So Chris could really work. And matter of fact, all the guys I flew with, so there's another guy, Matt, who also worked at Apple, who's now at SAP. We did our first night traps together. The bond between us, I mean, it's one of those things that you're never going to forget. But Chris and I, when we started flying together, we were actually the most junior crew in the squadron. We'd spent a lot of time training, and Chris was amazing at how he could work the system. One, because he was extremely brilliant, and he had that inquisitive mind of, we could do all these different things, and there's all these degradation modes. But we spent a lot of time to see how good we could actually get, because, and it's, you almost talk in partials. So as the BN is looking at his radar scope, Chris would say, I've got rising terrain. That's just what they say, showing rising terrain at 12 miles. And I'd see the little bump, and I'd say, got it. This is going to go to your question on the autonomy and how you work with two heads.
Yes.
So when you first get together, the interaction, it's almost like you have to rehearse it. You have to know, and you talk in full sentences. The more and more we fly together, Chris could go, I'm showing, and he'd get like rising out. And before he finished, I'd say, I've got it. So you end up starting to talk in partials, because I have to trust him. Like, I mean, I can have no doubt that he knows how to do his job, because I'm literally looking at this little scope that's not giving me this continuous picture of that mountain moving. Remember, the mountain's here, and then it's going to pop up here, and then it's going to pop up here, because there's gaps in the coverage on how the system was set up. Remember, it's an analog system, to where he is telling me, like, I can't see all the way to the left, and he's got a wider scope on the radar, but my screen doesn't show that. So he's telling me, start a left turn.
How to avoid the mountain.
Start a hard turn, and we would do that. So my trust.
And this is all happening quick?
Very quick. Well, we would typically fly between 420 and 480 knots of ground speed. How
many miles an hour?
420 is 7 miles a minute.
Okay.
Or between 7 and 8 miles a minute is what you're flying.
That's fast.
At night. I mean, I broke out of clouds. I mean, I remember him and I flying. We were on its IR, it's called an IR route, an instrument route that's low. They're all around the country. There's the IR 344 that we used to fly, which would coast in off of Oregon. You'd fly from the land, you go out over the ocean, turn around, and then you could practice actually coming in on a coastline. And we were flying, and we ended up in the clouds. Keep in mind, we're between 500 and 1,000 feet in the mountains, and we're in the clouds. Like, you can't see anything. And I had to turn off our red lights that flash. They're called the anti-collision lights. Mm-hmm. Because it was reflecting off the clouds, and it starts to bother you. It just gets annoying. So I turned it off, and we're flying. We break out of that coastal marine layer, and poof, we break out. And it's a decent night. And this is right by Mount St. Helens. This is kind of where we're coming in. So we're coming in from the east, and we're just north of Mount St. Helens is where the route goes. And you look up, because you can kind of see the silhouette of this mountain that's right next to you. But you're flying along. You're just like, you got to trust. And you can see houses. You can see the lights. They're above you. We're literally below people's houses flying down these valleys and stuff. So just incredible experience. So when you take that and then you move into an F-18F. So now we're into modern technology that was actually built in this century. And you're flying. So now, the Wizzo is behind us, and we're not doing those night low levels, but that same type of crew coordination that has to happen, because what you're doing is you're sharing the load. So most of the communications that go out of the airplane, the Wizzo does all the talking. He uses his feet. That's the weapons systems operator in the back of an F-18F. So he's going to run, the radar kind of runs itself now, but we have a situational awareness display, and it's linked to all the other airplanes.
Just out of curiosity, what's the situational awareness display? Because that term comes up a lot.
Think of it as a God's eye view. So if you have the back of the Super Hornet the Block 2s has about an 8x10 display for the Wizzos. That they can look at. The pilot's is smaller. It's down between it's a 6x6 between his legs, and they're getting ready to redesign that. Boeing is, but when you looked, it'd be like if you put your airplane and you're looking down. So all the stuff, like if your radar's seeing bad guys out in front of you, it'd be like looking down going, oh, I'm right here. And no, there's bad guys out here. And my wingman is over here. And it shows everything. It's just like, it gives you can look at that display and go, oh,
Okay.
I can see where everything's at. I can see if one guy's trying to target another guy. It shows you all this. It's an incredible amount of knowledge that comes up for the crews to maintain the overall picture of what's going on.
The big picture sense of what's going on.
Because it's happening so fast. And this is with that autonomy piece. This is the third brain. So we're all looking at it, and the third brain is doing fusion. It's pulling stuff together, going, oh, this is all this guy, this is this guy, this is this guy. It's sending it out through the link. So all the airplanes are talking to each other through this digital network, that we don't even see. It just says, that airplane says, hey, I'm over here. And it tells us, and we go, oh, he's right there. And then we can go, his airplane says, oh, I'm looking at this airplane, this bad guy. And it shows us, oh, he's over there and he's looking at this guy. I mean, it's an incredible amount of visual intake, because your eye, you can hear a lot, but when you look down at stuff, it's you can solve the picture really quick.
The third brain is doing the sensor fusion, the integration of the different sensors, and gives you a big picture view. What about the control? Like, is there, and I apologize as if this is a dumb question, but people use the high level term of autopilot. How much is there? Let's use a loose term of AI. How much automation is there? How much AI is there in helping you control the airplane?
The AI piece would be more of a control loop because of the digital flight controls. So the airplane actually, they had to make the airplane easier to fly. And when I say easy, it's relative, because people go, I could do it because I did it on flight sim. Real life is a lot different. In flight sim, you have no apparent fear of death. You'll do things on the simulator that you would never do in real life. But the autonomy in the airplane to allow you to manage, I mean, because you think about it, you've got a radar that's feeding you data, you've got a targeting pod that's feeding you data. All that stuff is hooked to your head because you've got a joint helmet mounted cueing system on that it basically maps the magnetic field in the cockpit so it can tell where your head's at looking. So if I turn my head to the right, the radar will actually look to the right, the targeting FLIR will look to the right. And oh, by the way, the back seater has a helmet on too, so he can look to the left and he can do things. So depending on what sensor he's controlling, so if he's got control of the targeting pod and he looks left, the targeting pod looks left. But if I have something where I want to lock a guy up that I don't see, that maybe the radar didn't see, but I can get over and now point the radar, because it's a phase array radar now, it doesn't really scan. There's all kinds of cool stuff that that technology brings. Because if you'd went back 30 years and said, hey, or 40 years ago and said, hey, we're gonna have this helmet and you're gonna be able to slew everything to your head, and I don't mean a mechanical setup, but I mean literally you're just gonna map magnetic resonance and go, oh look, and I can literally slew my sensors this fast, and then mash a button and transfer high quality coordinates from a system into a joint, a JDAM, which is a joint direct attack munition that is the GPS bombs that you see all the time, and then let that thing fly. And I'm solving this problem in seconds, vice minutes, or, hey, I got it. We're going to have to mensurate coordinates. And you bring back the data and then they do all the targeting for it. And then they send another group out to get it. Instead of all that, now it's that fast.
So there's we probably don't have enough time to talk about the beautiful fusion of minds that happens when two people are flying, controlling the plane. But at a high level, this is a really interesting question for people who don't know what they're talking about, like me, which is, what is the difference between a human being and an AI system? Like, what is the ceiling of a current AI technology for controlling the plane? Like, how much does the human contribute? Is it possible to have automated flight, for example? Like, what is the hardest part about flying that a human does expertly that an AI system cannot? In warfare situations, in flying a fighter jet plane.
So I would say AI systems are usually black and white. When you write the algorithm for an AI system, it's basically you're taking thought and turning it into a giant math problem is really what you're doing, right? So you've got this logical math problem. Math problems are there's a line. It says I can or I can't, and it's a very finite line, but you can go up to the line. Where a human, we all have gray areas where we go, maybe, yeah, I'll try it.
So humans can operate within that gray.
So if you take an airplane and say, and I'll just take a Hornet for a while, a Super Hornet, doesn't matter, any airplane, and you go, here is the flight performance model of the airplane. So if you know what an EM diagram is, the energy. So it basically says the airplane can fly as slow as this, it can go as fast as this, it can pull this many G's, force of gravity, so 1, 2, 3, 4, 5, 6, 7. And then based on the airfoil design and everything else and how it can pull, here's how it's going to fly, because it's really physics based. Well, depending on how you write the AI, but typically AI, you don't want the airplane to leave controlled flight, right? You want to maintain it so that it is flying in a controlled envelope. Or there are times, and you can go back to World War I, where people intentionally departed the airplane from controlled flight in order to obtain an advantage, that's where the human goes, can I do this? I know it's outside of where I would normally go, but I can do that. So you can do some crazy things now, especially since the flight control logic in modern airplanes with digital flight controls, they're extremely forgiving. So you can literally, I've done things in Super Hornets that literally, even as a pilot inside the airplane, you're just like, wow, I cannot believe it just did that. Like it'll flop ends, which defies most logic. And I guess, in a way you could probably program it, but I still think that when you get to the edges that may or may not give you an advantage, there are things that a human will do that AI won't. And I don't think we've got to the point, because how do you map illogical solutions? Most AI is logical. It's based on some type of premise. When you write the algorithm to control it, there's bounds.
So you're saying that there is a gap between the computer or the machine that performs computation and this machine that appears to have consciousness and intelligence.
Yeah.
Can we
that piece of meat in your head?
Piece of meat.
And maybe it's not just the meat in your head, it's the rest of you too. I mean, you actually have a neural system in your gut.
I tend to also not believe, but we're now dancing around things we don't know. But I tend to believe other humans are important. Like, so we're almost like, I just don't think we would ever have achieved the level of intelligence we have with other humans. I'm not saying so confidently, but I have an intuition that some of the intelligence is in the interaction.
Yeah, and I think I think it seems to me very likely. Again, this is speculation, but our species, and probably Neanderthals to some extent, because you can find old bones where they seem to be counting on them by putting notches that were Neanderthals had done. We're able to put some of our stuff outside our body into the world, and then other people can share it. Mm-hmm. And then we get these tools that become shared tools. And so there's a whole coupling that would not occur in, the single deep learning network, which was fed, all of literature or something.
Yeah, the neural network can't step outside of itself. But is there some? Can we explore this dark room a little bit and try to get at something? What is the magic? Where does the magic come from in the human brain that creates the mind? What's your sense as scientists that try to understand it and try to build it? What are the directions that, if followed, might be productive? Is it creative, interactive robots? Is it creating large, deep neural networks that do like self-supervised learning, and just like we'll discover that when you make something large enough, some interesting things will emerge? Is it through physics and chemistry and biology, like artificial life angle, like we'll sneak up in this 4-quadrant matrix that you mentioned? Is there anything you're most, if you had to bet all your money, financial advice?
I wouldn't.
Okay.
So every intelligence we know, and includes, animal intelligence, dog intelligence, octopus intelligence, which is a very different sort of architecture from us. All the intelligences we know perceive the world in some way, and then have action in the world, but they're able to perceive objects in a way which is actually pretty damn phenomenal and surprising. We tend to think, that the box over here between us, which is a sound box, I think, is a blue box. But blueness is something that we construct with color constancy. The blueness is not a direct function of the photons we're receiving. It's actually context, which is why you can turn, you've maybe seen the examples where someone turns a stop sign into some other sort of sign by just putting a couple of marks on them, and the deep learning system gets it wrong, and everyone says, but the stop sign's red. Why is it think it's the other sort of sign? Because redness is not intrinsic in just the photons. It's actually a construction of an understanding of the whole world and the relationship between objects to get color constancy. But our tendency, in order that we get an archive paper really quickly, is you just show a lot of data and give the labels and hope it figures it out. But it's not figuring it out in the same way we do. We have a very complex perceptual understanding of the world. Dogs have a very different perceptual understanding based on smell. They go smell a post. They can tell how many different dogs have visited it in the last 10 hours and how long ago. There's all sorts of stuff that we just don't perceive about the world. And just taking a single snapshot is not perceiving about the world. It's not perceiving the registration between us and the object. And registration is a philosophical concept. Brian Cantwell Smith talks about it a lot. Very difficult, squirmy thing to understand. But I think none of our systems do that. We've always talked in AI about the symbol grounding problem, how our symbols that we talk about are grounded in the world. And when deep learning came along and started labeling images, people said, the grounding problem has been solved. No, the labeling problem was solved with some percentage accuracy, which is different from the grounding problem.
So you agree with Hans Moravec and what's called the Moravec's paradox that highlights this counterintuitive notion that reasoning is easy, but perception and mobility are hard.
Yeah, we shared an office when I was working on computer vision and he was working on his first mobile robot.
What were those conversations like?
They were great.
So do you still kind of, maybe you can elaborate, and do you still believe this kind of notion that perception is really hard? And like, can you make sense of why we humans have this poor intuition about what's hard and not?
Well, let me give a sort of another story.
Sure.
If you go back to the original teams working on AI from the late 50s into the 60s, and you go to the AI lab at MIT, who was it that was doing that? Was a bunch of really smart kids who got into MIT, and they were intelligent. So what's intelligence about? Well, the stuff they were good at, playing chess, doing integrals. That was hard stuff.
Yeah.
But, a baby could see stuff. That wasn't intelligent. Anyone could do that. That's not intelligence. Yes. And so there was this intuition that the hard stuff is the things they were good at, and the easy stuff was the stuff that everyone could do.
Yeah.
And maybe I'm overplaying it a little bit, but I think there's an element of that.
Yeah, I mean, I don't know how much truth there is to, like chess, for example, was for the longest time seen as the highest level of intellect, right?
Until we got computers that were better at it than people. And then we realized, but if you go back to the 90s, you'll see, the stories in the press around when Kasparov was beaten by Deep Blue. Oh, this is the end of all sorts of things. Computers are going to be able to do anything from now on. And we saw exactly the same stories with AlphaZero, the Go playing program.
Yeah. But still, to me, reasoning is a special thing. And perhaps...
No, we're really bad at reasoning. We just use these analogies based on our hunter-gatherer intuitions.
But why is that not... Don't you think the ability to construct metaphor is a really powerful thing?
Oh, like, yeah, it is.
Stories.
It is. It's the constructing the metaphor and registering that to something constant in our brains.
Like, isn't that what we're doing with vision too? And
We're telling our stories. We're constructing good models of the world.
Yeah, but I think we jumped between what we're capable of and how we're doing it. Right there, there was a little confusion that went on.
Sure.
As we were telling each other stories. There.
Yes, exactly. Trying to delude each other. No, I just think I'm not exactly. So I'm trying to pull apart this Moravec's paradox.
I don't view it as a paradox. What did evolution spend its time on?
Yes,
it spent its time on getting us to perceive and move in the world. That was 600 million years as multi-cell creatures doing that, and then it was relatively recent that we were able to hunt or gather, or even animals hunting. That's much more recent. And then anything that we speech, language, those things are just a couple of 100,000 years, probably, if that long. And then agriculture, 10,000 years. All that stuff was built on top of those earlier things, which took a long time to develop.
So if you then look at the engineering of these things, so building it into robots, what's the hardest part of robotics, do you think? As through the decades that you worked on robots, in the context of what we're talking about, vision, perception, the actual sort of the biomechanics of movement. I'm kind of drawing parallels here between humans and machines always. What do you think is the hardest part of robotics?
I sort of think all of them. There are no easy parts to do well. We sort of go reductionist and we reduce it to, if only we had all the location of all the points in 3D, things would be great. If only we had labels on the images, things would be great. But as we see, that's not good enough. Some deeper understanding.
But if I came to you and I could solve one category of problems in robotics instantly, what would give you the greatest pleasure? Is it you look at robots that manipulate objects. What's hard about that? Is it the perception? Is it the reasoning about the world, like common sense reasoning? Is it the actual building a robot that's able to interact with the world? Is it like human aspects of a robot that's interacting with humans and that game theory of how they work well together?
Well, let's talk about manipulation for a second, because I had this really blinding moment. I'm a grandfather, so grandfathers have blinding moments.
Yes.
Just 3 or 4 miles from here, last year, my 16-month-old grandson was in his new house. First time, right? First time in this house. And he'd never been able to get to a window before, but this had some low windows. And he goes up to this window with a handle on it that he's never seen before. And he's got one hand pushing the window and the other hand turning the handle to open the window. Mm-hmm. He knew two different hands, two different things he knew how to put together.
Yeah.
And he's 16 months old.
And there you are watching in awe.
Yeah. Well, in an environment he'd never seen before, a mechanism he'd never seen.
How did he do that?
Yes, that's a good question. How did he do that? That's why.
It's like, okay, like you could see the leap of genius from using one hand to perform a task to combining to doing. I mean, first of all, in manipulation, that's really difficult. It's like two hands, both necessary to complete the action.
And completely different. And he'd never seen a window open before.
Huh.
But he inferred somehow handle open something.
Yeah. There may have been a lot of slightly different failure cases that you didn't see. Yeah. Not with a window, but with other objects of turning and twisting and handles.
Well, there's a great counter to, reinforcement learning. We'll just give the robot you give the robot plenty of time to try everything.
Yes.
Actually, can I tell a little side story here? So I'm in DeepMind in London. This is 3-4 years ago, where there's a big Google building, and then you go inside and you go through this more security, and then you get to deep mind where the other Google employees can't go.
Yeah.
And I'm in a conference room, bare conference room with some of the people, and they tell me about their reinforcement learning experiment with robots, which are just trying stuff out. And they're my robots. They're Sawyers that we sold them. And they really like them because Sawyers are compliant and can sense forces, so they don't break when they're bashing into walls. They stop and they do all the stuff. And, so you just let the robot do stuff, and eventually it figures stuff out.
By the way, Sawyer, we're talking about robot manipulation, so robot arms and so on.
Yeah, Sawyer's a robot.
Yeah. What's Sawyer?
Sawyer's a robot arm that my company, Rethink Robotics, built.
Thank you for the context.
Yeah, sorry.
Okay, cool. So we're in deep mind.
And it's in the next room. These robots are just bashing around to try and use reinforcement learning to learn how to act. And can I go see them? Oh no, they're secret. They were my robots that were secret.
That's hilarious. Okay.
Anyway, the point is, this idea that you just let reinforcement learning figure everything out is so counter to how a kid does stuff. So, again, story about my grandson. I gave him this box that had lots of different lock mechanisms. He didn't randomly, and he was 18 months old. He didn't randomly try to touch every surface or push everything. He found he could see where the mechanism was, and he started exploring the mechanism for each of these different lock mechanisms. And there was reinforcement, no doubt, of some sort going on there. But he applied a pre-filter which cut down the search space dramatically.
I wonder to what level we're able to introspect what's going on, because what's also possible is you have something like reinforcement learning going on in the mind in the space of imagination. So like you have a good model of the world you're predicting, and you may be running those tens of thousands of like loops, but you're like, as a human, you're just looking at yourself trying to tell a story of what happened, and it might seem simple, but maybe there's a lot of computation going on.
Whatever it is, but there's also a mechanism that's being built up. It's not just random search. That mechanism prunes it dramatically.
Yeah, that pruning step, but it doesn't. It's possible that's so. You don't think that's akin to a neural network inside a reinforcement learning algorithm? Is it possible?
It's until it's possible. I'll be incredibly surprised if that happens. I'll also be incredibly surprised that, after all the decades that I've been doing this, where every few years someone thinks, now we've got it. Mm-hmm. Now we've got it. 4 or 5 years ago, I was saying, I don't think we've got it yet. And everyone was saying, oh, you don't understand how powerful AI is. I had people tell me, you don't understand how powerful it is. I sort of had a track record of what the world had done to think, well, this is no different from before. Oh, we had bigger computers. We had bigger computers in the 90s, and we could do more stuff.
Yeah. But okay, so let me push back, because I'm generally sort of optimistic and try to find the beauty in things. I think there's a lot of surprising and beautiful things that neural networks, this new generation of deep learning revolution, has revealed. To me, it has continually been very surprising, the kind of things it's able to do. Now, generalizing that over, saying like this, we've solved intelligence, that's another big leap. But is there something surprising and beautiful to you about neural networks that where actually you sat back and said, I did not expect this?
Oh, I think their performance on ImageNet was shocking.
So computer vision, those early days, was just very like, wow, okay.
That doesn't mean that they're solving everything in computer vision we need to solve, or in vision for robots.
What about AlphaZero and self-play mechanisms and reinforcement learning? Isn't that?
Yeah, that was all in Donald Mickey's 1961 paper. Everything there was there, which introduced reinforcement learning.
No, but come on. So, no, you're talking about the actual techniques, but isn't it surprising to you the level it's able to achieve with no human supervision of chess play? Like, So to me, there's a big difference between Deep Blue and
maybe what that's saying is how overblown our view of ourselves is. You know,
that chess is easy. Is that?
Yeah, I mean, I came across this 1946 report that, and I'd seen this as a kid in one of those books that my mother had given me, actually. 1946 report, which pitted someone with an abacus against an electronic calculator, and he beat the electronic calculator. You know, so there at that point was, well, humans are still better than machines at calculating. Are you surprised today that a machine can, you know, do 1 billion floating point operations a second, and you know you're puzzling for minutes to do one? So you know,
I am. I mean, I don't know, but I am certainly surprised. There's something to me different about learning. So a system that's able to
learning. Now, see, now you're getting into one of the deadly sins.
Because of using terms overly broadly.
Yeah, I mean, there's so many different forms of learning.
Yeah.
There's so many different forms. You know, I learned my way around the city. I learned to play chess. I learned Latin. I learned to ride a bicycle. All of those are, you know, are very different capabilities.
Yeah.
And if someone, you know, has in the old days, people would write a paper about learning something. Now, the corporate press office puts out a press release about how company X is leading the world because they have a system that can.
Yeah, but here's the thing. Okay, so what is learning? When I refer to
learning is many things,
but
it's a suitcase word.
It's a suitcase word, but loosely, there's a dumb system, and over time, it becomes smart.
Well, it becomes less dumb at the thing that it's doing.
Yeah,
smart
exactly.
is a loaded word.
Yes, less dumb at the thing it's doing.
It gets better performance under some measure.
Yeah,
under some set of conditions at that thing, and most of these learning algorithms, learning systems, fail when you change the conditions just a little bit in a way that humans don't. So,
right,
I was at DeepMind. The AlphaGo had just come out. And I said, what would have happened if you'd given it a 21 by 21 board instead of a 19 by 19 board? They said, failed totally. But a human player would actually, you know, would actually be able to play a game.
And actually, funny enough, if you look at DeepMind's work since then, they're presenting a lot of algorithms that would do well at the bigger board. So they're slowly expanding this generalization. I mean, to me, there's a core element there. It is very surprising to me that even in a constrained game of chess or Go, that through self-play, by a system playing itself, that it can achieve superhuman level performance through learning alone. So, like,
okay, so you know, you didn't.
It's so fundamentally different than search of that.
You didn't like it when I referred to Donald Mickey's 1961 paper. There, in the second part of it, which came a year later, they had self-play on an electronic computer at tic-tac-toe. Okay, it's not as, but it learned to play tic-tac-toe through self-play.
No. That's not,
and it learned to play optimally.
What I'm saying is, I have a little bit of a bias, but I find ideas beautiful, but only when they actually realize the promise. That's another level of beauty. Like, for example, what Bezos and Elon Musk are doing with rockets. We had rockets for a long time, but doing reusable, cheap rockets, it's very impressive. In the same way, I would have not predicted. First of all, when I was started and fell in love with AI, the game of Go was seen to be impossible to solve. Okay, so I thought maybe it'd be possible to maybe have big leaps in a Moore's law style of way in computation that will be able to solve it. But I would never have guessed that you could learn your way. However, I mean, in the narrow sense of learn your way to beat the best people in the world at the game of Go without human supervision, not studying the game of experts.
Okay, so
That's surprising.
using a different learning technique.
Yes.
Arthur Samuel in the early 60s, and he was the first person to use machine learning, had a program that could beat the world champion at checkers. Now,
Yes.
And that at the time was considered amazing. Yeah. By the way, Arthur Samuel had some fantastic advantages.
Yeah.
Do you want to hear Arthur Samuel's advantages?
Please.
Two things. One, he was at the 1956 AI conference. I knew Arthur later in life. He was at Stanford when I was a grad student there. He wore a tie and a jacket every day. Nice. The rest of us didn't. Delightful man. It turns out Claude Shannon, in a 1950 Scientific American article, outlined on chess playing, outlined the learning mechanism that Arthur Samuel used, and they had met in 1956. I assume there was some communication, but I don't know that for sure. But Arthur Samuel had been a vacuum tube engineer on getting reliability of vacuum tubes, and then had overseen the first transistorized computers at IBM. And in those days, before you shipped a computer, you ran it for a week to get early failures. So he had this whole farm of computers running random code for hours and hours a week for each computer. He had a whole bunch of them. So he ran his chess learning program with self-play on IBM's production line. He had more computation available to him than anyone else in the world. And then he was able to produce a chess playing program, a checkers playing program that could beat the world champion. So
that's amazing. The question is, what I mean, surprised, I don't just mean it's nice to have that accomplishment, is there is a stepping towards something that feels more intelligent than before.
Yeah, but
and the question is,
that's in your view of the world.
Okay. Well, let me doesn't mean I'm wrong.
No, no, it doesn't.
So the question is, if we keep taking steps like that, how far that takes us? Are we going to build a better recommender systems? Are we going to build slightly better robots? Okay, or will we solve intelligence?
So, I'm putting my bet on, we're still missing a whole lot.
A lot.
And why would I say that? Well, in these games, they're all, 100% information games. But each of these systems is a very short description of the current state, which is different from registering and perception in the world.
Okay.
Which gets back to Moravec's paradox.
I'm definitely not saying that chess is somehow harder than perception, or any kind of even any kind of robotics in the physical world. I definitely think is way harder than the game of chess. So I was always much more impressed by the workings of the human mind. It's incredible. The human mind is incredible. I believe that from the very beginning. I wanted to be a psychiatrist for the longest time. I always thought that's way more incredible than the game of chess. I think the game of chess is I love the Olympics. It's just another example of us humans picking a task and then agreeing that 1 million humans will dedicate their whole life to that task. And that's the cool thing, that the human mind is able to focus on one task and then compete against each other and achieve weirdly incredible levels of performance. That's the aspect of chess that's super cool. Not that chess in itself is really difficult. It's like the Fermat's last theorem is not in itself, to me, that interesting. The fact that thousands of people have been struggling to solve that particular problem is fascinating.
So can I tell you my disease in this way?
Sure.
Which actually is closer to what you're saying. Yeah. So as a child, I was building various, I called them computers. They weren't general purpose computers.
Ice Cube Tray.
The Ice Cube Tray was one. But I built other machines, and what I liked to build was machines that could beat adults at a game, and the adults couldn't beat my machine.
Yes.
So that was.
So you were like, that's powerful. That's a way to rebel.
Yeah.
I by the way, when was the first time you built something that outperformed you? Do you remember?
Well, I knew how it worked. I was probably 9 years old, and I built a thing that it was a game where you take turns in taking matches from a pile, and either the one who takes the last one or the one who doesn't take the last one wins. I forget. And so it was pretty easy to build that out of wires and nails and little coils that were plugging in the number and a few light bulbs. The one I was prouder of, I was 12 when I built a thing out of old telephone switchboard switches that could always win at tic-tac-toe. And that was a much harder circuit to design. But again, it was no active components. It was just 3 position switches, empty, X, 0, or O, and 9 of them, and a light bulb on which move it wanted next, and then the human would go and move that.
See, there's magic in that creation. I tend to see magic in robots that, like, I also think that intelligence is a little bit overrated. I think we can have deep connections with robots very soon. And
we'll come back to connections with robots.
Sure.
But I do want to say, I think too many people make the mistake of seeing that magic and thinking, well, it will just continue, But each one of those is a hard fought battle for the next step.
Yes. The open question here is, and this is why I'm playing devil's advocate, but I often do when I read your blog post in my mind, because I have like this eternal optimism, is it's not clear to me. So I don't do what obviously the journalists do or like give into the hype, but it's not obvious to me how many steps away we are from a truly transformational understanding of what it means to build intelligent systems, or how to build intelligent systems. I'm also aware of the whole history of artificial intelligence, which is where your deep grounding of this is there's been an optimism for decades. And that optimism, just like reading old optimism, is absurd because people were like, they were saying things are trivial for decades, since the 60s. They were saying everything is true. Computer vision is trivial. But I think my mind is working crisply enough to where, I mean, we can dig into if you want. I'm really surprised by the things DeepMind has done. I don't think they're yet close to solving intelligence, but I'm not sure it's not 10 years away. What I'm referring to is interesting to see when the engineering it takes that idea to scale, and the idea works.
And no, it fools people.
Okay, honestly, Rodney, if it was you, me, and Demis inside a room, forget the press, forget all those things. Just as a scientist, as a roboticist, that wasn't surprising to you that at scale. So we're talking about very large now. Okay, let's pick one that's the most surprising to you. Okay, please don't yell at me. GPT-3. Okay, hold on a second.
I was going to bring that up.
Okay, thank you. Alpha 0. AlphaGo 0, Alpha 0, and then AlphaFold 1 and 2. So do any of these kind of have this core of not forget usefulness or application or so on, which you could argue for AlphaFold. Like, as a scientist, was those surprising to you that it worked as well as it did?
Okay, so if we're going to make the distinction between surprise and usefulness, and I have to explain this. I would say AlphaFold. And one of the problems at the moment with AlphaFold is, it gets a lot of them right, which is a surprise to me because they're a really complex thing. But you don't know which ones it gets right, which then is a bit of a problem. Now they've come out with a recent...
You mean the structure of the protein, it gets a lot of those right?
Yeah, it's a surprising number of them right. Yeah. It's been a really hard problem. So that was a surprise how many it gets right. So far, the usefulness is limited because you don't know which ones are right or not. And now they've come out with a thing in the last few weeks, which is trying to get a useful tool out of it, and they may well do it.
In that sense, at least AlphaFold is different because your AlphaFold 2 is different. Because now it's producing data sets that are actually... potentially revolutionizing computational biology. Like, they will actually help a lot of people. But
you did say potentially revolutionizing. Yeah. We don't know yet, but yeah,
that's true. Yeah, but but I got you. I mean, this is okay. So you know what? This is going to be so fun. So let's go right on the merger with AI question and the incredible work that's being done at Neuralink. There's a lot of fascinating innovation here across different disciplines going on.
So the flexible wires, the robotic sewing machine, that responds to brain movement, and everything around ensuring safety and so on. So we currently understand very little about the human brain. Do you also hope that the work at Neuralink will help us understand more about the human mind, about the brain?
Yeah, I think the work in Neuralink will definitely shed a lot of insight into how the brain and the mind works. Right now, just the data we have regarding how the brain works is very limited. We've got fMRI, which is that's kind of like putting a stethoscope on the outside of a factory wall and then putting it like all over the factory wall, and you can sort of hear the sounds, but you don't know what the machines are doing really. It's hard. You can infer a few things, but it's a very broad brushstroke. In order to really know what's going on in the brain, you have to have high precision sensors, and then you want to have stimulus and response. Like if you trigger a neuron, how do you feel? What do you see? How does it change your perception of the world?
You're speaking to physically, just getting close to the brain, being able to measure signals from the brain, will give us sort of open the door inside the factory.
Yes, exactly. Being able to have high precision sensors that tell you what individual neurons are doing, and then being able to trigger the neuron and see what the response is in the brain. So you can see the consequences of if you fire this neuron, what happens? How do you feel? What does it change? It'll be really profound to have this in people, because people can articulate their change, like if there's a change in mood, or if they can tell you if they can see better or hear better, or be able to form sentences better or worse, or their memories are jogged, or that kind of thing.
So, well, if we could dive in some aspects of the book, I would love that. Can we talk about? So one of the essays looks at evolution. Let me ask the big question: did the human brain evolve to think? That's essentially the question that you address in the essay. Can you speak to it?
Sure. The big caveat here is that we don't really know why brains evolved. The big why questions are called teleological questions. And in general, scientists should avoid those questions because we don't know really why. We don't know the why. However, for a very long time, the assumption was that evolution worked in a progressive upward scale, that you start off with simple organisms and those organisms get more complex and more complex and more complex. Now, obviously, that's true in some like really general way, right? That life started off as single cell organisms and, things got more complex. But the idea that that brains evolved in some upward trajectory from simple brains in simple animals to complex brains in complex animals is called a phylogenetic scale. Mm-hmm. That phylogenetic scale is embedded in a lot of evolutionary thinking, including Darwin's, actually. And it's been seriously challenged, I would say, by modern evolutionary biology. And so, thinking is something that, rationality is something that humans, at least in the West, really prize as a great human achievement. And so the idea that the most common evolutionary story is that, brains evolved in like sedimentary rock with, a layer for instincts, that's your lizard brain, and a layer on top of that for emotions, that's your limbic system, limbic meaning border. So it borders the parts that are for instincts.
Oh, interesting.
And then the neocortex or new cortex where rationality is supposed to live. That's the sort of traditional story.
It just keeps getting layered on top,
right,
by evolution.
Right. And so you can think about, sedimentary rock is the way typically people describe it. The way I sometimes like to think about it is, thinking about the cerebral cortex like icing on an already baked cake, where, the cake is your inner beast. these boiling, roiling instincts and emotions that have to be contained. And by the cortex. And it's just, it's a fiction. It's a myth. It's a myth that you can trace all the way back to stories about morality in ancient Greece. But what you can do is look at the scientific record and say, well, there are other stories that you could tell about brain evolution and the context in which brains evolved. So when you look at creatures who don't have brains and you look at creatures who do, what's the difference? And you can look at, some animals. So scientists call an environment that an animal lives in a niche, their environmental niche. What are the parts of the environment that matter to that animal? And so there's some animals whose niche hasn't changed in 400 million years. So these creatures are modern creatures, but they're living in a niche that hasn't changed much. And so their biology hasn't changed much. And you can kind of verify that by looking at the genes that lurk deep, in the molecular structure of cells. Mm-hmm. And so you can, by looking at various animals in their developmental state, meaning you don't look at adult animals, you look at embryos of animals and developing animals, you can piece together a different story. And that story is that brains evolved under the selection pressure of hunting. That in the Cambrian period, hunting emerged on the scene where animals deliberately ate one another. Before the Cambrian period, the animals didn't really they didn't have brains, but they also didn't have senses, really. The very, very rudimentary senses. So the animal that I wrote about in 7.5 lessons is called an amphioxus or a lancelet. Mm-hmm. And little amphioxus has no eyes. It has no ears. It has no nose. It has no eyes. It has a couple of cells for detecting light and dark for circadian rhythm purposes. So, and it can't hear. It has a vestibular cell to keep its body upright. It has a very rudimentary sense of touch, and it doesn't really have any internal organs other than this, basically stomach. It's it doesn't have an enteric nervous system. It doesn't have a gut that, moves like we do. It just has basically a tube.
Yeah.
So it's
a little container.
Like a little container, yeah. And really it doesn't move very much. It can move. It just sort of wriggles. It doesn't have very sophisticated movement. And it's this really sweet little animal. It sort of wriggles its way to a spot and then plants itself in the sand and just filters food as the food goes by. And then when the food concentration decreases, it just ejects itself, wriggles to some spot randomly where probabilistically there will be more food, and plants itself again. Yeah. So it's not really very aware that it has an environment. It has a niche, but that niche is very small, and it's not really experiencing that niche very much. So it's basically like a little stomach on a stick. Yeah. That's really what it is. And But when animals start to literally hunt each other, all of a sudden it becomes important to be able to sense your environment, because you need to know, is that blob up ahead going to eat me, or should I eat it? Mm-hmm. And so all of a sudden distance senses are very useful. And so in the water, distance senses are vision, and a little bit hearing, olfaction, smelling, and touch. Because in the water, touch is a distance sense because you can feel the vibration. So it's right. So cool. On land, vision is a distant sense. Touch, not so much, but for elephants, maybe, right?
The vibrations.
Olfaction, definitely, because of the concentration of, the more concentrated something is, the more likely it is to be close to you. So animals developed senses. They developed a head, like a literal head. So Amphioxus doesn't even have a head, really. It's just a
What's the purpose of a head?
That's a great question.
Is it to have a jaw?
That's a great question. So yes, jaws are a major
Useful feature.
yeah, I would say they're a major adaptation after there's a split between vertebrates and invertebrates. So Amphioxus is thought to be very, very similar to the animal that's before that split. But then very quickly after the development of a head is the development of a jaw, which is a big thing. And what goes along with that is the development of a brain.
It's weird. Is that just a coincidence that the part of our body, of the mammal, I think, body that we eat with and like attack others with is also the thing that contains all the majority of the brain type of
Well,
stuff?
actually, the brain goes with the development of a head and the development of a visual system and an auditory system and an olfactory system and so on. So your senses are developing, and the other thing that's happening, right, is that animals are getting bigger.
Yeah.
Because their niche is getting bigger.
Well, this is just sorry to take a tiny tangent on the niche thing. It seems like the niche is getting bigger, but not just bigger, like more complicated, like shaped in weird ways. So like predation seems to create like the whole world becomes your oyster, whatever. But like you also start to carve out like the places in which you can operate the best.
Yeah, and in fact, that's absolutely right. And in fact, some scientists think that theory of mind, your ability to make inferences about the inner life of other creatures, actually developed under the selection pressure of predation, because it makes you a better predator.
Do you ever you just said you looked at babies as these wiring creatures. Do you ever think of humans as just clever predators? Like that there's underneath it all is this, the Nietzschean will to power in all of its forms? Or are we now friendlier?
Yeah, so it's interesting. I mean, there are zeitgeists in how humans think about themselves, right? And so if you look in the 20th century, you can see that the idea of an inner beast, that we're just predators, we're just basically animals, baseless animals, violent animals that have to be contained by culture and by our prodigious neocortex, really took hold, particularly after World War I, and really held sway for much of that century. And then around, at least in Western writing, I would say, we're talking mainly about Western scientific writing, Western philosophical writing, and then late 90s maybe, you start to see books and articles about our social nature, that we're social animals, and we are social animals, but what does that mean exactly? And about
it's us carving out different niches in the space of ideas, it looks like.
I think so. So do humans can humans be violent? Yes. Can humans be really helpful? Yes, actually. And humans are interesting creatures because other animals can also be helpful to one another. In fact, there's a whole booming literature on how other animals are support one another. They regulate each other's nervous systems in interesting ways, and they will be helpful to one another, right? So, for example, there's a whole literature on rodents and how they signal one another what is safe to eat, and they will perform acts of generosity to their conspecifics that are related to them, or who they were raised with. So if an animal was raised in a litter that they were raised in, although not even at the same time, they'll be more likely to help that animal. So there's always some kind of physical relationship between animals that predicts whether or not they'll help one another. For humans, we have ways of categorizing who's in our group and who isn't by non-physical ways, right? By just something abstract like an idea. And we are much more likely to extend help to people in our own group, whatever that group may be, at that moment, whatever feature you're using to define who's in your group and who isn't. We're more likely to help those people than even members of our own family at times. So humans are much more flexible in the way that they help one another, but also in the way that they harm one another. So I don't think I subscribe to, we are primarily this or we are primarily that. I don't think humans have essences in that way, really.
The brain. I wonder, from almost an AI perspective, but just computationally, is the brain just mostly a prediction machine then? Like, is the perception just a nice little feature added on top? Like both the integration of new perceptual information. I wonder how big of an impressive system is that relative to just the big predictor, model constructor?
Well, I think that we can look to evolution for that, for one answer, which is that when you go back, 550 million years, give or take, the world was populated by creatures, really ruled by creatures without brains. That's a biological statement, not a political statement. Like, world with
You
creatures
calling
without...
dinosaurs dumb? You're talking about like...
Oh, no, I'm not talking about dinosaurs, honey. I'm talking way back, further back than that. Really, there are these little creatures called Amphioxus, which is the modern, or a lancet. That's the modern animal. But it's an animal that scientists believe is very similar to the common ancestor that we share with invertebrates, basically because of the tracing back the molecular genetics in cells. And that animal had no brain. It had some cells that would later turn into a brain, but in that animal, there's no brain. But that animal also had no head, and it had no eyes, and it had no ears, and it had really, really no senses for the most part. It had very, very limited sense of touch. It had an eye spot for, not for seeing, but just for in training to circadian rhythm to light and dark. And it had no hearing. It had a vestibular cell so that it could keep upright in the water. At the time, we're talking evolutionary scale here, so, give or take some 100 million years or something. But at the time, what are the vertebrate, like when a backbone evolved and a brain evolved, a full brain, that was when a head evolved with sense organs, and when that's when your viscera, like internal systems, involved. So the answer, I would say, is that senses, motor neuroscientists, people who study the control of motor behavior, believe that senses evolved in the service of motor action. So the idea is that, like, what was the big evolutionary change? What was the big pressure that made it useful to have eyes and ears and a visual system and an auditory system and a brain, basically? And the answer that is commonly entertained right now is that it was predation. That when at some point an animal evolved that deliberately ate another animal, and this launched an arms race between predators and prey, and it became very useful to have senses, right? So these little amphioxy, don't really have don't have they're not aware of their environment very much, really. And so being able to look up ahead and, ask yourself, should I eat that or will it eat me? Is a very useful thing. So the idea is that sense data is not there for consciousness. It didn't evolve for the purposes of consciousness. It didn't evolve for the purposes of experiencing anything. It evolved to be in the service of motor control. However, maybe it's useful. This is why, scientists sometimes avoid questions about why things evolved. That this is what philosophers call this teleology. You might be able to say something about how things evolve, but not necessarily why. We don't really know the why. That's all speculation.
But the why is kind of nice here. The interesting thing is that was the first element of social interaction is, am I going to eat you or are you going to eat me? And for that, it's useful to be able to see each other, sense each other. That's kind of fascinating that there was a time when life didn't eat each other.
Or they did by accident, right? So an amphioxus, for example, will, it kind of like gyrates in the water and then it plants itself in the sand like a living blade of grass, and then it just filters whatever comes into its mouth, right? So it is eating, but it's not actively hunting. And when the concentration of food decreases, the amphioxus can sense this, and so it basically wriggles itself randomly to some other spot, which probabilistically will have more food than wherever it is. So it's not really, it's not guiding its actions on the basis of, it's not, we would say there's no real intentional action in the traditional sense.
But if we look at the human brain versus the brains, or whatever you call them, the mechanisms of intelligence in our ancestors, even early ancestors, that you write about, for example, in your new book, what's the difference between the fanciest brain we got, which is the human brain, and the ancestor brains that it came from?
Yeah, I think it depends on how far back you want to go.
You go all the way back, right? In your book. But, so what's the interesting comparison, would you say?
Well, first of all, I wouldn't say that the human brain is the fanciest brain we've got. I mean, an octopus brain is pretty different and pretty fancy, and they can do some pretty amazing things that we cannot do. We can't grow back limbs. We can't change color and texture. We can't comport ourselves and squeeze ourselves into a little crevice. I mean, these are things that we invent. These are like superhero abilities that we invent in stories, right? We can't do any of those things. And so the human brain is certainly, we can certainly do some things that other animals can't do that seem pretty impressive to us. But I would say that there are a number of animal brains which seem pretty impressive to me, that can do interesting things and really impressive things that we can't do.
I mean, with your work on how emotions are made and so on, you kind of repaint the view of the brain as less glamorous, I suppose, than you would otherwise think. Or like, I guess you draw a thread that connects all brains together in terms of homeostasis and all that kind of stuff.
I wouldn't say that the human brain is any less miraculous than anybody else would say. I just think that there are other brain structures which are also miraculous. And I also think that there are a number of things about the human brain which we share with other vertebrates, other animals with backbones, but that we share these miraculous things. But we can do some things in abundance, and we can also do some things with our brains together, working together, that other animals can't do, or at least we haven't discovered their ability to do it.
Yeah, this social thing. That's one of the things you write about. How do you make sense of the fact, like the book *Sapiens*, and the fact that we're able to kind of connect, like network our brains together, like you write about. I'll try to stop saying that. uh, is that like some kind of feature that's built into there? Is that unique to our human brains? Like, how do you make sense of that?
What I would say is that our ability to coordinate with each other is not unique to humans. There are lots of animals who can do that, and we. But what we do with that coordination is unique because of some of the structural features in our brains, and it's not that other animals don't have those structural features. It's we have them in abundance. So, the human brain is not larger than you would expect it to be for a primate of our size. If you took a chimpanzee and you grew it to the size of a human, that chimpanzee would have a brain that was the size of a human brain. So there's nothing special about our brain in terms of its size. There's nothing special about our brain in terms of the basic blueprint that builds our brain from an embryo is the basic blueprint that builds all mammalian brains and maybe even all vertebrate brains. It's just that because of its size, and particularly because of the size of the cerebral cortex, which is the a part that people mistakenly attribute to rationality.
Why mistakenly? Isn't that where all the clever stuff happens?
Well, no, it really isn't. And I will also say that lots of clever stuff happens in animals who don't have a cerebral cortex. But but because of the size of the cerebral cortex and because of some of the features that are enhanced by that size, that gives us the capacity to do things like build civilizations and coordinate with each other, not just to manipulate the physical world, but to add to it in very profound ways. Like, other animals can cooperate with each other and use tools. We draw a line in the sand and we make countries, and then we create, we create citizens and immigrants.
But also ideas. I mean, the countries are centered around the concept of like ideas.
What do you think a citizen is and an immigrant? Those are ideas. Right. Those are ideas that we impose on reality and make them real. And then they have very, very serious and real effects, physical effects on people.
What do you think about the idea that a bunch of people have written about, Dawkins with memes, which is like ideas are breeding, like we're just like the canvas for ideas to breed in our brains. So this kind of network that you talk about of brains is just a little canvas for ideas to then compete against each other and so on.
I think as a rhetorical tool, it's cool to think that way. So I think it was Michael Pollan. I don't remember if it was in The Botany of Desire, but it was in one of his early books on botany and gardening, where he wrote about plants sort of utilizing humans for their own evolutionary purposes, which is kind of interesting. You can think about a human gut in a sense as a propagation device for the seeds of tomatoes and what have you. So it's kind of cool. So I think rhetorically it's an interesting device, but ideas are, as far as I know, invented by humans, propagated by humans. So I don't think they're separate from human brains in any way. Although it is interesting to think about it that way.
Well, of course, the ideas that are using your brain to communicate and write excellent books, and they basically picked you, Lisa, as an effective communicator, and thereby are winning. So that's an interesting worldview. to think that there's particular aspects of your brain that are conducive to certain sets of ideas, and maybe those ideas will win out.
Yeah, I think the way that I would say it really, though, is that there are many species of animals that influence each other's nervous systems, that regulate each other's nervous systems. And they mainly do it by physical means. They do it by chemicals, scent. They do it by, so termites and ants and bees, for example, use chemical scents. Mammals like rodents use scent, and they also use hearing, audition, and that little bit of vision. Primates, non-human primates add vision, right? Mm-hmm. I think everybody uses touch. Humans, as far as I know, are the only species that use ideas and words to regulate each other, right? I can text something to someone halfway around the world.
That's fascinating.
They don't have to hear my voice. Yeah. They don't have to see my face, and I can have an effect on their nervous system. And ideas, the ideas that we communicate with words, I mean, words are, in a sense, a way for us to do mental telepathy with each other, right? I mean, I'm not the first person to say that, obviously, but how do I control your heart rate? How do I control your breathing? How do I control your actions with words? It's because those words are communicating ideas.
What's the more accurate view of the brain that we should use when we're thinking about it?
I'll answer that in a second, but I'll say that even our notion of what an instinct is or what a reflex is not quite right? So if you look at evidence from ecology, for example, and you look at animals in their ecological context, what you can see is that even things which are reflexes are very context sensitive. The brains of those animals are executing so-called instinctual actions in a very, very context-sensitive way. And so, even when a physician, takes the, it's like the idea of your patellar reflex where they hit, your patellar tendon on your knee and you kick. The force with which you kick and so on is influenced by all kinds of things. It's a reflex isn't like a robotic response. And so I think a better way is a way that to think about how brains work is the way that matches our best understanding, our best scientific understanding, which I think is really cool because it's really counterintuitive. So how I came to this view, and I'm certainly not the only one who holds this view. I was reading work on neuroanatomy, and the view that I'm about to tell you was strongly suggested by that. And then I was reading work in signal processing, like by electrical engineering. And similarly, the work suggested that the research suggested that the brain worked this way. And I'll just say that I was reading across multiple literatures, and they were who don't speak to each other, and they were all pointing in this direction. And so far, although some of the details are still up for grabs, the general gist, I think, is I've not come across anything yet which really violates, and I'm looking. Mm-hmm. And so the idea is something like this. It's very counterintuitive. So the way to describe it is to say that your brain doesn't react to things in the world. It's not, to us, it feels like our eyes are windows on the world. We see things, we hear things, we react to them. In psychology, we call this stimulus response. So your voice is a stimulus to me. I receive input and then I react to it. And I might react very automatically, system one. But I also might execute some control where I maybe stop myself from saying something or doing something, and in a more reflective way, execute a different action, right? That's system two. The way the brain works, though, is it's predicting all the time. It's constantly talking to itself, constantly talking to your body, and it's constantly predicting what's going on in the body and what's going on in the world, and making predictions. And the information from your body and from the world really confirm or correct those predictions.
So fundamentally, the thing that the brain does most of the time is just talking to itself and predicting stuff about the world, not like this dumb
thing that just senses and responds, senses and
Yeah.
responds.
So the way to think about it is like this. Your brain is trapped in a dark, silent box.
Yeah, that's very romantic of you.
Which is your skull. And the only information that it receives from your body and from the world, right, is through the senses, through the sense organs, your eyes, your ears, and you have sensory data that comes from your body that you're largely unaware of to your brain, which we call interoceptive, as opposed to exteroceptive, which is the world around you. But your brain is receiving sense data continuously, which are the effect of some set of causes. Your brain doesn't know the cause of these sense data. It's only receiving the effects of those causes, which are the data themselves. And so your brain has to solve what philosophers call an inverse inference problem. How do you know, when you only receive the effects of something, how do you know what caused those effects? So when there's a flash of light or a change in air pressure or a tug somewhere in your body, how does your brain know what caused those events so that it knows what to do next to keep you alive and well? And the answer is that your brain has one other source of information available to it, which is your past experience. It can reconstitute in its wiring past experiences, and it can combine those past experiences in novel ways. And so we have lots of names for this in psychology. We call it memory, we call it perceptual inference, we call it simulation. It's also, we call it concepts or conceptual knowledge. We call it prediction. Basically, if we were to stop the world right now, stop time, your brain is in a state and it's representing what it believes is going on in your body and in the world. And it's predicting what will happen next based on past experience, right? Probabilistically, what's most likely to happen. And it begins to prepare your action, and it begins to prepare your experience based. So it's anticipating the sense data it's going to receive, and then when those data come in, they either confirm that prediction and your action executes because the plan's already been made, or there's some sense data that your brain didn't predict that's unexpected, and your brain takes it in. We say encodes it. We have a fancy name for that. We call it learning. Your brain learns, and it updates its storehouse of knowledge, which we call an internal model, and so that you can predict better next time. And it turns out that predicting and correcting is a much more metabolically efficient way to run a system than constantly reacting all the time. Because if you're constantly reacting, it means you can't anticipate in any way what's going to happen. Mm-hmm. And so the amount of uncertainty that you have to deal with is overwhelming to a nervous system.
Metabolically costly. I like it.
And so what is a reflex? A reflex is when your brain doesn't check against the sense data, that the potential cost to you is so great, maybe because, your life is threatened, that your brain makes the prediction and executes the action without checking.
Yeah, but prediction is still at the core. That's a beautiful vision. So you also write, I think, let's go back to the brain. You write that Plato gave us the idea that the human brain has 3 brains in it, 3 forces, which is kind of a compelling notion. You disagree. First of all, what are the 3 parts of the brain, and why do you disagree?
So Plato's description of the psyche, which for the moment we'll just assume is the same as a mind. There are some scholars who would say, a soul, a psyche, a mind, those aren't actually all the same thing in ancient Greece, but we'll just for now gloss over that. So Plato's idea was that, and it was a description of really about moral behavior and moral responsibility in humans. So the idea was that, the human psyche can be described with an metaphor of two horses and a charioteer. So one horse for instincts, like feeding and fighting and fleeing and reproduction. I'm trying to control my salty language, which apparently they print in England. Like I actually tossed off a fairly...
Which F? S?
Yeah,
Which
F.
okay.
Yeah. I was like, you printed that. I couldn't believe you printed that.
Without like the stars or whatever?
No. There was full print.
Okay,
They
great.
also printed a B word, and it was really right. Yeah.
Well,
Anyways,
we should learn something from England.
Indeed. Anyways, but instincts, and then the other horse represents emotions, and then the charioteer represents rationality, which controls, the two beasts, right? And fast forward, couple of centuries, and in the middle of the 20th century, there was a very popular view of brain evolution, which suggested that you have this reptilian core, like an inner lizard brain for instincts, and then wrapped around that layer on top of that evolved a limbic system for in mammals. So the novelty was in a mammalian brain, which bestowed mammals with, gave them emotions, the capacity for emotions. And then on top of that evolved a cerebral cortex, which in largely in primates, but very large in humans. And it's not that I personally disagree. It's that as far back as the 1960s, but really by the 1970s, it was shown pretty clearly with evidence from molecular genetics, so peering into cells in the brain to look at the molecular makeup of genes, that the brain did not evolve that way. And the irony is that, the idea of the three-layered brain with an inner lizard, that hijacks your behavior and causes you to do and say things that you would otherwise not, or maybe that you will regret later. That idea became very popular, was popularized by Carl Sagan in The Dragons of Eden, which won a Pulitzer Prize in 1977, when it was already known pretty much in evolutionary neuroscience that the whole narrative was a myth.
So, the narrative is on the way it evolved, but again, it's that problem of it being a useful tool of conversation to say, like, there's a lizard brain and there's if I get overly emotional on Twitter, that was the lizard brain and so on. But do you...
No, I don't think it's useful. I think that...
But is it useful? Is it accurate?
I don't think it's accurate, and therefore I don't think it's useful.
Got it.
So here's what I would say. I think that the way I think about philosophy and science is that they are useful tools for living. And in order to be useful tools for living, they have to help you make good decisions. The triune brain, as it's called, this three-layer brain, the idea that your brain is like an already baked cake, and the cortex, cerebral cortex, just layered on top like icing. Mm-hmm. That idea is the foundation of the law in most Western countries. It's the foundation of economic theory, and it's a great narrative. It sort of fits our intuitions about how we work. But it also, it's in addition to being wrong, it lets people off the hook for nasty behavior, and it also suggests that emotions can't be a source of wisdom, which they often are. in fact, you would not want to be around someone who didn't have emotions. That's a psychopath.
Right.
I mean, that's not someone you want to really have that person deciding your outcome. So I guess and I could sort of go on and on and on, but my point is that I don't think it's a useful narrative in the end.
Work. What other interesting problems are there? The open problems and brain inspired approaches that you're thinking about?
I mean, everything is open, right? Like, no problem is solved. Right? I think of perception as kind of the first thing that you have to build, but the last thing that you will be actually solved. Because if you do not build perception system in the right way, you cannot build concept system in the right way. So you have to build a perception system, however wrong that might be. You have to still build that and learn concepts from there, and then keep iterating. And finally, perception will get solved fully when perception, cognition, language, all those things work together finally.
So what? Great. We've talked a lot about perception, but then maybe on the concept side and like common sense or just general reasoning side, is there some intuition you can draw from the brain about how we could do that?
So I have this classic example I give. So suppose I give you a few sentences and then ask you a question following that sentence. This is a natural language processing problem, right? So here it goes. I'm telling you, Sally pounded a nail on the ceiling. Mm-hmm. Okay, that's a sentence. Mm-hmm. Now I'm asking you a question. Was the nail horizontal or vertical?
Vertical.
Okay, how did you answer that?
Well, I imagined Sally. It was kind of hard to imagine what the hell she was doing, but but I imagined I had a visual of the whole situation.
Exactly. Yeah. So here, I posed a question in natural language. The answer to that question was you got the answer from actually simulating the scene. Now I can go more and more detail about, okay, was Sally standing on something while doing this? Could she have been standing on a light bulb to do this? I could ask more and more questions about this, and I can make you simulate the scene in more and more detail, right? Where is all that knowledge that you're accessing stored? It is not in your language system. It was not just by reading text you got that knowledge. It is stored from the everyday experiences that you have had from, and by the age of 5, you have pretty much all of this, right? And it is stored in your visual system, motor system, in a way such that it can be accessed through language.
Got it. I mean, right. So the language is just almost serves as a query into the whole visual cortex, and it does the whole feedback thing. But it is all reasoning kind of connected to the perception system in some way.
You can do a lot of it. You can still do a lot of it by quick associations without having to go into the depth. And most of the time you will be right? You can just do quick associations, but I can easily create tricky situations for you where that quick associations is wrong, and you have to actually run the simulation.
So the figuring out how these concepts connect. Do we have a good idea of how to do that?
That's exactly what
that's
one of the problems that we are working on, and the way we are approaching that is basically saying, okay, you need to. So the takeaway is that language is simulation control. And your perceptual plus motor system is building a simulation of the world. Mm-hmm. And so that's basically the way we are approaching it. And the first thing that we built was a controllable perceptual system. And we built a schema networks, which was a controllable dynamic system. Then we built a concept learning system that puts all these things together into programs as abstractions that you can run and simulate. And now we are taking the step of connecting it to language, and it will be very simple examples initially. It will not be the GPT-3 like examples, but it will be grounded simulation based language.
And for like the querying would be like question answering kind of thing.
Correct. Correct. And it will be in some simple world initially but it will be about, okay, can the system connect the language and ground it in the right way and run the right simulations to come up with the answer.
And the goal is to try to do things that, for example, GPT-3 couldn't do.
Correct.
Do you think we need to understand the brain in order to build it?
Yes, if you want to build the brain, we definitely need to understand how it works. So Blue Brain, or Henry Markram's project, is trying to build the brain without understanding it, just trying to put details of the brain from neuroscience experiments into a giant simulation by putting more and more neurons, more and more details. But that is not going to work because when it doesn't perform as what you expect it to do, then what do? You just keep adding more details. How do you debug it? So unless you understand, unless you have a theory about how the system is supposed to work, how the pieces are supposed to fit together, what they're going to contribute, you can't build it
at the functional level. Understand. So can you actually linger on and describe the Blue Brain project? It's kind of a fascinating principle, an idea to try to simulate the brain. We're talking about the human brain, right?
Right. Human brains and rat brains or cat brains have lots in common. That the cortex, the neocortex structure is very similar. So initially they were trying to just simulate a cat brain and to
understand the nature of evil.
Understand the nature of evil, or as it happens in most of these simulations, you easily get one thing out, which is oscillations. If you simulate a large number of neurons, they oscillate, and you can adjust the parameters and say that oscillations match the rhythm that we see in the brain, etc. But
I see. So so the idea is the simulation at the level of individual neurons?
Yeah. So the Blue Brain project, the original idea as proposed was you put very detailed biophysical neurons, biophysical models of neurons, and you interconnect them according to the statistics of connections that we have found from real neuroscience experiments, and then turn it on and see what happens. And these neural models are, incredibly complicated in themselves, right? Because these neurons are modeled using this idea called Hodgkin-Huxley models, which are about how signals propagate in a cable, and there are active dendrites, all those phenomena, those phenomena themselves we don't understand that well. And then we put in connectivity, which is part guesswork, part observed. And of course, if we do not have any theory about how it is supposed to work, we just have to take whatever comes out of it as, okay, this is something interesting.
But in your sense, like these models of the way signal travels along, or like with the axons and all the basic models, they're too crude.
Oh, well, actually, they are pretty detailed and pretty sophisticated, and they do replicate the neural dynamics. If you take a single neuron and you try to turn on the different channels, the calcium channels and the different receptors, and see what the effect of turning on or off those channels are in the neuron's spike output, people have built pretty sophisticated models of that, and they are, I would say, in the regime of correct.
Well, see, the correctness, that's interesting because you mentioned it at several levels. The correctness is measured by looking at some kind of aggregate statistics.
It would be more the spiking dynamics of a single
spiking
neuron.
Dynamics of a single neuron. Okay.
Yeah. And these models, because they are going to the level of mechanism, right? So they are basically looking at what is the effect of turning on an ion channel, and you can model that using electric circuits, and then so they are model. So it is not just a function fitting. It is people are looking at the mechanism underlying it and putting that in terms of electric circuit theory, signal propagation theory, and modeling that. And so those models are sophisticated, but getting a single neurons model 99% right does not still tell you how to, it would be the analog of getting a transistor model right and now trying to build a microprocessor. And if you just observe, if you did not understand how a microprocessor works, but you say, oh, I now can model one transistor well, and now I will just try to interconnect the transistors according to whatever I could, guess from the experiments and try to simulate it, then it is very unlikely that you will produce a functioning microprocessor. You want to, when you want to produce a functioning microprocessor, you want to understand Boolean logic. How do the gates work? All those things, and then understand how do those gates get implemented using transistors.
Yeah, there's actually, I remember, this reminds me, there's a paper, maybe you're familiar with it, that I remember going through in a reading group that approaches a microprocessor from a perspective of a neuroscientist. I think it basically, it uses all the tools that we have of neuroscience to try to understand, like as if we just aliens showed up to study computers, and to see if those tools can be used to get any kind of sense of how the microprocessor works. And I think the takeaway from at least this initial exploration is that we're screwed. There's no way that the tools of neuroscience would be able to get us to anything, like not even Boolean logic. I mean, it's just any aspect of the architecture, of the function, of the processes involved, the clocks, the timing, all that. You can't figure that out from the tools of neuroscience.
Yeah, so I'm very familiar with this particular paper. Yeah. I think it was called "Can a Neuroscientist Understand a Microprocessor?" or something like that. Following the methodology in that paper, even electrical engineer would not understand microprocessors. So I could, I don't think it is that bad in the sense of saying neuroscientists do find valuable things by observing the brain. They do find good insights, but those insights cannot be put together just as a simulation. You have to investigate what are the computational underpinnings of those findings. How do all of them fit together from an information processing perspective? Somebody has to painstakingly put those things together and build hypotheses. So I don't want to diss all of neuroscience as saying, oh, they're not finding anything. No, that paper almost went to that level of neuroscientists will never understand. That's not true. I think they do find lots of useful things, but it has to be put together in a computational framework.
Yeah, I mean, but just the AI systems will be listening to this podcast 100 years from now, and they will probably, there's some non-zero probability they'll find your words laughable. There's like, I remember humans thought they understood something about the brain. They were totally clueless. There's a sense about neuroscience that we may be in the very, very early days of understanding the brain. But I mean, that's one perspective. I mean, in your perspective, how far are we into understanding any aspect of the brain? So the dynamics of the individual neuron communication to the how when they in a collective sense, how they're able to store information, transfer information, how intelligence then emerges, all that kind of stuff. Where are we on that timeline?
Yeah. So, timelines are very, very hard to predict. And you can, of course, be wrong. And it can be wrong on either side. We know that when we look back, the first flight was in 1903. In 1900, there was a New York Times article on flying machines that do not fly, and humans might not fly for another 100 years. That was what that article stated, and but no, they flew 3 years after that. So it is, it's very hard to.
Well, and on that point, one of the Wright brothers, I think 2 years before, said that. Like he said, like some number, like 50 years, he has become convinced that it's impossible.
even during their experimentation. Yeah.
I mean, that's attributed to that's like the entrepreneurial battle of like depression of going through just like thinking this is impossible.
Right.
But there's something. Even the person that's in it is not able to see estimate correctly.
Exactly. But I can tell from the point of objectively what are the things that we know about the brain and how that can be used to build AI models, which can then go back and inform how the brain works. So my way of understanding the brain would be to basically say, look at the insights neuroscientists have found, understand that from a computational angle, information processing angle, build models using that, and then building that model which functions, which is a functional model, which is doing the task that we want the model to do. It is not just trying to model a phenomena in the brain. It is trying to do what the brain is trying to do on the whole functional level. And building that model will help you fill in the missing pieces that biology just gives you the hints, and building the model fills in the rest of the pieces of the puzzle. And then you can go and connect that back to biology and say, okay, now it makes sense that this part of the brain is doing this, or this layer in the cortical circuit is doing this, and then continue this iteratively, because now that will inform new experiments in neuroscience. And of course, building the model and verifying that in the real world will also tell you more about, does the model actually work, and you can refine the model, find better ways of putting these neuroscience insights together.
Mm-hmm.
So I would say it is so neuroscientists alone, just from experimentation, will not be able to build a model of the brain, or a functional model of the brain. So there's lots of efforts, which are very impressive efforts, in collecting more and more connectivity data from the brain. How are the microcircuits of the brain connected with each other?
Those are beautiful, by the way.
Those are beautiful. And at the same time, those do not itself by themselves convey the story of how does it work.
Yeah.
And somebody has to understand, okay, why are they connected like that, and what are those things doing? And we do that by building models in AI using hints from neuroscience and repeat this.
How's that all encoded in the brain? Like, where's the storage of information? Are we talking, just maybe to get it a little bit more specific, is it in the hardware of the actual connections? Is it in chemical communication? Is it electrical communication? Do we know?
So this is a paper that we are bringing out soon.
Which one is this?
This is the cortical microcircuits paper that I sent you a draft of. Of course, this is a lot of it is still hypothesis. One hypothesis is that you can think of a cortical column as encoding a concept. A concept, think of it as an example of a concept is an edge present or not, or is an object present or not. Okay, so you can think of it as a binary variable, a binary random variable, the presence of an edge or not, or the presence of an object or not. So each cortical column can be thought of as representing that one concept, one variable. And then the connections between these cortical columns are basically encoding the relationship between these random variables. Mm-hmm. And then there are connections within the cortical column. Each cortical column is implemented using multiple layers of neurons with very, very, very rich structure there. There are thousands of neurons in a cortical column.
But that structure is similar across the different cortical columns.
Correct.
Yeah.
Correct. And also these cortical columns connect to a substructure called thalamus. So all cortical columns pass through this substructure. So our hypothesis is that the connections between the cortical columns implement this. That's where the knowledge is stored about how these different concepts connect to each other, and then the neurons inside this cortical column and in the thalamus in combination implement this actual computations needed for inference, which includes explaining away and competing between the different hypotheses. And it is all very... So what is amazing is that neuroscientists have actually done experiments to the tune of showing these things. They might not be putting it in the overall inference framework, but they will show things like, if I poke this higher level neuron, it will inhibit through this complicated loop through the thalamus, it will inhibit this other column. So they will do such experiments.
But do they use terminology of concepts, for example? So you're I mean, is it something where it's easy to anthropomorphize and think about concepts like you start moving into logic-based kind of reasoning systems? So are we to think of concepts in that kind of way, or is it a lot messier, a lot more gray area? Even more gray, even more messy than the artificial neural network kinds of abstractions.
It's easiest way to think of it as a variable, right? It's a binary variable, which is showing the presence or absence of something.
But I guess what I'm asking is that something that we're supposed to think of something that's human interpretable of that something?
It doesn't need to be. It doesn't need to be human interpretable. There is no need for it to be human interpretable. But it's almost like you will be able to find some interpretation of it because it is connected to the other things that you know about.
And the point is it's useful somehow.
Yeah.
It's useful as an entity in the graph that in connecting to the other entities that are, let's call them concepts.
Right.
Okay. So, by the way, are these the cortical microcircuits?
Correct. These are the cortical microcircuits. That's what neuroscientists use to talk about the circuits in within a level of the cortex. So you can think of, let's think of in neural network, artificial neural network terms. People talk about the architecture of the, so how many layers they build, what is the fan in, fan out, etc. That is the macro architecture. And then within a layer of the neural network, you can, the cortical neural network is much more structured within a level. There's a lot more intricate structure there. But even within an artificial neural network, you can think of in feature detection plus pooling as one level. And so that is kind of a microcircuit. It's much more complex in the real brain. And so within a level, whatever is that circuitry within a column of the cortex and between the layers of the cortex, that's the microcircuitry.
I love that terminology. Machine learning people don't use the circuit terminology,
right?
But they should. It's a nice. So okay, so that's the cortical microcircuit. So what's interesting about we don't really understand the full biophysics or whatever of how the brain learns.
Exactly.
But let me ask, and sorry to interrupt. What's your sense? What's our best understanding of how the brain learns?
So things like backpropagation, credit assignment. So many of these algorithms learning algorithms have things in common, right? It is backpropagation is one way of credit assignment. There is another algorithm called expectation maximization, which is another weight adjustment algorithm.
But is it your sense the brain does something like this?
Has to. There is no way around it, in the sense of saying that you do have to adjust the connections.
So and you're saying credit assignment, you have to reward the connections that were useful in making a correct prediction and not. Yeah, I guess what else? But it doesn't have to be differentiable. I mean,
it doesn't have to be differentiable.
Yeah.
But you have to have you have a model that you start with. You have data comes in, and you have to have a way of adjusting the model such that it better fits the data.
Yeah.
So that is all of learning, right? And some of them can be using backprop to do that. Some of it can be using very local graph changes to do that. There can be many of these learning algorithms have similar update properties locally in terms of what the neurons need to do locally.
I wonder if small differences in learning algorithms can have huge differences in the actual effect. So the dynamics of I mean, sort of the reverse, like spiking, like if credit assignment is like a lightning versus like a rainstorm or something, like whether there's like a looping local type of situation with the credit assignment, whether there is like regularization, like how it injects robustness into the whole thing, like whether it's chemical or electrical or mechanical, all those kinds of things like that. I feel like I feel like those differences could be essential, right?
It could be. It's just that you don't know enough on the learning side, you don't know enough to say that is definitely not the way the brain does it.
Got it. So you don't want to be stuck to it.
Right.
So so you've been open-minded on that side of things.
Correct. On the inference side, on the recognition side, I am much more amenable to being constrained because it's much easier to do experiments because, it's like, okay, here's the stimulus, how many steps did it get to take the answer? Right. I can trace it back. I can understand the speed of that computation, etc. Much more readily on the inference side.
Got it. And then you can't do good experiments on the learning side.
Correct.
So well, let me ask you this kind of touchy question. I've spoken with your friend, colleague, Jeff Hawkins too. I mean, I have to kind of ask, there is a bit of, whenever you have brain inspired stuff.
Yeah.
And you make big claims.
Yeah.
Big sexy claims.
Yeah.
There's there's critics. I mean, machine learning subreddit. Don't get me started on those people. They're hard. I mean, criticism is good, but they're a bit over the top. There is quite a bit of sort of skepticism and criticism. Is this work really as good as it promises to be?
Yeah.
What do you have thoughts on that kind of skepticism? Do you have comments on the kind of criticism I might have received about, is this approach legit? Is this a promising approach?
Yeah.
Or at least as promising as it seems to be, advertised as?
Yeah, I can comment on it. So, our RCN paper is published in Science, which I would argue is a very high quality journal, very hard to publish in, and usually it is indicative of the quality of the work. And I am very, very certain that the ideas that we brought together in that paper, in terms of the importance of feedback connections, recursive inference, lateral connections, coming to best explanation of the scene as the problem to solve, trying to solve recognition, segmentation, all jointly in a way that is compatible with higher level cognition, top-down attention, all those ideas that we brought together into something, coherent and workable in the world, and tackling a challenging problem. I think that will stay, and that contribution I stand by. Right.
Yeah.
Now, I can tell you a story which is funny in the context of this. Right. So if you read the abstract of the paper and the argument we are putting in, look, current deep learning systems take a lot of training data. They don't use these insights. And here is our new model, which is not a deep neural network. It's a graphical model. It does inference. This is how the paper is, right? Now, once the paper was accepted and everything, it went to the press department in Science, AAAS Science office. We didn't do any press release when it was published. It went to the press department. What was the press release that they wrote up? A new deep learning model.
Solves CAPTCHAs.
And so you can see where was what was being hyped in that thing, right? So it's like there is a dynamic in the community of that's especially happens when there are lots of new people coming into the field and they get attracted to one thing, and some people are trying to think different compared to that. So there is some. I think skepticism in science is important, and it is very much required. But it's not skepticism usually. It's mostly bandwagon effect that is happening rather than.
Well, but that's not even that. I mean, I'll tell you what they react to, which is like I'm sensitive to as well. If you look at just companies, OpenAI, DeepMind, Vicarious. I mean, there's there's a little bit of a race to the top and hype, right?
Right.
It's like it doesn't pay off to be humble.
Right.
So like and the press is just irresponsible often. They just, I mean, don't get me started on the state of journalism today. Like, it seems like the people who write articles about these things, they literally have not even spent an hour on the Wikipedia article about what is neural networks. Like,
Yeah.
they haven't like invested just even the language, the laziness. It's like robots beat humans. Like they write this kind of stuff that just and then of course the researchers are quite sensitive to that because it gets a lot of attention. They're like, why did this word get so much attention? That's over the top, and people get really sensitive. The same kind of criticism with OpenAI did work with the Rubik's Cube with the robot that people criticized. Same with GPT-2 and 3, they criticize. Same thing with Deep Minds with AlphaZero. I mean, I'm sensitive to it. But of course, with your work, you mentioned deep learning, but there's something super sexy to the public about brain inspired. I mean, that immediately grabs people's imagination. Not even like neural networks, but like really brain inspired. Like, brain-like neural networks.
Right.
That seems really compelling to people, and to me as well, to the world as a narrative. And so people hook onto that, and sometimes the skepticism engine turns on in the research community, and they're skeptical. But I think, putting aside the ideas of the actual performance on captures or performance on any data set, I mean, to me, all these data sets are useless anyway. It's nice to have them, but in the grand scheme of things, they're silly toy examples. The point is there intuition about the ideas, just like you mentioned, bringing the ideas together in a unique way? Is there something there? Is there some value there? And is it going to stand the test of time?
Yes.
And that's the hope. That's the hope.
My confidence there is very high. I don't treat brain inspired as a marketing term.
Mm-hmm.
I am looking into the details of biology and puzzling over those things, and I am grappling with those things. And so it is not a marketing term at all. You can use it as a marketing term, and people often use it, and you can get combined with them. And when people don't understand how we are approaching the problem, it is easy to be misunderstood and think of it as purely marketing. But that's not the way we are.
So you really, I mean, as a scientist, you believe that if we kind of just stick to really understanding the brain, that's the right, like you should constantly meditate on how does the brain do this? Because that's going to be really helpful for engineering intelligent systems.
Yes, you need to. So I think it's one input, and it is helpful, but you should know when to deviate from it too. So an example is convolutional neural networks, right?
Yeah.
Convolution is not an operation brain implements. The visual cortex is not convolutional. Visual cortex has local receptive fields, local connectivity, but there is no translation in invariance in the network weights in the visual cortex. That is a computational trick, which is a very good engineering trick that we use for sharing the training between the different nodes. And that trick will be with us for some time. It will go away when we have robots with eyes and heads that move. And so then that trick will go away. It will not be useful at that time. So
the brain doesn't. So the brain doesn't have translational invariance. It has the focal point, like it has a thing it focuses on.
Correct. It has a fovea, and because of the fovea, the receptive fields are not like the copying of the weights. Like the weights in the center are very different from the weights in the periphery.
Yes, at the periphery. I mean, I did this. Actually wrote a paper and just gotten a chance to really study peripheral vision, which is a fascinating thing. Very understood thing of what the brain, at every level the brain does with the periphery. It does some funky stuff.
Yeah.
So it's another kind of trick than convolutional. Like it does. It's convolution in neural networks is a trick for efficiency. Is an efficiency trick, and the brain does a whole nother kind of thing. I guess.
Correct. So you need to understand the principles of processing so that you can still apply engineering tricks where you want it to. You don't want to be slavishly mimicking all the things of the brain. So it should be one input, and I think it is extremely helpful. But it should be the point of really understanding so that you know when to deviate from it.
So, okay, that's really cool. That's work from a few years ago. So you did work in Numenta with Jeff Hawkins, with hierarchical temporal memory. How is if you could just give a brief history, how is your view of the way the models of the brain changed over the past few years leading up to now? Is there some interesting aspects where there was an adjustment to your understanding of the brain, or is it all just building on top of each other?
In terms of the higher level ideas, especially the ones Jeff wrote about in the book, if you blur out, right,
on intelligence,
right, on intelligence. If you blur out the details and if you just zoom out and at the higher level idea, things are, I would say, consistent with what he wrote about. But many things will be consistent with that because it's a blur. When you deep learning systems are also multi-level, hierarchical, all of those things, right? In terms of the detail, a lot of things are different, and those details matter a lot. So one point of difference I had with Jeff was how to approach, how much of biological plausibility and realism do you want in the learning algorithms? When I was there, this was almost 10 years ago now. So
flies when you're having fun.
I don't know what Jeff thinks now, but 10 years ago, the difference was that I did not want to be so constrained on saying my learning algorithms need to be biologically plausible based on some filter of biological plausibility available at that time. To me, that is a dangerous cut to make because we are, discovering more and more things about the brain all the time. New biophysical mechanisms, new channels are being discovered all the time. So I don't want to upfront kill off a learning algorithm just
because
the day.
Can you linger just briefly on, because you use this term a lot, and it'd be nice to try to get a little more color to it, which is interoception and exteroception. What are we exactly talking about? So, like, what's included in each category, and how much overlap is there?
Interoception would be an awareness of anything that's within the confines or on the surface of my skin that I'm sensing.
Oh, so literally physiological.
Physiologically, like within the boundaries of my skin and probably touch to the skin as well. Exteroception would be perception of anything that's beyond the reach of my skin. So that bottle of water, a scent, a sound. Although, and this can change dramatically, actually. If you have headphones in, you tend to hear things in your head as opposed to a speaker in the room.
Yeah.
This is actually the basis of ventriloquism. So there are beautiful experiments done by Greg Reckenzone up at UC Davis looking at how auditory and visual cues are matched, and we have an array of speakers, and you can, this will become obvious as I say it, but obviously the ventriloquist doesn't throw their voice. Right. What they do is they direct your vision to a particular location, and you think the sound is coming from that location. Yeah. And there are beautiful experiments that Greg and his colleagues have done where they suddenly introduce an auditory visual mismatch, and it freaks people out because you can actually make it seem, from a perception standpoint, as if the sound arrived from the corner of the room and hit you, like physically, and people will recoil. And so sounds aren't getting thrown across the room. They're still coming from this defined location, an array of speakers. But this is the way the brain creates these internal representations. And again, I don't want to go down a rabbit hole, but I think as much as I'm sure the listeners appreciate this, but everything in the brain is an abstraction, right? I mean, they're the sensory apparati that are the eyes and ears and nose and skin and taste and all that are taking information, and with interoception, it's taking information from sensors inside the body, the enteric nervous system for the gut. I've got sensory neurons that innervate my liver, et cetera. Taking all that, and the brain is abstracting that in the same way that if I took a picture of your face and I handed it to you and I'd say, that's you, you'd say, yeah, that's me. But if I were an abstract artist, I'd be doing a little bit more of what the brain does, where if I took a pad and paper, maybe I could do this because I'm a terrible artist, and I could just mix it up, and let's say I would make your eyes like water bottles, but I'd flip them upside down, and I'd start assigning fruits and objects to the different features of your face, and I show it to you, I say, Lex, that's you. You'd say, well, that's not me. And I'd say, no, but that's my abstraction of you. But that's what the brain does. The space-time relationship of the neurons that fire, that encode your face, have no resemblance to your face.
Right.
And I think people don't really, I don't know if people have fully internalized that, but the day that and I'm not sure I fully internalized that because it's weird to think about, but all neurons can do is fire in space and in time, different neurons in different sequences, perhaps with different intensities. It's not clear the action potential is all or none, although neuroscientists don't like to talk about that, even though it's been published in Nature a couple times. The action potential for a given neuron doesn't always have the exact same waveform. It's in all the textbooks, but you can modify that waveform.
Well, I mean, there's a lot of fascinating stuff with neuroscience about the fuzziness of all the transfer of information from neuron to neuron. I mean, we certainly touch upon it every time we at all try to think about the difference between artificial neural networks and biological neural networks. But can we maybe linger a little bit on the circuitry that you're getting at? So the brain is just a bunch of stuff firing, and it forms abstractions that are fascinating and beautiful, like layers upon layers upon layers of abstraction. And I think it, just like when you're programming, I'm programming in Python, it's awe-inspiring to think that underneath it all, it ends up being zeros and ones. And the computer doesn't know about stupid Python or Windows or Linux. It only knows about the zeros and ones. In the same way with the brain, is there something interesting to you or fundamental to you about the circuitry of the brain that allows for the magic that's in our mind to emerge? How much do we understand? I mean, maybe even focusing on the vision system. Is there something specific about the structure of the vision system, the circuitry of it, that allows for the complexity of the vision system to emerge? Or is it all just a complete chaotic mess that we don't understand?
It's definitely not all a chaotic mess that we don't understand if we're talking about vision. And that's not just because I'm a vision scientist.
Let's stick to vision.
Let's stick to vision. Well, because in the beauty of the visual system, the reason David Hubel and Torsten Wiesel won the Nobel Prize was because they were brilliant and forward thinking and adventurous and all that good stuff. But the reason that the visual system is such a great model for addressing these kinds of questions and other systems are hard is we can control the stimuli. We can adjust spatial frequency, how fine the gratings are, thick gratings, thin gratings. We can adjust temporal frequency, how fast things are moving. We can use cone isolating stimuli. We can use, there's so many things that you can do in a controlled way. Whereas if we were talking about cognitive encoding, right, like encoding the space of concepts or something, right, I like you, if I may, am drawn to the big questions in neuroscience. But I confess, in part because of some good advice I got early in my career, and in part because I'm not perhaps smart enough to go after the really high level stuff, I also like to address things that are tractable. And I want, we need to address what we can stand to make some ground on at a given time.
That you can construct brilliant controlled experiments just to study, to really literally answer questions about.
Yeah. I mean, I'm happy to have a talk about consciousness, but it's a scary talk, and I think most people don't want to hear what I have to say, which is we can save that for later, perhaps. Or
it's an interesting question of we talk about psychedelics, we can talk about consciousness, we can talk about cognition. Can experiments in neuroscience be constructed to shed any kind of light on these questions? So, I mean, it's cool that vision I mean, to me, vision is probably one of the most beautiful things about human beings. Also, from the AI side, computer vision is some of the most exciting applications of neural networks is in computer vision. But it feels like that's a neighbor of cognition and consciousness. It's just that we maybe haven't come up with experiments to study. If we look at our own brain, which is an interesting illustrative example, in your work with TensorFlow and trying to design deep learning architectures, do you think about the brain at all? Maybe from a hardware designer perspective, if you could change something about the brain, what would you change or do?
Funny question.
How would you do
so your
a better
brain is
job?
really weird. Like, your cerebral cortex, where we think we do most of our thinking, is what, like 6 or 7 neurons thick?
Yeah.
Like, that's weird. Like, all the big networks are way bigger than that. Like, way deeper. So that seems odd. And then, when you're thinking, if the input generates a result you can lose, it goes really fast. But if it can't, that generates an output that's interesting, which turns into an input, and then your brain, to the point where you mull things over for days. And how many trips through your brain is that, right? Like, it's 300 milliseconds or something to get through 7 levels of neurons. I forget the number exactly, but then it does it over and over and over as it searches. And the brain clearly looks like some kind of graph, because you have a neuron with connections, and it talks to other ones, and it's locally very computationally intense, but it's also does sparse computations across a pretty big area.
There's a lot of messy biological type of things, and it's meaning, like, first of all, there's mechanical, chemical, and electrical signals. That's all that's going on.
Yeah.
Then there's the asynchronicity of signals. And there's just a lot of variability that seems continuous and messy, and just a mess of biology. And it's unclear whether that's a good thing or it's a bad thing. Because if it's a good thing, then we need to run the entirety of the evolution. Well, we're going to have to start with basic bacteria to create something.
But imagine we could control. You could build a brain with 10 layers. Would that be better or worse? Or more connections or less connections? Or, we don't know to what level our brains are optimized. But if I was changing things, you can only hold like 7 numbers in your head.
Yeah.
Like, why not 100 or 1,000,000?
Never thought of that.
And why can't we have like a floating point processor that can compute anything we want, and see it all properly? Like, that would be kind of fun. And why can't we see in 4 or 8 dimensions? Like, it's 3D is kind of a drag. Like, all the hard mass transforms are up in multiple dimensions. So there's you could imagine a brain architecture that you could enhance with a whole bunch of features that would be really useful for thinking about things.
It's possible that the limitations you're describing are actually essential for, like, the constraints are essential for creating, like, the depth of intelligence, like that, the ability to reason.
Yeah, it's hard to say, because, like, your brain is clearly a parallel processor. 10 billion neurons talking to each other at a relatively low clock rate, but it produces something that looks like a serial thought process. It's a serial narrative in your head.
That's true.
Right? But then there are people famously who are visual thinkers. Like, I think I'm a relatively visual thinker. I can imagine any object and rotate it in my head and look at it. And there are people who say they don't think that way at all. And recently, I read an article about people who say they don't have a voice in their head. They can talk, but when they it's like, well, what are you thinking? They'll describe something that's visual. So that's curious. Now, if you're saying, if we dedicated more hardware to holding information, like 10 numbers or 1,000,000 numbers, like, would that distract us from our ability to form this kind of singular identity?
Like, it dissipates somehow,
right? But maybe future humans will have many identities that have some higher level organization, but can actually do lots more things in parallel.
Yeah, there's no reason, if we're thinking modularly, there's no reason we can't have multiple consciousnesses in one brain.
Yeah, and maybe there's some way to make it faster, so that the area of the computation could could still have a unified feel to it, but while still having way more ability to do parallel stuff at the same time. Could definitely be improved.
Could be improved.
Yeah.
Okay. Well, it's pretty good right now. Actually, people don't give it enough credit. The thing is pretty nice that it's there.
Yeah.
But let me ask the highest challenge, the interesting challenge to this plasticity, to this liveware system. If we could talk about brain-computer interfaces and Neuralink, what are your thoughts about the efforts of Elon Musk, Neuralink, BCI in general, in this regard, which is adding a machine, a computer, the capability of a computer to communicate with the brain and the brain to communicate with the computer at the very basic applications, and then like the futuristic kind of thoughts.
Yeah. First of all, it's terrific that people are jumping into doing that because it's clearly the future. The interesting part is our brains have pretty good methods of interacting with technology. So maybe it's your fat thumbs on a cell phone or something, but or maybe it's watching a YouTube video and getting into your eye that way. But we have pretty rapid ways of communicating with technology and getting data. So if you actually crack open the skull and go into the inner sanctum of the brain, you might be able to get a little bit faster. But I'll tell you, I'm not so sanguine on the future of that as a business, and I'll tell you why. It's because there are various ways of getting data in and out, and an open head surgery is a big deal. Neurosurgeons don't want to do it because there's always risk of death and infection on the table. And also, it's not clear how many people would say, I'm going to volunteer to get something in my head so that I can text faster, 20% faster. So I think it's, Mother Nature surrounds the brain with this armored, bunker of the skull because it's a very delicate material. And there's an expression in neurosurgery about the brain is, the person is never the same after you open up their skull. Now, whether or not that's true or whatever, who cares? But it's a big deal to do an open head surgery. So what I'm interested in is how can we get information in and out of the brain without having to crack the skull open?
Got it. Without messing with the biologicals, the part, like directly connecting or messing with the intricate biological thing that we got going on that seems to be working.
Yeah, exactly. And by the way, where Neuralink is going, which is wonderful, is going to be in patient cases. It really matters for all kinds of surgeries that a person needs, whether for Parkinson's or epilepsy or whatever. It's a terrific new technology for essentially sewing electrodes in there and getting more higher density of electrodes. So that's great. I just don't think, as far as the future of BCI goes, I don't suspect that people will go in and say, yeah, drill a hole in my head and do that.
Well, it's interesting because I think there's a similar intuition, but say in the world of autonomous vehicles, that folks know how hard it is, and it seems damn impossible. The similar intuition about, I'm sticking on the Elon Musk thing, is just a good, easy example. The similar intuition about colonizing Mars, if you really think about it, it seems extremely difficult, and almost, just technically difficult to a degree where you want to ask, is it really worth doing, worth trying? And then the same is applied with BCI. But the thing about the future is it's hard to predict. So the exciting thing to me with once if successful, it's able to help patients, it may be able to discover something very surprising about our ability to directly communicate with the brain. So exactly what you're interested in is figuring out how to play with this malleable brain, but help assist it somehow. It's such a compelling notion to me that we're now working on all these exciting machine learning systems that are able to learn, from data. And then if we can have this other brain that's a learning system that's live wired on the human side, and them to be able to communicate. It's like a self-play mechanism was able to beat the world champion at Go, so they can play with each other, the computer and the brain, like when you sleep. There's a lot of futuristic kind of things that it's just exciting possibilities. But I hear you. We understand so little about the actual intricacies of the communication of the brain that it's hard to find the common language?
Well, interestingly, the technologies that have been built don't actually require the perfect common language. So, for example, hundreds of thousands of people are walking around with artificial ears and artificial eyes, meaning cochlear implants or retinal implants. So this is, you take essentially a digital microphone, you slip an electrode strip into the inner ear, and people can learn how to hear that way. Or you take an electrode grid and you plug it into the retina at the back of the eye, and people can learn how to see that way. The interesting part is those devices don't speak exactly the natural biological language. They speak the dialect of Silicon Valley. And it turns out that as recently as about 25 years ago, a lot of people thought this was never going to work. They thought it wasn't going to work for that reason, but the brain figures it out. It's really good at saying, okay, look, there's some correlation between what I can touch and feel and hear and so on, and the data that's coming in, or between, I clap my hands and I have signals coming in there, and it figures out how to speak any language.
Oh, that's fascinating. So no matter if it's Neuralink, so directly communicating with the brain, or it's a smartphone or Google Glass, or the brain figures out the efficient way of communication.
Well, exactly. And what I propose is the potato head theory of evolution, which is that all, our eyes and nose and mouth and ears and fingertips, all this stuff is just plug and play. Yeah. And the brain can figure out what to do with the data that comes in. And part of the reason that I think this is right, and I care so deeply about this, is when you look across the animal kingdom, you find all kinds of weird peripheral devices plugged in, and the brain figures out what to do with the data. And I don't believe that Mother Nature has to reinvent the principles of brain operation each time to say, oh, now I'm going to have heat pits to detect infrared. Now I'm going to have something to detect, electroreceptors on the body. Now I'm going to detect something to pick up the magnetic field of the earth with cryptochromes in the eye and so on. Instead, the brain says, oh, I got it. There's data coming in. Is that useful? Can I do something with it? Oh, great. I'm going to mold myself around the data that's coming in.
It's kind of fascinating to think that we think of smartphones and all this new technology as novel. It's totally novel, as outside of what evolution ever intended, or what nature ever intended. It's fascinating to think that the entirety of the process of evolution is perfectly fine and ready for the smartphone and the internet. It's ready. It's ready to be malleable to that, and whatever comes to cyborgs, to virtual reality. We kind of think this is, there's all these books written about what's natural, and we're destroying our natural selves by embracing all this technology. It's kind of, we're probably not giving the brain enough credit. This thing is just fine with new tech.
Oh, exactly. It wraps itself around. And by the way, wait till you have kids. You'll see the ease with which they pick up on stuff. And as Kevin Kelly said, technology is what gets invented after you're born. But the stuff that already exists when you're born, that's not even tech. That's just background furniture. The fact that the iPad exists for my son and daughter, that's just background furniture. So, it's because we have this incredibly malleable system, it just absorbs whatever is going on in the world and learns what to do with it.
So do you think, just to linger for a little bit more, do you think it's possible to co-adjust? We're kind of, for the machine to adjust to the brain, for the brain to adjust to the machine. I guess that's what's already happening.
Sure, that is what's happening. So, for example, when you put electrodes in the motor cortex to control a robotic arm for somebody who's paralyzed, the engineers do a lot of work to figure out, okay, what can we do with the algorithm here so that we can detect what's going on from these cells and figure out how to best program the robotic arm to move given the data that we're measuring from these cells. But also, the brain is learning too. So, the paralyzed woman says, wait, I'm trying to grab this thing. And by the way, it's all about relevance. So if there's a piece of food there and she's hungry, she'll figure out how to get this food into her mouth with the robotic arm because that is what matters.
So in terms of the structure of the brain, again, this may be going into speculation land. I hope you go along with me. Yeah, okay, so the brain seems to be intelligent, and our AI systems aren't very currently. So where do you think intelligence arises in the brain? What is it about the brain?
So if you mean where location-wise, it's no single spot. It would be equivalent to asking, I'm looking at New York City, where is the economy? The answer is you can't point to anywhere. The economy is all about the interaction of all of the pieces and parts of the city. And that's what, intelligence, whatever we mean by that in the brain, is interacting from everything going on at once.
In terms of a structure, so look, humans are much smarter than fish. Maybe not dolphins, but dolphins are mammals, right?
But I assert that what we mean by smarter has to do with live wiring. So what we mean when we say, oh, we're smart is, we can figure out a new thing and figure out a new pathway to get where we need to go. And that's because fish are essentially coming to the table with, okay, here's the hardware, go, swim, mate, eat. But we have the capacity to say, okay, look, I'm going to absorb, but I saw someone else do this thing and I read once that you could do this other thing and so on.
So do you think is there something, I know these are mysteries, but like architecturally speaking, what feature of the brain of the live wire aspect of it that is really useful for intelligence? So like, is it the ability of neurons to reconnect? Like, is there any lessons about the human brain you think might be inspiring for us to take into the machine learning world?
Yeah. I'm actually just trying to write some up on this now called, if you want to build a robot, start with the stomach. And what I mean by that is a robot has to care. It has to have hunger. It has to care about surviving, that kind of thing. Here's an example. So the penultimate chapter of my book, I titled the Wolf and the Mars Rover. And I just look at this simple comparison of, you look at a wolf, it gets its leg caught in a trap. What does it do? It gnaws its leg off, and then it figures out how to walk on 3 legs. No problem. Now, the Mars rover, Curiosity, got its front wheel stuck in some Martian soil, and it died. This project that cost billions of dollars died because it's got its wheel. So wouldn't it be terrific if we could build a robot that chewed off its front wheel and figured out how to operate with a slightly different body plan? That's the kind of thing that we want to be able to build. And to get there, what we need, the whole reason the wolf is able to do that is because its motor and somatosensory systems are live wired. So it says, oh, you know what? Turns out I've got a body plan that's different than what I thought a few minutes ago, but I have a yen to survive, and I care about relevance, which in this case is getting to food, getting back to my pack, and so on. So I'm just going to figure out how to operate with this. Oh, whoops, that didn't work. Oh, okay, I'm kind of getting it to work. But the Mars rover doesn't do that. It just says, oh, geez, I was pre-programmed to have 4 wheels. Now I have 3. I'm screwed.
Yeah, I don't know if you're familiar with a philosopher named Ernest Becker. He wrote a book called Denial of Death. And there's a few psychologists, Sheldon Solomon, I think I just spoke with him on his podcast, who developed terror management theory, which is like Ernest Becker is a philosopher that basically said that fear of mortality is at the core of it. And so I don't know if it sounds compelling as an idea that that all of the civilization we've constructed is based on this, but
I'm familiar with his work. Here's what I think. I think that, yes, fundamentally, this desire to survive is at the core of it. I would agree with that. But how that expresses itself in your life ends up being very different. The reason you do what you do is, you could list the 100 reasons why you chose to write your tweet this way and that way. And it really has nothing to do with the survival part. It has to do with, trying to impress fellow humans and surprise them and say something.
Yeah, it's so many things built on top of each other.
Yeah,
but
exactly.
It's fascinating to think that in artificial intelligence systems, we want to be able to somehow engineer this drive for survival, for immortality. Because as humans, we're not just about survival. We're aware of the fact that we're going to die, which is a very we're aware like
most
space
people
time.
Aren't, by the way.
Aren't?
Confucius said, he said, each person has 2 lives. The second one begins when you realize that you have just one.
Yeah.
But most people, it takes a long time for most people to get there.
You could argue this kind of Freudian thing, which Ernest Becker argues is they actually figured it out early on, and the terror they felt was like the reason it's been suppressed. And the reason most people, when I ask them about whether they're afraid of death, they basically say no. They basically say like,
I'm afraid I won't get like submit the paper before I die. Like they see death as a kind of inconvenient deadline for a particular set of like a book you're writing.
Yeah.
It's as opposed to like, what the hell, this thing ends. It's like, at any moment, like most people as I've encountered do not meditate on the idea that like right now you could die, like right now, like it's like it in the next 5 minutes it could be all over, and meditate on that idea. I think that somehow brings you closer to like the core of the motivations and the core of the human cognition.
I think it might
condition.
be at the core, but like I said, it is not what
There's so many
drives us
stuff
day
on
to
top of
day.
it.
Yeah, there's so many things on top of it, but it is interesting. I mean, as the ancient poet said, "Death whispers at my ear, live, for I come." So it is certainly motivating when we think about that. Okay, I've got some deadline. I don't know exactly what it is, but I better make stuff happen. It is motivating, but I don't think. I mean, I know for just speaking for me personally, that's not what motivates me day to day. It's instead, I want to get this, program up and running before this, or I want to make sure my co-author isn't mad at me because I haven't gotten this in, or I don't want to miss this grant deadline, or, whatever the thing is.
Yeah. It's too distant in a sense. Nevertheless, it is good to reconnect. But for the AI systems, none of that is there. Like a neural network does not fear its mortality. And that seems to be somehow fundamentally missing the point.
I think that's missing the point, but I wonder, it's an interesting speculation about whether you can build an AI system that is much closer to being a human without the mortality and survival piece, but just the thing of relevance. Just, I care about this versus that. Right now, if you have a robot roll into the room, it's going to be frozen because it doesn't have any reason to go there versus there. It doesn't have any particular set of things about this is how I should navigate my next move because I want something.
Yeah, that's the thing about humans is they seem to generate goals. They're like you said, live wired. I mean, it's very flexible in terms of the goals and creative in terms of the goals we generate when we enter a room. You show up to a party without a goal usually, and then you figure it out along the way.
Yes, but this goes back to the question about free will, which is when I walk into the party, if you rewound it 10,000 times, would I go and talk to that couple over there versus that person? Like, I might do this exact same thing every time because I've got some goal stack and I think, okay, well, at this party, I really want to meet these kind of people, or I feel awkward, or whatever my goals are.
So let's step into the gray area between metaphor and engineering with, I'm not sure if you're familiar with brain-computer interfaces. So a company like Elon Musk has Neuralink that's working on putting electrodes into the brain and trying to be able to both read and send electrical signals. Just as you said, even the basic mechanism of communication in the brain is not something we understand. But do you hope, without understanding the fundamental principles of how the brain works, we'll be able to do something interesting at that gray area of metaphor?
It's not my area. So I hope, in the sense like anybody else hopes for some interesting things to happen from research. I would expect more something like Alzheimer's will get figured out from modern neuroscience. That, there's a lot of human suffering based on brain disease. And we throw things like lithium at the brain, it kind of works. No one has a clue why. That's not quite true, but mostly we don't know. And that's even just about the biochemistry of the brain and how it leads to mood swings and so on. How thought emerges from that, we were really, really completely dim. So that you might want to hook up electrodes and try to do some signal processing on that and try to find patterns. Fine, by all means, go for it. It's just not scientific at this point. It's like kind of sitting in a satellite and watching the emissions from a city and trying to infer things about the microeconomy, even though you don't have microeconomic concepts. I mean, it's really that kind of thing. And so, yes, can you find some signals that do something interesting or useful? Can you control a cursor or mouse with your brain? Yeah, absolutely. And I can imagine business models based on that, and even, medical applications of that. But from there to understanding algorithms that allow us to really tie in deeply from the brain to the computer, I don't agree with Elon Musk. I don't think that's not for our generation. It's not even for this century.
So just in the hopes of getting you to dream, you've mentioned Kolmogorov and Turing might pop up. Do you think that there might be breakthroughs that will get you to sit back in 5-10 years and say, wow?
Oh, I'm sure there will be, but I don't think that there'll be demos that impress me. I don't think that having a computer call a restaurant and pretend to be a human is breakthrough.
Right.
And people, some people present it as such. It's imitating human intelligence. It's even putting coughs in the thing to make a bit of a PR stunt. And so, fine, that the world runs on those things too. And I don't want to diminish all the hard work and engineering that goes behind things like that, and the ultimate value to the human race. But that's not scientific understanding. And I know the people that work on these things, they are after scientific understanding. In the meantime, they've got to kind of, the train's got to run, and they got mouths to feed, and they got things to do. And there's nothing wrong with all that. I would call that, though, just engineering. And I want to distinguish that between an engineering field like electrical engineering, chemical engineering, that originally emerged, that had real principles, and you really knew what you're doing, and you had a little scientific understanding, maybe not even complete. So it became more predictable, and it really gave value to human life because it was understood. And so we don't want to muddle too much these waters of what we're able to do versus what we really can do in a way that's going to impress the next. So I don't need to be wowed, but I think that someone comes along in 20 years, a younger person who's absorbed all the technology, and for them to be wowed, I think they have to be more deeply impressed. A young Kolmogorov would not be wowed by some of the stunts that you see right now coming from the big companies.
The demos, but do you think the breakthroughs from Kolmogorov would be, and give this question a chance, do you think they'll be in the scientific fundamental principles arena, or do you think it's possible to have fundamental breakthroughs in engineering? Meaning, I would say some of the things that Elon Musk is working with, SpaceX, and then others, sort of trying to revolutionize the fundamentals of engineering, of manufacturing, of saying, here's a problem we know how to do a demo of, and actually taking it to scale.
Yeah, so there's going to be all kinds of breakthroughs. I just don't like that terminology. I'm a scientist, and I work on things day in and day out, and things move along, and eventually say, wow, something happened, but I don't like that language very much. Also, I don't like to prize theoretical breakthroughs over practical ones. I tend to be more of a theoretician, and I think there's lots to do in that arena right now. And so I wouldn't point to the Kolmogorovs. I might point to the Edisons of the era, and maybe Musk is a bit more like that. But, Musk, God bless him, also will say things about AI that he knows very little about. And he doesn't know what he is, leads people astray when he talks about things he doesn't know anything about. Trying to program a computer to understand natural language, to be involved in a dialogue like we're having right now, that can happen in our lifetime. You could fake it. You can mimic, sort of take old sentences that humans use and retread them. But the deep understanding of language, no, it's not going to happen. And so from that, I hope you can perceive that the yet deeper kind of aspects in intelligence are not going to happen. Now, will there be breakthroughs? I think that Google was a breakthrough. I think Amazon is a breakthrough. I think Uber is a breakthrough, that bring value to human beings at scale in brand new ways based on data flows and so on. A lot of these things are slightly broken because there's not a kind of a engineering field that takes economic value in context of data and at planetary scale and worries about all the externalities, the privacy. We don't have that field, so we don't think these things through very well. But I see that as emerging, and that will be looking back from 100 years, that will be constitute a breakthrough in this era, just like electrical engineering was a breakthrough in the early part of the last century, and chemical engineering was a breakthrough.
So the scale, the markets that you talk about, and we'll get to, will be seen as sort of breakthrough, and we're in the very early days of really doing interesting stuff there, and we'll get to that. But it's just taking a quick step back. Can you give? We kind of threw off the historian hat. I mean, you briefly said that the history of AI kind of mimics the history of chemical engineering, but what are they?
Yes.
And how can you use them to help us understand the brain and the development of the brain?
This is very, very important. So the first thing I like to say, and please keep this in the video. The first thing I like to say is that an organoid, a brain organoid, is not the same as a brain. Okay? It's a fundamental distinction. It's a system, a cellular system, that one can develop in the culture dish, starting from stem cells, that will mimic some aspects of the development of the brain, but not all of it. They are very small. Maximum, they become about 4 to 5 millimeters in diameters. They are much simpler than our brain, of course, but yet they are the only system where we can literally watch a process of human brain development unfold. And by watch, I mean study it. Remember when I told you that we can't understand everything about development in our own brain by studying a mouse? Well, we can study the actual process of development of the human brain because it all happens in utero, so we will never have access to that process, ever. And therefore, this is our next best thing, like a bunch of stem cells that can be coaxed into starting a process of neural tube formation. Remember that tube that is made by the embryo early on? And from there, a lot of the cell types that are present within the brain, and you can simply watch it and study it. But you can also think about diseases where development of the brain does not proceed normally, right, properly. Think about neurodevelopmental diseases. There are many, many different types. Think about autism spectrum disorders. There are also many different types of autism. So there you could take a stem cell, which really means either a sample of blood or a sample of skin from the patient, make a stem cell, and then with that stem cell, watch a process of formation of a brain organoid of that person. With that genetics, with that genetic code in it. And you can ask, what is this genetic code doing to some aspects of development of the brain? And for the first time, you may come to solutions like what cells are involved in autism.
So I have so many questions around this. So if you take this human stem cell for that particular person with that genetic code, and you try to build an organoid, how often will it look similar? What's the
the reproducibility.
Yes, or how much variability is the flip side of that.
So there is much more variability in building organoids than there is in building brain. It's really true that the majority of us, when we are born as babies, our brains look a lot like each other. This is the magic that the embryo does, where it builds a brain in the context of a body. And there is very little variability there. There is disease, of course, but in general, little variability. When you build an organoid, we don't have the full code for how this is done. And so in part, the organoid somewhat builds itself because there are some structures of the brain that the cells know how to make. And another part comes from the investigator, the scientist, adding to the media factors that we know in the mouse, for example, would foster a certain step of development. But it's very limited. And so as a result, the kind of product you get in the end is much more reductionist, is much more simple than what you get in vivo. It mimics early events of development as of today, and it doesn't build very complex type of anatomy and structure, does not as of today, which happens instead in vivo. And also the variability that you see one organoid to the next tends to be higher than when you compare an embryo to the next.
So, then the next question is, how hard, and maybe another flip side of that, expensive is it to go from one stem cell to an organoid? How many can you build in life? Because it sounds very complicated.
It's work, definitely, and it's money, definitely. But you can really grow a very high number of these organoids. Can go... Perhaps I told you the maximum they become about 5 millimeters in diameter.
Which is how many cells?
So this is about the size of a tiny raisin, or perhaps the seed of an apple. And so you can grow 50 to 100 of those inside one big bioreactors, which are these flasks where the media provides nutrients for the organoids. So the problem is not to grow more or less of them. it's really to figure out how to grow them in a way that they are more and more reproducible. For example, organoid to organoid, so they can be used to study a biological process. Because if you have too much variability, then you never know if what you see is just an exception or really the rule.
So what does an organoid look like? Are there different neurons already emerging? Is there, well, first, can you tell me what kind of neurons are there?
Yes.
Are they sort of all the same? Are they not all the same? How much do we understand? And how much of that variance, if any, can exist in organoids?
Yes. So you could grow. I told you that the brain has different parts. Right. So the cerebral cortex is on top, the top part of the brain, but there is another region called the striatum that is below the cortex, and so on and so forth. All of these regions have different types of cells in the actual brain. Okay. Mm-hmm. And so scientists have been able to grow organoids that may mimic some aspects of development of these different regions of the brain. Yeah. And so we are very interested in the cerebral cortex.
That's the coolest part, right?
Very cool. I agree with you. We wouldn't be here talking if we didn't have a cerebral cortex. Yeah. It's also, I like to think, the part of the brain that really truly makes us human, the most evolved in recent evolution. And so in the attempt to make the cerebral cortex, and by figuring out a way to have these organoids continue to grow and develop for extended periods of time, much like it happens in the real embryo, months and months in culture, then you can see that many different types of neurons of the cortex appear. And at some points, also the astrocytes, so the glia cells of the cerebral cortex also appear.
What are these?
Astrocytes.
The astrocytes.
The astrocytes are not neurons, so they're not nerve cells, but they play very important roles. One important role is to support the neuron, mm-hmm. but of course they have much more active type of roles. They're very important, for example, to make the synapses, which are the point of contacts and communication between two neurons. So
all that chemistry fun happens in the synapses happens because of these cells? Are they the medium in which?
It happens because of the interactions. It happens because you are making the cells, and they have certain properties, including the ability to make, neurotransmitters, which are the chemicals that are secreted to the synapses, including the ability of making these axons grow with their growth cones, and so on and so forth. And then you have other cells around it that release chemicals or touch the neurons or interact with them in different ways to really foster this perfect process, in this case of synaptogenesis. Yeah. And this does happen within organoids.
With organoids. So the mechanical and the chemical stuff happens.
Yeah. The connectivity between neurons. This, in a way, is not surprising because scientists have been culturing neurons forever. And when you take a neuron, even a very young one, and you culture it, eventually finds another cell or another neuron to talk to, it will form a synapse.
Are we talking about mice neurons? Are we talking about human neurons?
It doesn't matter, both.
So you can culture a neuron, like a single neuron, and give it a little friend, and it starts interacting?
Yes. So neurons are able to, it's more simple than what it may sound to you. Neurons have molecular properties and structural properties that allow them to really communicate with other cells. And so if you put not one neuron, but if you put several neurons together, chances are that they will form synapses with each other.
Okay, great. So an organoid is not a brain.
No.
But there's it's able to, especially what you're talking about, mimic some properties of the cerebral cortex, for example. Mm-hmm. So what can you understand about the brain by studying an organoid of the cerebral cortex?
I can literally study how all this incredible diversity of cell type, all these many, many different classes of cells, how are they made? How do they look like? What do they need to be made properly? And what goes wrong if the genetics of that stem cell that I used to make the organoid came from a patient with a neurodevelopmental disease? Can I actually watch for the very first time what may have gone wrong years before in this kid when its own brain was being made? Think about that loop. In a way, it's a little tiny rudimentary window into the past, into the time when that brain in a kid that had this neurodevelopmental disease was being made. And I think that's unbelievably powerful because today we have no idea of what cell types, we barely know what brain regions are affected in these diseases. Now we have an experimental system that we can study in the lab, and we can ask, what are the cells affected? When, during development, things went wrong? What are the molecules among the many, many different molecules that control brain development? Which ones are the ones that really messed up here and we want perhaps to fix? And what is really the final product? Is it a less strong kind of circuit and brain? Is it a brain that lacks a cell type? What is it? Because then we can think about treatment and care for these patients that is informed rather than just based on current diagnostics.
So how hard is it to detect through the developmental process? It's a super exciting tool to see how different conditions develop. How hard is it to detect that, wait a minute, this is abnormal development?
Yeah.
How hard is, how much signal is there? How much of it is it a mess?
Because things can go wrong at multiple levels, right? You could have a cell that is born and built, but then doesn't work properly, or a cell that is not even born, or a cell that doesn't interact with other cells differently, and so on and so forth. So today we have technology that we did not have even 5 years ago that allows us to look, for example, at the molecular picture of a cell, of a single cell in a sea of cells with high precision. And so that molecular information, where you compare many, many single cells for the genes that they produce, between a control individual and an individual with a neurodevelopmental disease, that may tell you what is different molecularly. Or you could see that some cells are not even made, for example, or that the process of maturation of the cells may be wrong. There are many different levels here. And we can study the cells at the molecular level, but also we can use the organoids to ask questions about the properties of the neurons, the functional properties, how they communicate with each other, how they respond to a stimulus, and so on and so forth. And we may get at abnormalities there, right?
Detect those. So how early is this work maybe in the history of science? so
an easy question.
I mean, so if you were to, if you and I time travel 1,000 years into the future, organoids seem to be, maybe I'm romanticizing the notion, but you're building not a brain, but something that has properties of a brain. So it feels like you might be getting close to, in the building process, to build this to understand. So how far are we in this understanding process of development?
1,000 years from now, it's a long time from now. So if this planet is still gonna be here 1,000 years from now.
So I mean, if brain, sort of living through the whole mess of it, the human condition, full of love, maybe fear, ultimately mortal. How has studying the brain changed the way you see yourself? When you look in the mirror, when you think about your life, the fears, the love, when you see your own life, your own mortality?
Yeah, that's a very good question. It's almost impossible to dissociate sometime, for me, some of the things we do or some of the things that other people do from, oh, that's because that part of the brain is working in a certain way. Yeah. Or thinking about a teenager, going through teenage years and being at times funny in the way they think. And impossible for me not to think it's because they're going through this period of time called critical periods of plasticity where their synapses are being eliminated here and there, and they're just confused. And so from that comes perhaps a different take on that behavior, or maybe I can justify it scientifically in some sort of way. I also look at humanity in general, and I am amazed by what we can do and the kind of ideas that we can come up with. And I cannot stop thinking about how the brain is continuing to evolve. I don't know if you do this, but I think about the next brain sometimes. Where are we going with this? Like, what are the features of this brain that, evolution is really playing with to get us, in the future, the new brain? It's not over, right? It's a work in progress.
So let me just maybe talk through the first few months and then on to the first 20 years and then for the rest of our lives. What does the development of the human brain look like? What are the different stages?
Yeah. At the beginning, you have to build a brain, right? And the brain is made of cells.
What's the very beginning? Which beginning are we talking about?
In the embryo. As the embryo is developing in the womb, in addition to making all of the other tissues of the embryo, the muscle, the heart, the blood, the embryo is also building the brain. And it builds from a very simple structure called the neural tube, which is basically nothing but a tube of cells that spans sort of the length of the embryo from the head all the way to the tail, let's say, right, of the embryo. And then in human beings, over many months of gestation, from that neural tube, which contains stem cell-like cells of the brain, you will make many, many other building blocks of the brain. So all of the other cell types, because there are many, many different types of cells in the brain, that will form specific structures of the brain. So you can think about embryonic development of the brain as just the time in which you are making the building blocks, the cells.
Are the stem cells relatively homogeneous, like uniform, or are they all different
types? It's a very good question. It's exactly how it works. You start with a more homogeneous, perhaps more multipotent type of stem cell.
What's multipotent?
Multipotent, it means that it has the potential to make many, many different types of other cells. And then with time, these progenitors become more heterogeneous, which means more diverse. There are going to be many different types of these stem cells. And also they will give rise to progeny, to other cells that are not stem cells, that are specific cells of the brain that are very different from the mother stem cell. And now you think about this process of making cells from the stem cells over many, many months of development for humans. And what you're doing, you're building the cells that physically make the brain, and then you arrange them in specific structures that are present in the final brain. So you can think about the embryonic development of the brain as the time where you're building the bricks. You're putting the bricks together to form buildings, structures, regions of the brain, and where you make the connections between these many different type of cells, especially nerve cells, neurons, right, that transmit action potentials and electricity.
I've heard you also say somewhere, I think, correct me if I'm wrong, that the order of the way this builds matters.
Oh, yes. If you are an engineer and you think about development, you can think of it as, well, I could also take all the cells and print them all together into a brain in the end. But development is much more than that. So the cells are made in a very specific order that subserve the final product that you need to get. And so, for example, all of the nerve cells, the neurons, are made first. And all of the supportive cells of the neurons, like the glia, is made later. And there is a reason for that, because they have to assemble together in specific ways. But you also may say, well, why don't we just put them all together in the end? It's because as they develop next to each other, they influence their own development. So it's a different thing for a glia to be made alone in a dish than a glia cell be made in a developing embryo with all these other cells around it that produce all these other signals.
First of all, that's mind-blowing that this development process, from my perspective in artificial intelligence, you often think of how incredible the final product is.
Yeah.
The final product, the brain. But you're making me realize that the final product is just, the beautiful thing is the actual development process. Do we know the code that drives that development?
Yeah.
Do we have any sense?
First of all, thank you for saying that it's really the formation of the brain. It's really its development, this incredibly choreographed dance that happens the same way every time each one of us builds the brain, right? And that builds an organ that allows us to do what we're doing today, right?
Yeah.
That is mind-blowing, and this is why developmental neurobiologists never get tired of studying that. Now you're asking about the code. What drives this? How is this done? Well, it's millions of years of evolution, of really fine-tuning gene expression programs that allow certain cells to be made at a certain time and to become a certain cell type, but also mechanical forces of pressure, bending. This embryo is will not stay a tube, this brain for very long. At some point, this tube in the front of the embryo will expand to make the primordium of the brain, right? Now the forces that control that these cells feel, and this is another beautiful thing, the very force that they feel, which is different from a week before, a week ago, will tell the cell, oh, you're being squished in a certain way. Begin to produce these new genes because now you are at the corner or you are, in a stretch of cells or whatever it is. And that mechanical physical force shapes the fate of the cell as well.
So
it's not only chemical, it's also mechanical.
So from my perspective, biology is this incredibly complex mess, gooey mess. So you're saying mechanical forces.
Yes.
How different is like a computer or any kind of mechanical machine that we humans build and the biological systems?
Yeah.
Have you been, because you've worked a lot with biological systems,
yes.
Are they as much of a mess as it seems from a perspective of an engineer, a mechanical engineer?
Yeah. They are much more prone to taking alternative routes, right? So if we go back to printing a brain versus developing a brain, of course, if you print a brain, given that you start with the same building blocks, the same cells, you could potentially print it the same way every time. Mm-hmm. But that final brain may not work the same way as a brain built during development does, because the very same building blocks that you're using developed in a completely different environment, right? That was not the environment of the brain. Therefore, they're going to be different just by definition. So if you instead use development to build, let's say, a brain organoid, which maybe we will be talking about in a few minutes.
Those things are fascinating.
Yes. Sorry. So if you use processes of development, then when you watch it, you can see that sometimes things can go wrong in some organoids. And by wrong, I mean different, one organoid from the next. While if you think about that embryo, it always goes right. So it's this development, it's for as complex as it is. Every time a baby is born has, with very few exceptions, the brain is like the next baby. But it's not the same if you develop it in a dish. And first of all, we don't even develop a brain, you develop something much simpler in the dish. But there are more options for building things differently, which really tells you that evolution has played a really tight game here for how, in the end, the brain is built in vivo.
So just a quick, maybe dumb question, but it seems like the building process is not a dictatorship. It seems like there's not a centralized, like, high-level mechanism that says, okay, this cell built itself the wrong way, I'm going to kill it. It seems like there's a really strong distributed mechanism. Is that in your sense from what
there are a lot of possibilities, right? And if you think about, for example, different species building their brain, each brain is a little bit different. So the brain of a lizard is very different from that of a chicken, from that of a, one of us, and so on and so forth. And still is a brain, but it was built differently, starting from stem cells that pretty much had the same potential, but in the end, evolution builds different brains in different species because that serves, in a way, the purpose of that species and the well-being of that organism.
Right.
And so there are many possibilities, but then there is a way, and you were talking about a code. Nobody knows what the entire code of development is. Of course, we don't. We know bits and pieces of very specific aspects of development of the brain, what genes are involved to make a certain cell types, how those two cells interact to make the next level structure. That we might know, but the entirety of it, how it's so well controlled, it's really mind-blowing.
So in the first 2 months in the embryo or whatever, the first few weeks, few months, the building blocks are constructed, the different regions of the brain, I guess, and the nervous system.
Well, this continues way longer than just the first few months. So over the very first few months, you build a lot of these cells, but then there is continuous building of new cell types all the way through birth. And then even postnatally, I don't know if you've ever heard of myelin. Myelin is this sort of insulation that is built around the cables of the neurons so that the electricity can go really fast from
the axons, I guess they're called.
The axons, they're called axons, exactly. And so as human beings, we myelinate our cells postnatally. A kid, a 6-year-old kid has barely started the process of making the mature oligodendrocytes, which are the cells that then eventually will wrap the axons into myelin. And this will continue, believe it or not, until we are about, 25, 30 years old. So there is a continuous process of maturation and tweaking and additions and also in response to what we do.
I remember taking AP biology in high school, and in the textbook, it said that, I'm going by memory here, that scientists disagree on the purpose of myelin in the brain. Is that totally wrong? So like I guess it speeds up the okay, might be wrong here, but I guess it speeds up the electricity traveling down the axon or something.
Yeah.
But
so that's the most sort of canonical, and definitely that's the case. So you have to imagine an axon, and you can think about it as a cable of some type with electricity going through. And what myelin does by insulating the outside, I should say there are tracts of myelin and pieces of axons that are naked without myelin. And so by having the insulation, the electricity, instead of going straight through the cable, it will jump over a piece of myelin, right, to the next naked little piece and jump again. And therefore, that's the idea that you go faster. And it was always thought that in order to build a big brain, a big nervous system, in order to have a nervous system that can do very complex type of things, then you need a lot of myelin because you want to go fast with this information from point A to point B. A few years ago, maybe 5 years ago or so, we discovered that some of the most evolved, which means the newest type of neurons that we have as non-human primates, as human beings in the top of our cerebral cortex, which should be the neurons that do some of the most complex things that we do. Well, those have axons that have very little myelin.
Wow.
And they have very interesting ways in which they put this myelin on their axons, a little piece here, then a long track with no myelin, another chunk there, and some don't have myelin at all. So now you have to explain where we're going with evolution. And if you think about it, perhaps as an electrical engineer, when I looked at it, I initially thought, and I'm a developmental neurobiologist, I thought maybe this is what we see now, but if we give evolution another few million years, we'll see a lot of myelin on these neurons too. But I actually think now that that's instead the future of the brain.
Myelin.
Less myelin might allow for more flexibility on what you do with your axons, and therefore more complicated and unpredictable type of functions, which is also a bit mind-blowing.
Well, so it seems like it's controlling the timing of the signal. So in the timing, you can encode a lot of information.
Yeah.
And so the brain
The timing, the chemistry of that little piece of axon. Perhaps it's a dynamic process where the myelin can move. Now you see how many layers of variability you can add, and that's actually really good if you're trying to come up with a new function or a new capability or something unpredictable in a way.
So we're going to jump around a little. Like they write a book. Obviously, there'll be a chapter about you.
Let's write the science fiction book today.
Yeah, today. I guess where we really understood very little about the brain a century ago. I was a big fan in high school of reading Freud and so on.
Yes.
Still am, of psychiatry. I would say we still understand very little about the functional aspect of just...
Yeah.
But how... in the history of understanding the biology of the brain, the development, how far are we along?
It's a very good question. And so this is just, of course, my opinion. I think that we did not have technology, even 10 years ago, or 20, certainly not 20 years ago, to even think about experimentally investigating the development of the human brain. So we've done a lot of work in science to study the brain of many other organisms. Mm-hmm. Now we have some technologies, which I'll spell out, that allow us to actually look at the real thing and look at the brain, at the human brain. So what are these technologies? There has been huge progress in stem cell biology. The moment someone figured out how to turn a skin cell into an embryonic stem cell, basically, and that how that embryonic stem cell could begin a process of development again to, for example, make a brain, there was a huge advance. And in fact, there was a Nobel Prize for that. That started the field really of using stem cells to build organs. Now we can build on all the knowledge of development that we built over the many, many, many years to say, how do we make these stem cells now make more and more complex aspects of development of the human brain? So this field is young, the field of brain organoids, but it's moving fast. And it's moving fast in a very serious way that is rooted in labs with the right ethical framework and really building on solid science for what reality is and what is not. And but it will go fast and it will be more and more powerful. We also have technology that allows us to basically study the properties of single cells across many, many millions of single cells, which we didn't have perhaps 5 years ago. So now with that, even an organoid that has millions of cells can be profiled in a way, looked at with very, very high resolution, the single cell level, to really understand what is going on. And you could do it in multiple stages of development, and you can build your hypothesis and so on and so forth. So it's not going to be 1,000 years. It's going to be a shorter amount of time. And I see this as a sort of an exponential growth of this field enabled by these technologies that we didn't have before. And so we're going to see something transformative that we didn't see at all in the prior 1,000 years.
So I apologize for the crazy sci-fi questions, but the developmental process is fascinating to watch and study. But how far are we away from, and maybe how difficult is it to build not just an organoid, but a human brain?
Okay.
From a stem cell.
Yeah. First of all, that's not the goal for the majority of the serious scientists that work on this, because you don't have to build the whole human brain to make this model useful for understanding how the brain develops or understanding disease. You don't have to build the whole thing.
So let me just comment on that. It's fascinating. It shows to me the difference between you and I. Is you're actually trying to understand the beauty of the human brain and to use it to really help thousands or millions of people with disease and so on, right? From an artificial intelligence perspective, we're trying to build systems that we can put in robots and try to create systems that have echoes of the intelligence about reasoning about the world, navigating the world. Right. It's different objectives, I think.
Yeah, that's very much science fiction.
Science fiction, but we operate in science fiction a little bit. But so on that point of building a brain, even though that is not the focus or interest perhaps of the community, how difficult is it? Is it truly science fiction at this point?
I think the field will progress, like I said. and that this system will be more and more complex in a way, right? But there are properties that emerge from the human brain that have to do with the mind, that may have to do with consciousness, may have to do with intelligence or whatever, that we really don't understand even how they can emerge from an actual real brain, and therefore we cannot measure or study in an organoid. So I think that this field, many years from now, may lead to the building of better neural circuits of that really are built out of understanding of how this process really works. And it's hard to predict how complex this really will be. I really don't think we're so far from. It makes me laugh. Really, it's really that far from building the human brain. But you're gonna be building something that is, always a bad version of it, but that may have really powerful properties and might be able to, respond to stimuli or be used in certain context. And this is why I really think that there is no other way to do this science but within the right ethical framework. Because where you're going with this is also, we can talk about science fiction and write that book, and we could today, but this work happens in a specific ethical framework that we don't decide just as scientists, but also as a society.
Brain for many years. So let me ask you an out-of-the-box question first. How likely is it that there's intelligent life out there in the universe outside of Earth with something like the human brain? So I can put it another way. How unlikely is the human brain? How difficult is it to build a thing through the evolutionary process?
Well, it has happened here, right, on this planet.
Once, yes.
Once. So that simply tells you that it could, of course, happen again other places. It's only a matter of probability. What the probability that you would get a brain like the ones that we have, like the human brain. So how difficult is it to make the human brain? It's pretty difficult. But most importantly, I guess we know very little about how this process really happens. And there is a reason for that, actually multiple reasons for that. Most of what we know about how the mammalian brain, so the brain of mammals, develop comes from studying in labs other brains, not our own brain, the brain of mice, for example. But if I showed you a picture of a mouse brain and then you put it next to a picture of a human brain, they don't look at all like each other. So they're very different. And therefore, there is a limit to what you can learn about how the human brain is made by studying the mouse brain. There is a huge value in studying the mouse brain. There are many things that we have learned, but it's not the same thing.
So in having studied the human brain, or through the mouse and through other methodologies that we'll talk about, do you have a sense, I mean, you're one of the experts in the world, how much do you feel you know about the brain? And how often do you find yourself in awe of this mysterious thing?
Yeah, you pretty much find yourself in awe all the time. It's an amazing process. It's a process by means that we don't fully understand, at the very beginning of embryogenesis, the structure called the neural tube literally self-assembles. And it happens in an embryo, and it can happen also from stem cells in a dish. Okay? And then from there, these stem cells that are present within the neural tube give rise to all of the thousands and thousands of different cell types that are present in the brain through time, right? With the very intriguing, interesting observation is that the time that it takes for the human brain to be made, it's human time, meaning that for me and you, it took almost 9 months of gestation to build the brain, and then another 20 years of learning postnatally to get the brain we have today that allows us to this conversation. Yeah. A mouse takes 20 days or so for an embryo to be born. And so the brain is built in a much shorter period of time. And the beauty of it is that if you take mouse stem cells and you put them in a culture dish, the brain organoid that you get from a mouse is formed faster than if you took human stem cells and put them in the dish and let them make a human brain organoid.
So the very developmental process is
controlled by the speed of the species.
Which means it's on purpose. It's not accidental, or there is something in that temporal.
It's
dynamics
very
of that
exactly that is very important for us to get the brain we have, and we can speculate for why that is. You know, it takes us a long time as human beings after we're born to learn all the things that we have to learn to have the adult brain. It's actually 20 years. Think about it. From when a baby is born to when a teenager goes through puberty to adults, it's a long time.
Do you think you can? So, do you think suffering is fundamental to happiness along these lines?
Suffering is the result of caring about things that you cannot change. And if you are able to change what you care about to those things that you can change, you will not suffer.
But would you then be able to experience happiness?
Yes. But happiness itself is not important. Happiness is like a cookie. When you are a child, you think cookies are very important and you want to have all the cookies in the world. You look forward to being an adult because then you have as many cookies as you want, right?
Yes.
But as an adult, you realize a cookie is a tool. It's a tool to make you eat vegetables. And once you eat your vegetables anyway, you stop eating cookies for the most part, because otherwise you will get diabetes and will not be around for your kids.
Yes, but then the scarcity of a cookie, if scarcity is enforced, nevertheless, so like the pleasure comes from the scarcity.
Yes, but the happiness is a cookie that your brain bakes for itself. It's not made by the environment. The environment cannot make you happy. It's your appraisal of the environment that makes you happy. And if you can change the appraisal of the environment, which you can learn to, then you can create arbitrary states of happiness. And some meditators fall into this trap. So they discover the room, this basement room in their brain where the cookies are made, and they indulge in stuff themselves. And after a few months, it gets really old and the big crisis of meaning comes. Because they thought before that their unhappiness was the result of not being happy enough. So they fixed this, right? They can release the neurotransmitters at will if they train. And then the crisis of meaning pops up at a deeper layer. And the question is, why do I live? How can I make a sustainable civilization that is meaningful to me? How can I insert myself into this? And this was the problem that you couldn't solve in the first place.
But at the end of all this, let me then ask that same question. What is the answer to that? What could a possible answer be of the meaning of life? What could an answer be? What is it to you?
I think that if you look at the meaning of life, you look at what the cell is. Life is the cell, right?
The original cell.
Yes, or this principle, the cell. It's this self-organizing thing that can participate in evolution. In order to make it work, it's a molecular machine. It needs a self-replicator, an entropy extractor, and a Turing machine. If any of these parts is missing, you don't have a cell and it is not living, right? And life is basically the emergent complexity over that principle. Once you have this intelligent supermolecule, the cell, there is very little that you cannot make it do. It's probably the optimal computonium, and especially in terms of resilience. Right? It's very hard to sterilize a planet once it's infected with life.
So it's active function of these three components of the supercell of cell is present in the cell, is present in us, and it's just...
We are just an expression of the cell. It's a certain layer of complexity in the organization of cells. So in a way, it's tempting to think of the cell as a von Neumann probe. If you want to build intelligence on other planets, the best way to do this is to infect them with cells. And wait for long enough, and with a reasonable chance, the stuff is going to evolve into an information processing principle that is general enough to become sentient.
With that idea is very akin to sort of the same dream and beautiful ideas that are expressed through cellular automata in their most simple mathematical form.
Mm-hmm.
If you just inject the system with some basic mechanisms of replication and so on, basic rules, amazing things would emerge.
And the cell is able to do something that James Tardy calls existential design. He points out that in technical design, we go from the outside in. We work in a highly controlled environment in which everything is deterministic, like our computers, or our labs, or our engineering workshops. And then we use this determinism to implement a particular kind of function that we dream up and that seamlessly interfaces with all the other deterministic functions that we already have in our world. So it's basically from the outside in. And biological systems designed from the inside out. A seed will become a seedling by taking some of the relatively unorganized matter around it and turn it into its own structure, and thereby subdue the environment. And cells can cooperate if they can rely on other cells having a similar organization that is already compatible. But unless that's there, the cell needs to divide to create that structure by itself, right? So it's a self-organizing principle that works on a somewhat chaotic environment. And the purpose of life, in the sense, is to produce complexity. And the complexity allows you to harvest negative entropy gradients that you couldn't harvest without the complexity. And in this sense, intelligence and life are very strongly connected, because the purpose of intelligence is to allow control under conditions of complexity. So basically, you shift the boundary between the ordered systems into the realm of of chaos. You build bridgeheads into chaos with complexity. And this is what we are doing. This is not necessarily a deeper meaning. I think the meaning that we have priors for, that we evolved for, outside of the priors, there is no meaning. Meaning only exists if a mind projects it, right?
Yeah.
That is probably civilization. I think that what feels most meaningful to me is to try to build and maintain a sustainable civilization.
And taking a slight step outside of that, we talked about a man with a beard and God, but some mechanism perhaps must have planted the seed, the initial seed of the cell. Do you think there is a God? What is a God? And what would that look like?
So if there was no spontaneous abiogenesis, that in the sense that the first cell formed by some happy random accidents where the molecules just happen to be in the right constellation to each other.
But there could also be the mechanism of that allows for the random. I mean, there's like turtles all the way down. There has to be a head turtle at the bottom.
Let's consider something really wild. Imagine, is it possible that a gas giant could become intelligent? What would that involve? So imagine you have vortices that spontaneously emerge on the gas giants, like big storm systems that endure for thousands of years. And some of these storm systems produce electromagnetic fields because some of the clouds are ferromagnetic or something. And as a result, they can change how certain clouds react rather than other clouds, and thereby produce some self-stabilizing patterns that eventually lead to regulation, feedback loops, nested feedback loops, and control. So imagine you have such a thing that basically has emergent, self-sustaining, self-organizing complexity. And at some point this wakes up and realizes, and basically Lem Solaris, I am a thinking planet, but I will not replicate because I cannot recreate the conditions of my own existence somewhere else. I'm just basically an intelligence that has spontaneously formed because it could. And now it builds a von Neumann probe. And the best von Neumann probe for such a thing might be the cell. So maybe it, because it's very, very clever and very enduring, creates cells and sends them out, and one of them has infected our planet. I'm not suggesting that this is the case, but it would be compatible with the panspermium hypothesis, and with my intuition that abiogenesis is very unlikely. It's possible, but you probably need to roll the cosmic dice very often, maybe more often than there are planetary surfaces. I don't know.
So God is just a large enough, a system that's large enough that allows randomness.
No, I don't think that God has anything to do with creation. I think it's a mistranslation of the Talmud into the Catholic mythology. I think that Genesis is actually the childhood memories of a God. So
Genesis is
the childhood memories of a God. It's basically a mind that is remembering how it came into being. Wow. And we typically interpret Genesis as the creation of a physical universe by a supernatural being.
Yes.
And I think when you'll read it, there is light and darkness that is being created. And then you discover sky and ground. You create them. You construct the plants and the animals, and you give everything their names and so on. That's basically cognitive development. It's a sequence of steps that every mind has to go through when it makes sense of the world. And when you have children, you can see how initially they distinguish light and darkness, and then they make out directions in it, and they discover sky and ground, and they discover the plants and the animals, and they give everything their name. And it's a creative process that happens in every mind. Because it's not given, right? Your mind has to invent these structures to make sense of the patterns on your retina. Also, if there was some big nerd who set up a server and runs this world on it, this would not create a special relationship between us and the nerd. This nerd would not have the magical power to give meaning to our existence, right? So this, equation of a creator god with the god of meaning is sleight of hand. You shouldn't do it. The other one that is done in Catholicism is the equation of the first mover, the prime mover of Aristotle, which is basically the automaton that runs the universe. Aristotle says, if things are moving and things seem to be moving here, something must move them, right?
Mm-hmm.
If something moves them, something must move the thing that is moving it. So there must be a prime mover. This idea to say that this prime mover is a supernatural being is complete nonsense, right? It's an automaton in the simplest case. So we have to explain the enormity that this automaton exists at all. But again, we don't have any possibility to infer anything about its properties except that it's able to produce change in information, right? So there needs to be some kind of computational principle. This is all there is. But to say this automaton is identical again with the creator or first cause or with the thing that gives meaning to our life is confusion. No, I think that what we perceive is the higher being that we are part of. And the higher being that we are part of is the civilization. It's the thing in which we have a similar relationship as the cell has to our body. And we have this prior because we have evolved to organize in these structures.
Mm-hmm.
So basically, the Christian God in its natural form, without the mythology, if you undress it, is basically the Platonic form of a civilization.
Is the ideal?
Yes, it's this ideal that you try to approximate when you interact with others, not based on your incentives, but on what you think is right.
Wow, we covered a lot of ground, and we're left with one of my favorite lines, and there's many, which is happiness is a cookie that the brain bakes itself. It's been a huge honor and a pleasure to talk to you. I'm sure our paths will cross many times again. Joscha, thank you so much for talking today. Really appreciate it.
Thank you, Lex. It was so much fun. I enjoyed it.
Awesome. Thanks for listening to this conversation with Joscha Bach, and thank you to our sponsors, ExpressVPN and Cash App. Please consider supporting this podcast by getting ExpressVPN at expressvpn.com/LexPod and downloading Cash App and using code LEXPodcast. If you enjoy this thing, subscribe on YouTube, review it with 5 stars on Apple Podcast, support it on Patreon, or simply connect with me on Twitter at Lex Fridman. And yes, try to figure out how to spell it without the E. And now, let me leave you with some words of wisdom from Joscha Bach. If you take this as a computer game metaphor, this is the best level for humanity to play. And this best level happens to be the last level, as it happens against the backdrop of a dying world. But it's still the best level. Thank you for listening, and hope to see you next time. So, I mean, fundamentally, you were searching for the source of non-computable source of consciousness within the human brain, in the biology. And so, what are if I may ask, what are microtubules?
Well, you see, I was ignorant in what I'd read. I never came across them in the books I looked at. Perhaps I only read rather superficially, which is true. But I didn't know about microtubules. Stuart, I think one of the things that impressed him about them was when you see pictures of mitosis, that's a cell dividing, and you see all the chromosomes, and the chromosomes all get lined up, and then they get pulled apart. And so that as the cell divides, half the chromosomes go, they divide into the two parts, and they go two different ways. And what is it that's pulling them apart? Well, those are these little things called microtubules. And so he started to get interested in them. And he formed the view, well, had his day job or night job or whatever you call it, is to put people to sleep, except he doesn't like calling it sleep because it's different. General anesthetics in a reversible way. So you want to make sure that they don't experience the pain that would otherwise be something that they feel. And consciousness is turned off for a while, and it can be turned back on again. So it's crucial that you can turn it off and turn it on. And what do you do when you're doing that? What do general anesthetic gases do? And see, he formed the view that it's the microtubules that they affect. And the details of why he formed that view is not altogether clear to me, but there's an interesting story he keeps talking about. But I found this very exciting because I thought these structures, these little tubes, which inhabit pretty well all cells, it's not just neurons. Apart from red blood cells, they inhabit pretty well all the other cells in the body. But they're not all the same kind. You get different kinds of microtubules. And the ones that excited me the most, may still not be totally clear, but the ones that excited me most were the only ones that I knew about at the time, because they're very, very symmetrical structures. And I had reason to believe that these very symmetrical structures would be much better at preserving a quantum state, quantum coherence, preserving the thing without... You just need to preserve certain degrees of freedom without them leaking into the environment. Once they leak into the environment, you're lost. So you've got to preserve these quantum states at a level which the state reduction process comes in, and that's where I think the non-computability comes in. And it's the measurement process in quantum mechanics, what's going on.
So something about the measurement process and what's going on, something about the structure of the microtubules.
Yes.
Your intuition says maybe there's something here. Maybe this kind of structure allows for the mystery of the.
There was a much better
mechanics.
chance. Yes, it just struck me that partly it was the symmetry, because there is a feature of symmetry. You can preserve quantum coherence much better with symmetrical structures. There's a good reason for that. And that impressed me a lot. I didn't know the difference between the A lattice and B lattice at that time, which could be important. Now that could be, that's an issue which isn't talked about much.
But that's in some sense details. We've got to take a step back just to say, in case people are not familiar. So this was called the orchestrated objective reduction idea, or OR, which is a biological philosophy of mind that postulates that consciousness originates at the quantum level inside neurons. So that has to do with your search for where is it coming from. So that's counter to the notion that consciousness might arise from the computation performed by the synapses.
Yes, so, I think the key point, sometimes people say it's because it's quantum mechanical. It's not just that. See, it's more outrageous than that. You see, this is one reason I think we're so far off from it, because we don't even know the physics right. You see, it's not just quantum mechanics. People say, quantum systems and biological structures. No, well, you're starting to see that some basic biological systems does depend on quantum. I mean, look, in the first place, all of chemistry is quantum mechanics. But people got used to that, so they don't count that. So he said, let's not count quantum chemistry. We sort of got the hang of that, I think. But you have quantum effects, which are not just chemical, in photosynthesis. And this is one of the striking things in the last several years, that photosynthesis seems to be a basically quantum process, which is not simply chemical. It's using quantum mechanics in a very basic way. So you could start saying, with photosynthesis is based on quantum mechanics, why not behavior of neurons and things like that? Maybe there's something which is a bit like photosynthesis in that respect. But what I'm saying is even more outrageous than that, because those things are talking about conventional quantum mechanics. Now, my argument says that conventional quantum mechanics, if you're just following the Schrödinger equation, that's still computable. So you've got to go beyond that. So you've got to go to where quantum mechanics goes wrong in a certain sense. You have to be a little bit careful about that, because the way people do quantum mechanics is a sort of mixture of two different processes. One of them is the Schrödinger equation, which is an equation Schrödinger wrote down, and it tells you how the state of a system evolves. And it evolves according to this equation, completely deterministic, but it evolves into ridiculous situations. And this was what Schrödinger was very much pointing out with his cat. He said, you follow my equation, that's Schrodinger's equation, and you could say that you have to, a cat which is dead and alive at the same time. That would be the evolution of the Schrodinger equation would lead to a state, which is the cat being dead and alive at the same time. And he's more or less saying this is an absurdity. People nowadays say, oh, well, Schrodinger said you can have a cat which is dead and alive. It's not that, you see. He was saying this is an absurdity. There's something missing. And that the reduction of the state or the collapse of the wave function or whatever it is something which has to be understood. It's not following the Schrodinger equation. It's not the way we conventionally do quantum mechanics. There's something more than that. And it's easy to quote authority here because Einstein, at least 3 of the greatest physicists of 20th century who were very fundamental in developing quantum mechanics, Einstein, one of them, Schrodinger, another, Dirac, another. You have to look carefully at Dirac's writing because he didn't tend to say this out loud very much because he was very cautious about what he said. You find the right place and you see he says quantum mechanics is a provisional theory. We need something which explains the collapse of the wave function. We need to go beyond the theory we have now. I happen to be one of the kinds of people, there's a whole group of people, they're all considered to be a bit mavericks, who believe that quantum mechanics needs to be modified. There's a small minority of those people, which are already a minority, who think that the way in which it's modified has to be with gravity. And there is an even smaller minority of those people who think it's the particular way that I think it is, you see. So
those are the quantum gravity folks. But what's...
You see, quantum gravity is already not this. Because when you say quantum gravity, what you really mean is quantum mechanics applied to gravitational theory. So you say, let's take this wonderful formalism of quantum mechanics and make gravity fit into it. So that is what quantum gravity is meant to be. Now I'm saying you've got to be more even-handed, that gravity affects the structure of quantum mechanics too. It's not just you quantize gravity. You've got to gravitize quantum mechanics. And it's a two-way thing.
But then when do you even get started? So that you're saying that we have to figure out a totally new ideas in there.
Exactly. No, you're stuck. You don't have a theory. That's the trouble. So this is a big problem. If you say, okay, well, what's the theory? I don't know.
So we may be in the very early days, sort of.
It is in the very early days. But I'm just making this point.
Yes.
You see, Stuart Hameroff tends to be, Penrose says that it's got to be a reduction of the state and so on, so let's use it. The trouble is Penrose doesn't say that. Penrose says, well, I think that. But
Yeah, right.
we have no experiments as yet which show it's that.
Yes.
There are experiments which are being thought through and which I'm hoping will be performed. There is an experiment which is being developed by Dirk Bouwmeester, who I've known for a long time, who shares his time between Leiden in the Netherlands and Santa Barbara in the US. And he's been working on an experiment which could perhaps demonstrate that quantum mechanics, as we now understand it, if you don't bring in the gravitational effects, has to be modified.
And then there's also experiments that are underway that kind of look at the microtubule side of things to see if there's, in the biology, you could see something like that. Could you briefly mention it? Because that's a really sort of one of the only experimental attempts in the very early days of even thinking about consciousness.
I think there's a very serious area here, which is what Stuart Hameroff is doing, and I think it's very important. One of the few places that you can really get a bit of a handle on what consciousness is what turns it off. And when you're thinking about general anesthetics, it's very specific. These things turn consciousness off. What the hell do they do? Right. Well, Stuart and a number of people who work with him and others happen to believe that the general anesthetics directly affect microtubules. And there is some evidence for this. I don't know how strong it is and how watertight the case is, but I think there is some evidence pointing in that kind of direction. It's not just an ordinary chemical process. There's something quite different about it. And one of the main candidates is that these anesthetic gases do affect directly microtubules. And how strong that evidence is, I wouldn't be in a position to say. But I think there is fairly impressive evidence.
And the point is the experiments are being undertaken, which is...
I mean, that is experimental. You see, so it's a very clear direction where you can think of experiments which could indicate whether or not it's really microtubules which the anesthetic gases directly affect.
That's really exciting. One of the sad things is, as far as from my outside perspective, is not many people are working on this. So there's a very, like with Stewart, even it feels like there's very few people are carrying the flag forward on this.
I think it's not many in the sense it's a minority, but it's not zero anymore. You see, when Stewart and I were originally talking about this, we were just us and a few of our friends. There weren't many people taking it, but it's grown into one of the main viewpoints. There might be about 4 or 5 or 6 different views which people hold, and it's one of them. So it's considered as one of the possible lines of thinking, yes.
You describe physics theories as falling into one of 3 categories: the superb, the useful, or the tentative. I like those words. It's a beautiful categorization. Do you think we will ever have a superb theory of intelligence and of consciousness?
We might. We're a long way from it. I don't think we're even whether we're in the tentative scale. I mean, it's...
you don't think we've even entered the realm of tentative?
Probably no. I think.
Yeah, that's right.
Yes. No, well, you see, it's so controversial. We don't have a clear view which is accepted by a majority. I mean, you see, people. Most views are computational in one form or another. They think it's but it's not very clear, because even the IIT people who think of them as computational, but I've heard them say no, consciousness is supposed to be not computational. I say, well, if it's not computational, what the hell is it? What's going on? What physical processes are going on which are that?
What does it mean for something to be computational then? So is
well, there has to be a process which is, you see, it's very curious the way the history has developed in quantum mechanics, because very early on people thought there was something to do with consciousness, but it was almost the other way around. You see, you have to say the Schrödinger equation says all these different alternatives happen all at once, and then when is it that only one of them happens? Well, one of the views, which was quite commonly held by a few distinguished quantum physicists, that's when a conscious being looks at the system or becomes aware of it, and at that point it becomes one or the other. That's a role where consciousness is somehow actively reducing the state. My view is almost the exact opposite of that. It's just the state reduces itself in some way, some non-computational way, which we don't understand, we don't have a proper theory of, and that is the building block of what consciousness is. So consciousness is the other way around. It depends on that choice which nature makes all the time, when the state becomes one or the other rather than the superposition of one and the other. And when that happens, there is what we're saying now, an element of proto-consciousness takes place. Proto-consciousness is, roughly speaking, the building block out of which actual consciousness is constructed. So you have these proto-conscious elements, which are when the state decides to do one thing or the other. And that's the thing which, when organized together, that's the OR part in OR. But the ORC part, that's the OR part, at least one can see where one's driving at a theory. You can say it's the quantum choice of going this way or that way. But the ORC part, which is the orchestration of this, is much more mysterious. And how does the brain somehow orchestrate all these individual OR processes into a genuine conscious experience?
And it might be something that's beautifully simple, but we're completely in the dark about.
Yeah, I think at the moment that's the thing. We happily put the word "orc" down there to say orchestrated, but that's even more unclear what that really means.
Just like the word material, orchestrated.
Yes,
Who knows?
Materialism, yes.
And we've been dancing a little bit between the word intelligence or understanding and consciousness. Do you
Yes.
kind of see those as sitting
Yeah.
in the same space of mystery as we've
Yes,
been
but you
discussing?
see, I tend to say you have understanding and intelligence and awareness. And somehow understanding is in the middle of it, you see. I like to say, could you say of an entity that is actually intelligent if it doesn't have the quality of understanding? Right, so I'm using terms I don't even know how to define. Right. But who cares? I'm just relating them.
They're somewhat poetic. So if I somehow understand them.
Yes. That's right. We don't exactly.
But they're not mathematical in nature.
Yes. You see, as a mathematician, I don't know how to define any of them, but at least I can point to the connections. So the idea is intelligence is something which I believe needs understanding. Otherwise, you wouldn't say it's really intelligence. And understanding needs awareness. Otherwise, you wouldn't really say it's understanding. Do you say of an entity that understands something, unless it's really aware of it, in our normal usage? So there's a three sort of awareness, understanding, and intelligence. And I just tend to concentrate on understanding because that's where I can say something. Yeah. And that's the Gödel theorem and things like that. But what does it mean to perceive the color blue or something? I mean, I'm the foggiest. That's a much more difficult question. I mean, is it the same if I see a color blue and you see it? Or if you're somebody with this condition, what is it called?
Or where you assign like a sound to a color.
Yeah, that's right. You get colors and sounds mixed up, and that sort of thing. I mean, an interesting subject. I mean, yeah.
But from the physics perspective, from the fundamentals perspective, we don't.
I think we're way off having much understanding what's going on there.
On the biological neural network side, the process of learning versus the process of inference. Maybe you can explain to me what is there a difference between, in artificial neural networks, there's a difference between the learning stage and the inference stage.
Yeah.
Do you see the brain as something different? One of the big distinctions that people often say, I don't know how correct it is artificial neural networks need a lot of data. They're very inefficient learning.
Yeah.
Do you see that as a correct distinction from the biology of the human brain, that the human brain is very efficient, or is that just something we deceive ourselves with?
No, it is efficient. Obviously, we can learn new things almost instantly.
And so what elements do you think?
Yeah, I can talk about that. You brought up two issues there. So remember I talked earlier about the constraints we always feel. Well, one of those constraints is the fact that brains are continually learning. That's not something we said, we can add that later. That's something that was upfront, had to be there from the start, made our problems harder. But we showed, going back to the 2016 paper on sequence memory, we showed how that happens, how do brains infer and learn at the same time. And our models do that. They're not two separate phases or two separate sets of time. I think that's a big, big problem in AI, at least for many applications, not for all. So I can talk about that. There are some, it gets detailed. There are some parts of the neocortex in the brain where actually what's going on, there's these cycles, they're like cycles of activity in the brain. And there's very strong evidence that you're doing more of inference on one part of the phase and more of learning on the other part of the phase. So the brain can actually sort of separate different populations of cells are going back and forth like this. But in general, I would say that's an important problem. We have, all of our networks that we've come up with do both. And they're continuous learning networks. And you mentioned benchmarks earlier. Well, there are no benchmarks about that.
Exactly.
So we have to we get in our little soapbox and say, hey, by the way, this is important, and here's a mechanism for doing that. But until you can prove it to someone in some, commercial system or something, it's a little harder.
So one of the things, sorry to linger on that, is in some ways to learn the concept of a coffee cup, you only need this one coffee cup and maybe some time alone in a room with it.
Well, no, the first thing is, imagine I reach my hand into a black box and I'm trying to touch something.
Yeah.
I don't know up front if it's something I already know or if it's a new thing.
Right.
And I'm doing both at the same time. I don't say, let's see if it's a new thing. Let's see if it's an old thing. I don't do that. As I go, my brain says, it's new or it's not new. And if it's new, I start learning what it is. So, by the way, it starts learning from the get-go, even if it's going to recognize it. So they're not separate problems. And so that's the thing there. The other thing you mentioned was the fast learning. So I was just talking about continuous learning, but there's also fast learning. Literally, I can show you this coffee cup, and I say, here's a new coffee cup. It's got the logo on it. Take a look at it. Done. You're done. You can predict what it's going to look like, in different positions. So I can talk about that too.
Yes.
In the brain, the way learning occurs, I mentioned this earlier, but I'll mention it again. The way learning occurs, imagine I have a section of a dendrite of a neuron. And I'm going to learn something new. Doesn't matter what it is. I'm just going to learn something new. I need to recognize a new pattern. So what I'm going to do is I'm going to form new synapses. New synapses, we're going to rewire the brain onto that section of the dendrite. Once I've done that, everything else that neuron has learned is not affected by it. Now, it's because it's isolated to that small section of the dendrite. They're not all being added together like a point neuron. So if I learn something new on this segment here, it doesn't change any of the learning that occur anywhere else in that neuron. So I can add something without affecting previous learning. And I can do it quickly. Now we can talk about the quickness, how it's done in real neurons. You might say, well, doesn't it take time to form synapses? Yes, it can take maybe an hour to form a new synapse. We can form memories quicker than that, and I can explain that how it happens too, if you want. But it's getting a bit neuroscience-y.
That's great, but is there an understanding of these mechanisms at every level?
Yeah.
So from the short-term memories and the forming new connections.
So this idea of synaptogenesis, the growth of new synapses, that's well described, is well understood.
And that's an essential part of learning.
That is learning.
That is
it's learning. Okay. Going back many years, people, was what's his name, the psychologist who proposed Donald Hebb. He proposed that learning was the modification of the strength of a connection between two neurons. People interpreted that as the modification of the strength of a synapse. He didn't say that. He just said there's a modification between the effect of one neuron and another neuron. So synaptogenesis is totally consistent with what Donald Hebb said. But anyway, there's these mechanisms, the growth of new synapses. You can go online, you can watch a video of a synapse growing in real time. It's literally, you can see this little thing going, boop, right? It's pretty impressive. Yeah. So those mechanisms are known. Now, there's another thing that we've speculated and we've written about, which is consistent with known neuroscience, but it's less proven. And this is the idea, how do I form a memory really, really quickly? Like instantaneously. If it takes an hour to grow a synapse, that's not instantaneous. So there are types of synapses called silent synapses. They look like a synapse, but they don't do anything. They're just sitting there. It's like if an action potential comes in, it doesn't release any neurotransmitter. Some parts of the brain have more of these than others. For example, the hippocampus has a lot of them, which is where we associate most short-term memory with. So what we speculated, again in that 2016 paper, we proposed that the way we form very quick memories, very short-term memories, or quick memories, is that we convert silent synapses into active synapses. It's like saying a synapse has a 0 weight and a 1 weight. But the long-term memory has to be formed by synaptogenesis. So you can remember something really quickly by just flipping a bunch of these guys from silent to active. It's not from 0.1 to 0.15. It's like doesn't do anything till it releases transmitter. And if I do that over a bunch of these, I've got a very quick short-term memory. So I guess the lesson behind this is that most neural networks today are fully connected. Every neuron connects every other neuron from layer to layer. That's not correct in the brain. We don't want that. We actually don't want that. It's bad. You want a very sparse connectivity so that any neuron connects to some subset of the neurons in the other layer, and it does so on a dendrite by dendrite segment basis. So it's a very parcellated out type of thing. And that then learning is not adjusting all these weights, but learning is just saying, okay, connect to these 10 cells here right now.
In that process, with artificial neural networks, so then let's get into it for people like myself who are not very well versed in the human brain, except my own. Can you describe to me at the highest level what are the different parts of the human brain, and then zooming in on the neocortex, the parts of the neocortex, and so on? A quick overview.
Yeah, sure. The human brain, we can divide it roughly into two parts. There's the old parts lots of pieces, and then there's a new part. The new part is the neocortex. It's new because it didn't exist before mammals. Only mammals have a neocortex, and in humans, in primates, it's very large. In the human brain, the neocortex occupies about 70 to 75% of the volume of the brain. It's huge. And the old parts of the brain are there's lots of pieces there. There's a spinal cord, and there's the brain stem, and the cerebellum, and the different parts of the basal ganglia, and so on. In the old parts of the brain, you have the autonomic regulation, like breathing and heart rate. You have basic behaviors. So like walking and running are controlled by the old parts of the brain. All the emotional centers of the brain are in the old part of the brain. So when you feel anger or hungry, lust, or things like that, those are all in the old parts of the brain. And we associate with the neocortex all the things we think about as sort of high-level perception and cognitive functions, anything from seeing and hearing and touching things to language to mathematics and engineering and science and so on. Those are all associated with the neocortex, and they're certainly correlated. Our abilities in those regards are correlated with the relative size of our neocortex compared to other mammals. So that's like the rough division. And you obviously can't understand the neocortex completely isolated, but you can understand a lot of it with just a few interfaces to the old parts of the brain. And so it gives you a system to study. The other remarkable thing about the neocortex, compared to the old parts of the brain, is the neocortex is extremely uniform. It's not visually or anatomically or it's like I always like to say it's like the size of a dinner napkin, about 2.5 millimeters thick. And it looks remarkably the same everywhere. Everywhere you look in that 2.5 millimeters is this detailed architecture, and it looks remarkably the same everywhere. And that's across species, a mouse versus a cat and a dog and a human. Where if you look at the old parts of the brain, there's lots of little pieces that do specific things. So it's like the old parts of the brain evolved, like this is the part that controls heart rate, and this is the part that controls this, and this is this kind of thing, and that's this kind of thing. And these evolved for eons, a long, long time, and they have their specific functions. And all of a sudden, mammals come along, and they got this thing called the neocortex, and it got large by just replicating the same thing over and over and over again. This is like, wow, this is incredible. So all the evidence we have, and this is an idea that was first articulated in a very cogent and beautiful argument by a guy named Vernon Mountcastle in 1978, I think it was, that the neocortex all works on the same principle. So language, hearing, touch, vision, engineering, all these things are basically underlying, are all built on the same computational substrate. They're really all the same problem.
So at the low level, the building blocks all look similar.
Yeah, and they're not even that low level. We're not talking about like neurons. We're talking about this very complex circuit that exists throughout the neocortex is remarkably similar. It's like, yes, you see variations of it here and there, more of this cell, left and left, and so on. But what Mountcastle argued was, it says, if you take a section of neocortex, why is one a visual area and one is a auditory area? And his answer was, it's because one is connected to eyes and one is connected to ears.
Literally, you mean just it's most closest in terms of number of connections to the sensor.
Literally, if you took the optic nerve and attached it to a different part of the neocortex, that part would become a visual region. This experiment was actually done by Morganka Sur.
Oh boy!
in developing, I think it was lemurs. I can't remember what it was, some animal. And there's a lot of evidence to this. If you take a blind person, a person is born blind at birth, they're born with a visual neocortex. It may not get any input from the eyes because of some congenital defect or something. And that region does something else. It picks up another task. So, it's this very complex thing. It's not like, oh, they're all built on neurons. No, they're all built in this very complex circuit, and somehow that circuit underlies everything. And so this is it's called the common cortical algorithm, if you will. Some scientists just find it hard to believe, and they just say, I can't believe that's true, but the evidence is overwhelming in this case. And so a large part of what it means to figure out how the brain creates intelligence and what is intelligence in the brain is to understand what that circuit does. If you can figure out what that circuit does,
The new, as you've mentioned, this idea, I don't know if you have a nice name,
We call it the 1,000 brain theory of intelligence.
I like it. So can you talk about this idea of spatial view of concepts and so on?
So can I just describe sort of there's an underlying core discovery, which then everything comes from that. There's a very simple, this is really what happened. We were deep into problems about understanding how we build models of stuff in the world and how we make predictions about things. And I was holding a coffee cup just like this in my hand. And my finger was touching the side, my index finger. And then I moved it to the top, and I was going to feel the rim at the top of the cup. And I asked myself a very simple question. I said, well, first of all, let's say I know that my brain predicts what it's going to feel before it touches it. You can just think about it and imagine it. And so we know that the brain's making predictions all the time. So the question is, what does it take to predict that, right? And there's a very interesting answer. First of all, it says the brain has to know it's touching a coffee cup. It has to have a model of a coffee cup. It needs to know where the finger currently is on the cup relative to the cup. Because when I make a movement, it needs to know where it's going to be on the cup after the movement is completed relative to the cup. And then it can make a prediction about what it's going to sense. So this told me that the neocortex, which is making this prediction, needs to know that it's sensing it's touching a cup, and it needs to know the location of my finger relative to that cup in a reference frame of the cup. It doesn't matter where the cup is relative to my body. It doesn't matter its orientation. None of that matters. It's where my finger is relative to the cup, which tells me then that the neocortex has a reference frame that's anchored to the cup, because otherwise I wouldn't be able to say the location, and I wouldn't be able to predict my new location. And then we quickly, very instantly, you can say, well, every part of my skin could touch this cup, and therefore every part of my skin is making predictions, and every part of my skin must have a reference frame that it's using to make predictions. So the big idea is that throughout the neocortex, everything is being stored and referenced in reference frames. You can think of them like XYZ reference frames, but they're not like that. We know a lot about the neural mechanisms for this, but the brain thinks in reference frames. And as an engineer, if you're an engineer, this is not surprising. You'd say, if I wanted to build a CAD model of the coffee cup, well, I would bring it up in some CAD software, and I would assign some reference frame and say this features at this locations and so on. But the fact that the idea that this is occurring throughout the neocortex everywhere, it was a novel idea. And then a zillion things fell into place after that, a zillion. So now we think about the neocortex as processing information quite differently than we used to do it. We used to think about the neocortex as processing sensory data and extracting features from that sensory data and then extracting features from the features, very much like a deep learning network does today. Yeah. But that's not how the brain works at all. The brain works by assigning everything, every input, everything to reference frames. And there are thousands, hundreds of thousands of them active at once in your neocortex. It's a surprising thing to think about, but once you sort of internalize this, you understand that it explains almost all the mysteries we've had about this structure. So one of the consequences of that is that every small part of the neocortex, say a millimeter square, and there's 150,000 of those, so it's about 150,000 square millimeters. If you take every little square millimeter of the cortex, it's got some input coming into it, and it's going to have reference frames where it's assigning that input to. And each square millimeter can learn complete models of objects. So what do I mean by that? If I'm touching the coffee cup, well, if I just touch it in one place, I can't learn what this coffee cup is because I'm just feeling one part. But if I move it around the cup and touch it at different areas, I can build up a complete model of the cup because I'm now filling in that three-dimensional map, which is the coffee cup. I can say, oh, what am I feeling at all these different locations? That's the basic idea. It's more complicated than that. So through time, and we talked about time earlier, through time, even a single column, which is only looking at, or a single part of the cortex, which is only looking at a small part of the world, can build up a complete model of an object. And so if you think about the part of the brain which is getting input from all my fingers, so they're spread across the top of your head here. This is the somatosensory cortex. There's columns associated with all the different areas of my skin. And what we believe is happening is that all of them are building models of this cup, every one of them. Or things. They're not all building, not every column or every part of the cortex builds models of everything, but they're all building models of something. And so you have, so when I touch this cup with my hand, There are multiple models of the cup being invoked. If I look at it with my eyes, there are again many models of the cup being invoked because each part of the visual system, the brain doesn't process an image. That's a misleading idea. It's just like your fingers touching the cup. So different parts of my retina are looking at different parts of the cup. And thousands and thousands of models of the cup are being invoked at once. And they're all voting with each other, trying to figure out what's going on. So that's why we call it the thousand brains theory of intelligence, because there isn't one model of a cup. There are thousands of models of this cup. There are thousands of models of your cell phone and about cameras and microphones and so on. It's a distributed modeling system, which is very different than the way people have thought about it.
So that's a really in what part can you actually relax and just be Jeff?
Me personally, like my personal day?
Yeah.
Unfortunately, I'm afflicted with too much of the former. I
well,
think,
unfortunately or unfortunately. Okay.
Yeah. So
you don't think it's useful?
Oh, it is useful. Totally useful. I think about this stuff almost all the time. And I'm at, one of my primary ways of thinking is when I'm in sleep at night, I always wake up in the middle of the night. And then I stay awake for at least an hour with my eyes shut in sort of a half sleep state, thinking about these things. I come up with answers to problems very often in that sort of half sleeping state. I think about it on my bike ride. I think about it on walks. I'm just constantly thinking about this. I have to almost schedule time to not think about this stuff because it's mentally taxing.
Are you, when you're thinking about this stuff, are you thinking introspectively, like almost taking a step outside of yourself and trying to figure out what is your mind doing right now?
I do that all the time, but that's not all I do. I'm constantly observing myself. So as soon as I started thinking about grid cells, for example, and getting into that, I started saying, oh, well, grid cells have my place of sense in the world. That's where you know where you are. And it's interesting, we always have a sense of where we are unless we're lost. And so I started at night when I got up to go to the bathroom, I would start trying to do it complete with my eyes closed all the time. And I would test my sense of grid cells. I would walk, 5 feet and say, okay, I think I'm here. Am I really there? What's my error?
Yeah.
And then I would calculate my error again and see how the errors accumulate. So even something as simple as getting up in the middle of the night to go to the bathroom, I'm testing these theories out. It's kind of fun. I mean, the coffee cup is an example of that too. So I think I find that these sort of everyday introspections are actually quite helpful. It doesn't mean you can ignore the science. I mean, I spend hours every day reading ridiculously complex papers. That's not nearly as much fun, but you have to sort of build up those constraints and the knowledge about the field and who's doing what and what exactly they think is happening here. And then you can sit back and say, okay, let's try to piece this all together. Let's come up with some, I'm very, in this group here, people, they know I do this all the time. I come in with these introspective ideas and say, well, have you ever thought about this? Now watch, well, let's all do this together.
Yeah.
And it's helpful. It's not, as long as you just, if all you did was that, then you're just making up stuff, right? But if you're constraining it by the reality of the neuroscience, then it's really helpful.
So let's talk a little bit about understanding the human brain or in creating artificial systems that have many of the same qualities, but don't necessarily require that you actually understand the underpinning workings of our mind.
So there's a clear answer to that question. My primary interest is understanding the human brain. No question about it. But I also firmly believe that we will not be able to create fully intelligent machines until we understand how the human brain works. So I don't see those as separate problems. I think there's limits to what can be done with machine intelligence if you don't understand the principles by which the brain works. And so I actually believe that studying the brain is actually the fastest way to get to machine intelligence.
And within that, let me ask the impossible question. How do you not define, but at least think about what it means to be intelligent?
So I didn't try to answer that question first. We said, let's just talk about how the brain works and let's figure out how certain parts of the brain, mostly the neocortex, but some other parts too, the parts of the brain most associated with intelligence. And let's discover the principles by how they work. Because intelligence isn't just like some mechanism and it's not just some capabilities. It's like, okay, we don't even know where to begin on this stuff. And so now that we've made a lot of progress on this, after we've made a lot of progress on how the neocortex works, and we can talk about that, I now have a very good idea what's going to be required to make intelligent machines. I can tell you today, some of the things are going to be necessary, I believe, to create intelligent machines.
Well, so we'll get there. We'll get to the neocortex and some of the theories of how the whole thing works. And you're saying as we understand more and more about the neocortex, about our own human mind, we'll be able to start to more specifically define what it means to be intelligent. It's not useful to really talk about that until.
I don't know if it's not useful. Look, there's a long history of AI, as you know.
Right.
And there's been different approaches taken to it. And who knows, maybe they're all useful. Right. So, the good old-fashioned AI, the expert systems, the current convolutional neural networks, they all have their utility. They all have a value in the world. But I would think almost everyone agree that none of them are really intelligent in a sort of a deep way that humans are. And so it's just the question of how do you get from where those systems were or are today to where a lot of people think we're going to go.
Right.
And there's a big gap there, a huge gap. And I think the quickest way of bridging that gap is to figure out how the brain does that. And then we can sit back and look and say, oh, which of these principles that the brain works on are necessary and which ones are not?
Right.
Clearly, we don't have to build this in intelligent machines aren't going to be built out of, organic living cells. But there's a lot of stuff that goes on in the brain that's going to be necessary.
So let me ask maybe, before we get into the fun details, let me ask maybe a depressing or a difficult question. Do you think it's possible that we will never be able to understand how our brain works? That maybe there's aspects to the human mind, like we ourselves cannot introspectively get to the core, that there's a wall you eventually hit?
Yeah. I don't believe that's the case. I have never believed that's the case. There's not been a single thing humans have ever put their minds to that we've said, oh, we reached the wall, we can't go any further. It's just, people keep saying that. People used to believe that about life, elan vital, right? There's like, what's the difference between living matter and non-living matter? Something special we never understand. We no longer think that. So there's no historical evidence to suggest this is the case, and I just never even consider that's a possibility. I would also say today, we understand so much about the neocortex. We've made tremendous progress in the last few years that I no longer think of it as an open question. The answers are very clear to me. And the pieces we don't know are clear to me, but the framework is all there. And it's like, oh, okay, we're going to be able to do this. This is not a problem anymore. It just takes time and effort, but there's no mystery, big mystery anymore.
So let's take a step back to HTM, the hierarchical temporal memory theory, which you first proposed on intelligence and went through a few different generations. Can you describe what it is, how it evolved through the 3 generations since you first put it on paper?
Yeah, so one of the things that neuroscientists just sort of missed for many, many years, and especially people who were thinking about theory, was the nature of time in the brain. Brains process information through time. The information coming into the brain is constantly changing. The patterns from my speech right now, if you're listening to it at normal speed, would be changing on your ears about every 10 milliseconds or so. You'd have a change. This constant flow. When you look at the world, your eyes are moving constantly, 3 to 5 times a second, and the input's completely. If I were to touch something like a coffee cup, as I move my fingers, the input changes. So this idea that the brain works on time-changing patterns is almost completely, or was almost completely missing from a lot of the basic theories, like theories of vision and so on. It's like, oh no, we're going to put this image in front of you and flash it and say, what is it?
Right.
Convolutional neural networks work that way today, right? Classify this picture. But that's not what vision is like. Vision is this sort of crazy time-based pattern that's going all over the place, and so is touch, and so is hearing. So the first part of hierarchical temporal memory was the temporal part. Right. It's to say, you won't understand the brain, nor will you understand intelligent machines unless you're dealing with time-based patterns. The second thing was, the memory component of it is to say that we aren't just processing input. We learn a model of the world. And the memory stands for that model. We have to, the point of the brain, the point of the neocortex, it learns a model of the world. We have to store things that our experiences in a form that leads to a model of the world. So we can move around the world, we can pick things up and do things and navigate and know how it's going on. So that's what the memory referred to. And many people they were thinking about like certain processes without memory at all. They're just like processing things. And then finally, the hierarchical component was a reflection to that the neocortex, although it's this uniform sheet of cells, the different parts of it project to other parts, which project to other parts. And there is a sort of a rough hierarchy in terms of that. So the hierarchical temporal memory is just saying, look, we should be thinking about the brain as time-based, model memory based and hierarchical processing, and that was a placeholder for a bunch of components that we would then plug into that. We still believe all those things I just said, but we now know so much more that I'm stopping to use the word hierarchical temporal memory yet because it's insufficient to capture the stuff we know. So again, it's not incorrect, but I now know more, and I would rather describe it more accurately.
Yeah, so you're basically, we could think of HTM as emphasizing that there's three aspects of intelligence that are important to think about, whatever the eventual theory converges to.
Yeah.
So in terms of time, how do you think of the nature of time across different time scales? So you mentioned things changing, sensory inputs changing every 10, 20 minutes. Like, what about every few minutes, every few months and years?
Well, if you think about a neuroscience problem, the brain problem, neurons themselves can stay active for certain periods of time. There are parts of the brain where they stay active for minutes. So you could hold a certain perception or an activity for a certain period of time, but most of them don't last that long. And so if you think about your thoughts are the activity of neurons, if you're going to want to involve something that happened a long time ago, even just this morning, for example, the neurons haven't been active throughout that time. So you have to store that. So if I ask you, what did you have for breakfast today? That is memory. That is, you've built it into your model of the world now. You remember that. And that memory is in the synapses, is basically in the formation of synapses. And so you're sliding into what, you said different time scales. There's time scales of which we are like understanding my language and moving about and seeing things rapidly and over time. That's the time scales of activities of neurons. But if you want to get in longer time scales, then it's more memory. And we have to invoke those memories to say, oh, yes, well, now I can remember what I had for breakfast because I stored that someplace. I may forget it tomorrow, but it's stored for now.
So does memory also need to have, so the hierarchical aspect of reality is not just about concepts, it's also about time? Do you think of it that way?
Yeah, time is infused in everything. It's like you really can't separate it out. If I ask you, what is your, how's the brain learn a model of this coffee cup here? I have a coffee cup, then I'm at the coffee cup. I say, well, time is not an inherent property of the model I have of this cup, whether it's a visual model or a tactile model. I can sense it through time, but the model itself doesn't really have much time. If I say, well, what is the model of my cell phone? My brain has learned a model of a cell phone. So if you have a smartphone like this, and I said, well, this has time aspects to it. I have expectations when I turn it on, what's going to happen, how long it's going to take to do certain things. If I bring up an app, what sequences. And so I have it's like melodies in the world. Melody has a sense of time. So many things in the world move and act, and there's a sense of time related to them. Some don't, but most things do actually. So it's sort of infused throughout the models of the world. You build a model of the world, you're learning the structure of the objects in the world, and you're also learning how those things change through time.
Okay, so so how deep do the roots of language go in our brain? Well, our mind? Is it yet another feature like vision, or is it something more fundamental from which everything else springs in the human mind?
Well, in a way, it's like vision. There's something about our genetic endowment that determines that we have a mammalian rather than an insect visual system. And there's something in our genetic endowment that determines that we have a human language faculty. No other organism has anything remotely similar. So in that sense, it's internal. Now, there is a long tradition, which I think is valid, going back centuries to the early scientific revolution, at least, that holds that language is the sort of the core of human cognitive nature. It's the source, it's the mode for constructing thoughts and expressing them, and that is what forms thought. And it's got fundamental creative capacities. It's free, independent, unbounded, and so on. And undoubtedly, I think the basis for our creative capacities and the other remarkable human capacities that lead to the unique achievements and not so great achievements of the species.
There's, not sure if you're familiar with the entire field of brain-computer interfaces that's become more and more intensely researched and developed recently, especially with companies like Neuralink with Elon Musk.
Yeah, I know there have always been the interest both in things like getting the eyes to be able to control things, or getting the thought patterns to be able to move what had been a connected limb, which is now connected through a computer.
That's right. So in the case of Neuralink, they're doing 1,000+ connections where they're able to do two-way, activate and read spikes, neural spikes. Do you have hope for that kind of computer-brain interaction in the near or maybe even far future, of being able to expand the ability of the mind of cognition or understand the mind?
It's interesting watching things go. When I first became interested in neurobiology, most of the practitioners thought you would be able to understand neurobiology by techniques which allowed you to record only one cell at a time.
One cell, yeah.
People like David Hubel very strongly reflected that point of view. And that's been taken over by a generation, a couple of generations later, by a set of people who says, not until we can record from 10 to the 4 or 10 to the 5 at a time will we actually be able to understand how the brain actually works. And in a general sense, I think that's right. You have to begin to be able to look for the collective modes, the collective operations of things. It doesn't rely on this action potential or that cell. It relies on the collective properties of this set of cells connected with this kind of patterns and so on. And you're not going to succeed in seeing what those collective activities are without recording many cells at once.
The question is how many at once? What's the threshold? And that's the
yeah. And look, it's being pursued hard in the motor cortex. The motor cortex does something which is complex, and yet the problem you're trying to address is fairly simple. Now, neurobiology does it in ways that differ from the way an engineer would do it. An engineer would put in 6 highly accurate stepping motors controlling a limb, right, rather than 100,000 muscle fibers, each of which has to be individually controlled. And so understanding how to do things in a way which is much more forgiving and much more neural, I think would benefit the engineering world. The engineering world, touch. Let's put in a pressure sensor or two, rather than an array of a gazillion pressure sensors, none of which are accurate, all of which are perpetually recalibrating themselves.
So you're saying your hope is, your advice for the engineers of the future is to embrace the large chaos of a messy, error-prone system like those of the biological systems. Like that's probably the way to solve some of these.
I think you'll be able to make better computation/robotics that way than by trying to force things into a robotics where joint motors are powerful and stepping motors are accurate.
But then the physicist in you will be lost forever in such systems, because there's no simple fundamentals to explore in systems that are so large and messy.
Well, you say that, and yet there's a lot of physics in the Navier-Stokes equations, the equations of nonlinear hydrodynamics. Huge amount of physics in them. All of the physics of atoms and molecules has been lost, but it's been replaced by this other set of equations, which is just as true as the equations at the bottom. Yeah. Now, those equations are going to be harder to find in neurobiology. But the physicist in me says there are probably some equations of that sort.
They're out there.
They're out there. And if physics is going to contribute anything, it may contribute to trying to find out what those equations are and how to capture them from the biology.
Would you say that's one of the main open problems of our age, is to discover those equations?
Yeah. If you look at, there's molecules and there's psychological behavior.
Mm-hmm.
And these two are somehow related. They're layers of detail, they're layers of collectiveness, and to capture that in some vague way, several stages on the way up to see how these things can actually be linked together.
So it seems in our universe, there's a lot of elegant equations that can describe the fundamental way that things behave, which is a surprise. I mean, it's compressible into equations. It's simple and beautiful, but there isn't. It's still an open question whether that link is equally between molecules and the brain is equally compressible into elegant equations. But your sense, well, you're both a physicist and a dreamer. You have a sense that
yeah, but I can only dream physics dreams.
Yeah, physics dreams.
There was an interesting book called Einstein's Dreams, which alternates between chapters on his life and descriptions of the way time might have been but isn't. As the linking between these being, of course, ideas that Einstein might have had to think about the essence of time as he was thinking about time.
So in your new book, you talk about our brain, our mind, as being made up of many brains. So the book is called A Thousand Brain Theory of Intelligence. What is the key idea of this book?
The book has 3 sections, and it has sort of maybe 3 big ideas. So the first section is all about what we've learned about the neocortex, and that's the thousand brains theory. Just to complete the picture, the second section is all about AI, and the third section is about the future of humanity. The thousand brains theory, the big idea there, if I had to summarize it into one big idea, is that we think of the brain, the neocortex, as learning this model of the world. But what we learned is actually there's tens of thousands of independent modeling systems going on. And so each, what we call a column in the cortex, there's about 150,000 of them, is a complete modeling system. So it's a collective intelligence in your head in some sense. Mm-hmm. So the thousand brains theory says, well, where do I have knowledge about, this coffee cup, or where's the model of this cell phone? It's not in one place. It's in thousands of separate models that are complementary, and they communicate with each other through voting. So this idea that we feel like we're one person, that's our experience. We can explain that. But reality, there's lots of these, it's almost like little brains, mm-hmm. But they're sophisticated modeling systems, about 150,000 of them in each of a human brain. And that's a totally different way of thinking about how the neocortex is structured than we or anyone else thought of even just 5 years ago.
So you mentioned you started this journey on just looking in the mirror and trying to understand who you are. So if you have many brains, who are you then?
So it's interesting. We have a singular perception, right? We think, oh, I'm just here, I'm looking at you. But it's composed of all these things. There's sounds and there's vision and there's touch and all kinds of inputs. Yet we have the singular perception. And what the thousand brains theory says, we have these models that are visual models. We have models that are auditory models that are tactile models, and so on. But they vote. Mm-hmm. And so in the cortex, you can think about these columns as about like little grains of rice, 150,000 of them stacked next to each other. And each one is its own little modeling system. But they have these long-range connections that go between them. Mm-hmm. And we call those voting connections or voting neurons. And so the different columns try to reach a consensus. Like, what am I looking at? Okay, each one has some ambiguity, but they come to a consensus. Oh, there's a water bottle I'm looking at. We are only consciously able to perceive the voting. Mm-hmm. We're not able to perceive anything that goes on under the hood. So the voting is what we're aware of.
The results of the voting.
Yeah, the voting. Well, it's you can imagine it this way. we were just talking about eye movements a moment ago. So as I'm looking at something, my eyes are moving about 3 times a second. And with each movement, a completely new input is coming into the brain. It's not repetitive. It's not shifting it around. It's completely new. I'm totally unaware of it. I can't perceive it. But yet, if I looked at the neurons in your brain, they're going on and off, on and off, on and off, on and off. But the voting neurons are not. The voting neurons are saying, we all agree, even though I'm looking at different parts of this is a water bottle right now. And that's not changing. And it's in some position and pose relative to me. So I have this perception of the water bottle about 2 feet away from me at a certain pose to me. That is not changing. That's the only part I'm aware of. I can't be aware of the fact that the inputs from the eyes are moving and changing and all this other stuff happening. So these long-range connections are the part we can be conscious of. The individual activity in each column doesn't go anywhere else. It doesn't get shared anywhere else. There's no way to extract it and talk about it or extract it and even remember it to say, oh, yes, I can recall that. But these long-range connections are the things that are accessible to language and to our, it's like the hippocampus, our memories, our short-term memory systems and so on. So we're not aware of 95% or maybe it's even 98% of what's going on in your brain. We're only aware of this sort of stable, somewhat stable voting outcome of all these things that are going on underneath the hood.
So what would you say is the basic element in the 1,000 brains theory of intelligence? Like, what's the atom of intelligence when you think about it? Is it the individual brains, and then what is a brain?
Well, can we just talk about what intelligence is first, and then we can talk about what the elements are. So in my book, intelligence is the ability to learn a model of the world, to build internal to your head a model that represents the structure of everything. To know what this is a table and that's a coffee cup and this is a gooseneck lamp and all this thing. To know these things, I have to have a model of them in my head. I just don't look at them and go, what is that? I already have internal representations of these things in my head, and I had to learn them. I wasn't born with any of that knowledge. We have some lights in the room here. That's not part of my evolutionary heritage, right? It's not in my genes. So we have this incredible model, and the model includes not only what things look like and feel like, but where they are relative to each other and how they behave. I've never picked up this water bottle before, but I know that if I took my hand on that blue thing and I turn it, it'll probably make a funny little sound as the little plastic things detach, and then it'll rotate a certain way and it'll come off. How do I know that? Right? Because I have this model in my head. So the essence of intelligence is our ability to learn a model. And the more sophisticated our model is, the smarter we are. Not that there is a single intelligence, because you know a lot about things that I don't know, and I know about things you don't know. And we can both be very smart. But we both learned a model of the world through interacting with it. So that is the essence of intelligence. Then we can ask ourselves, what are the mechanisms in the brain that allow us to do that? And what are the mechanisms of learning? Not just the neural mechanisms, what is the general process by how we learn a model? So that was a big insight for us. It's like, what is the actual things how do you learn this stuff? It turns out you have to learn it through movement. You can't learn it just that's how we learn. We learn through movement. We learn. So you build up this model by observing things and touching them and moving them and walking around the world and so on.
So either you move or the thing moves.
Somehow. Yeah. You can learn things just by reading a book, something like that. But think about if I were to say, oh, here's a new house. I want you to learn, what do? You have to walk from room to room. You have to open the doors, look around, see what's on the left, what's on the right. As you do this, you're building a model in your head. It's just, that's what you're doing. You can't just sit there and say, I'm going to grok the house. No, or you don't even want to just sit there and read some description of it, right?
Yeah.
You literally physically interact. And the same with like a smartphone. If I want to learn a new app, I touch it and I move things around and I see what happens when I do things with it. So that's the basic way we learn in the world.
And by the way, when you say model, you mean something that can be used for prediction in the future.
It's used for prediction and for behavior and planning.
Right. And does a pretty good job at doing so.
Yeah. Here's the way to think about a model. A lot of people get hung up on this. So you can imagine an architect making a model of a house, right? So there's a physical model that's small. And why do they do that? Well, we do that because you can imagine what it would look like from different angles. You can say, okay, look from here, look from there. And you can also say, well, how far to get from the garage to the swimming pool or something like that, right? You can imagine looking at this. You can say, what would be the view from this location? So we build these physical models to let you imagine the future and imagine behaviors. Now we can take that same model and put it in a computer. So today they'll build models of houses in a computer, and they do that using a set of we'll come back to this term in a moment, reference frames. But basically, you assign a reference frame for the house, and you assign different things for the house in different locations. And then the computer can generate an image and say, okay, this is what it looks like in this direction. The brain is doing something remarkably similar to this. Surprising. It's using reference frames. It's building these. It's similar to a model in a computer, which has the same benefits of building a physical model. It allows me to say, what would this thing look like if it was in this orientation? What would likely happen if I pushed this button? I've never pushed this button before. Or how would I accomplish something? I want to convey a new idea I've learned. How would I do that? I can imagine in my head, well, I could talk about it. I could write a book. I could do some podcasts. I could, maybe tell my neighbor, and I can imagine the outcomes of all these things before I do any of them. That's what the model lets you do. It lets us plan the future and imagine the consequences of our actions. Prediction, you asked about prediction. Prediction is not the goal of the model. Prediction is an inherent property of it, and it's how the model corrects itself.
So prediction is fundamental to intelligence.
It's fundamental to building a model, and the model's intelligent. And let me go back and be very precise about this. Prediction, you can think of prediction two ways. One is like, hey, what would happen if I did this? That's a type of prediction. That's a key part of intelligence. But even prediction is like, oh, what's this water bottle going to feel like when I pick it up? And that doesn't seem very intelligent. But one way to think about prediction is it's a way for us to learn where our model is wrong. So if I picked up this water bottle and it felt hot, I'd be very surprised. Or if I picked it up and it was very light, I'd be surprised. Or if I turned this top and I had to turn it the other way, I'd be surprised. Mm-hmm. And so all those, I have a prediction like, okay, I'm going to do it. I'll drink some water. Okay, I do this. There it is. I feel opening, right? What if I had to turn it the other way? Or what if it split in two? Then I say, oh my gosh, I misunderstood this. I didn't have the right model. This thing, my attention would be drawn to it. I'd be looking at it going, well, how the hell did that happen? Yeah. Why did it open up that way? And I would update my model by doing it. Just by looking at it and playing around with it, I'd update and say, this is a new type of water bottle.
But you're talking about sort of complicated things like a water bottle, but this also applies for just basic vision, just like seeing things. That's almost like a precondition of just perceiving the world is predicting it. Mm-hmm. So just everything that you see is first passed through your prediction.
Everything you see and feel. In fact, this is the insight I had back in the late 80s. Early 80s. And other people have reached the same idea, is that every sensory input you get, not just vision, but touch and hearing, you have an expectation about it. Yeah. And a prediction. Sometimes you can predict very accurately, sometimes you can't. Right? I can't predict what next word is going to come out of your mouth, but as you start talking, I'll get better and better predictions. Yeah. And if you talked about some topics, I'd be very surprised. So I have this sort of background prediction that's going on all the time for all of my senses. The way I think about that is this is how we learn. It's more about how we learn. It's a test of our understanding. Our predictions are a test of, is this really a water bottle? If it is, I shouldn't see, a little finger sticking out the side. Mm-hmm. And if I saw a little finger sticking out, I go, what the hell's going on? That's not normal.
That's fascinating. Let me linger on this for a second. It really honestly feels that prediction is fundamental to everything, to the way our mind operates, to intelligence. So like, it's just a different way to see intelligence, which is like everything starts at prediction.
And prediction requires a model. You can't predict something unless you have a model of it.
Right. But the action is prediction. So like the thing the model does is prediction.
But it also, but you can then extend it to things like, what would happen if I took this today? I went and did this. What would be the likely outcome? Or how you can extend prediction to like, I want to get a promotion at work. What action should I take? And you can say, if I did this, I predict what might happen. If I spoke to someone, I predict what might happen. So it's not just low-level predictions.
Yeah, it's all predictions.
It's all predictions.
It's like this black box that you can ask basically any question, low level or high level.
So we started off with that observation. It's like this nonstop prediction. And I write about this in the book and then we asked, well, how do neurons actually make predictions physically? Like, what does the neuron do when it makes a prediction? And, or the neural tissue does when it makes prediction. And then we asked, what are the mechanisms by how we build a model that allows you to make prediction? So we started with prediction as sort of the fundamental research agenda, if in some sense, and say, well, if we understand how the brain makes predictions, we'll understand how it builds these models and how it learns, and that's the core of intelligence. So it was like it was the key that got us in the door to say that is our research agenda. Understand predictions.
If you were to count the number of brains, how would you do it?
The thousand brain theory says that basically every cortical column in your neocortex is a complete modeling system. And that when I ask, where do I have a model of something like a coffee cup? It's not in one of those models. It's in thousands of those models. There's thousands of models of coffee cups. That's what the thousand brains theory
And then there's
says.
a voting mechanism.
Then there's a voting mechanism, which is the thing you're conscious of, which leads to your singular perception. That's why you perceive something. So that's the thousand brains theory. The details of how we got to that theory are complicated. It wasn't we just thought of it one day. And one of those details is we had to ask, how does a model make predictions? And we've talked about just these predictive neurons. That's part of this theory. It's like saying, oh, it's a detail, but it was like a crack in the door. It's like, how are we going to figure out how these neurons do this? What is going on here? So we just looked at prediction as like, well, we know that's ubiquitous. We know that every part of the cortex is making predictions. Therefore, whatever the predictive system is, it's going to be everywhere. We know there's a gazillion predictions happening at once. So let's see if we can start teasing apart, ask questions about, how could neurons be making these predictions? And that sort of built up to now what we have, this thousand brains theory, which is complex, it's just I can state it simply, but we just didn't think of it. We had to get there step by step. It took years to get there.
And where does reference frames fit in? So, yeah.
Okay. So again, a reference frame, I mentioned earlier about a model of a house. And I said, if you're going to build a model of a house in a computer, they have a reference frame. And you can think of reference frame like Cartesian coordinates, like X, Y, and Z axes. So I can say, I'm going to design a house. I can say, well, the front door is at this location, X, Y, Z, and the roof is at this location, X, Y, Z, and so on. That's the type of reference frame. So it turns out, for you to make a prediction, and I walk you through the thought experiment in the book where I was predicting what my finger was going to feel when I touched the coffee cup. It was a ceramic coffee cup, but this one will do. And what I realized is that to make a prediction what my finger is going to feel, like it's going to feel different than this, which will feel different if I touch the hole or this thing on the bottom, make that prediction, the cortex needs to know where the finger is, the tip of the finger, relative to the coffee cup. And exactly relative to the coffee cup. And to do that, I have to have a reference frame for the coffee cup. It has to have a way of representing the location of my finger to the coffee cup. And then we realized, of course, every part of your skin has to have a reference frame relative to things it touch. And then we did the same thing with vision. But so the idea that a reference frame is necessary to make a prediction when you're touching something or when you're seeing something and you're moving your eyes or you're moving your fingers. It's just a requirement to know what to predict. If I have a structure, I'm going to make a prediction. I have to know where it is I'm looking or touching it. So then we said, well, how do neurons make reference frames? It's not obvious. X, Y, Z coordinates don't exist in the brain. It's just not the way it works. So that's when we looked at the older part of the brain, the hippocampus and the entorhinal cortex, where we knew that in that part of the brain, there's a reference frame for a room or a reference frame for an environment. Remember I talked earlier about how you could make a map of this room. So we said, that they are implementing reference frames there. So we knew that reference frames needed to exist in every cortical column. And so that was a deductive thing. We just deduced it. Has to exist.
So you take the old mammalian ability to know where you are in a particular space and you start applying that to higher and higher levels.
Yeah, you apply it to like where your finger is. So here's the way I think about it. The old part of the brain says, where's my body in this room?
Yeah.
The new part of the brain says, where's my finger relative to this object?
Yeah.
Where is a section of my retina relative to this object? Like where is, I'm looking at one little corner, where is that relative to this patch of my retina?
Yeah.
And then we take the same thing and apply it to concepts, mathematics, physics, humanity, whatever you want to think about.
And eventually you're pondering your own mortality.
Well, whatever. But the point is, when we think about the world, when we have knowledge about the world, how is that knowledge organized, Lex? Where is it in your head? Yeah. The answer is it's in reference frames. So the way I learned the structure of this water bottle, where the features are relative to each other, when I think about history or democracy or mathematics, the same basic underlying structures happening. There's reference frames for where the knowledge that you're assigning things to. So in the book, I go through examples like mathematics and language and politics. But the evidence is very clear in the neuroscience. The same mechanism that we use to model this coffee cup, we're going to use to model high-level thoughts. The demise of the humanity, whatever you want to think about.
It's interesting to think about how different are the representations of those higher dimensional concepts, higher level concepts, how different the representation there is in terms of reference frames versus spatial.
But the interesting thing, it's a different application, but it's the exact same mechanism.
But isn't there some aspect to higher level concepts that they seem to be hierarchical? Like they just seem to integrate a lot of information into them.
So is our physical objects. So take this water bottle. I'm not particular to this brand, but this is a Fiji water bottle, and it has a logo on it. I use this example in my book. Our company's coffee cup has a logo on it. But this object is hierarchical. It's got like a cylinder and a cap, but then it has this logo on it. And the logo has a word. The word has letters. The letters have different features. And so I don't have to remember, I don't have to think about this. So I say, oh, there's a Fiji logo on this water bottle. Yeah. I don't have to go through and say, oh, what is the Fiji logo? It's the F and an I and a J and an I, and there's a hibiscus flower, and it has the stamen on it. I don't have to do that. I just incorporate all of that in some sort of hierarchical representation. I say, put this logo on this water bottle.
Yeah.
And then the logo has a word, and the word has letters. All hierarchical.
Just all that stuff is baked. It's amazing that the brain instantly just does all that.
Yeah.
The idea that there's water, it's liquid, and the idea that you can drink it when you're thirsty, the idea that there's brands.
Yeah.
And then there's like all of that information is instantly built into the whole thing once you perceive it.
So I wanted to get back to your point about hierarchical representation. The world itself is hierarchical, right? And I can take this microphone in front of me. I know inside there's going to be some electronics. I know there's going to be some wires, and I know there's going to be a little diaphragm that moves back and forth. I don't see that, but I know it. So everything in the world is hierarchical. You just go into a room, it's composed of other components. The kitchen has a refrigerator, the refrigerator has a door, the door has a hinge has screws and pin. So anyway, the modeling system that exists in every cortical column learns the hierarchical structure of objects. So it's a very sophisticated modeling system in this grain of rice. It's hard to imagine, but this grain of rice can do really sophisticated things. It's got 100,000 neurons in it. It's very sophisticated. So the same mechanism that can model a water bottle or a coffee cup can model conceptual objects as well. That's the beauty of this discovery that this guy, Vernon Mountcastle, made many, many years ago, which is that there's a single cortical algorithm underlying everything we're doing.
So common sense concepts and higher level concepts are all represented in the same way?
They're set in the same mechanisms, yeah. It's a little bit like computers, right? All computers are universal Turing machines. Even the little teeny one that's my toaster and the big one that's running some cloud server someplace. They're all running on the same principle. They can apply different things. So the brain is all built on the same principle. It's all about learning these models, structured models using movement and reference frames. And it can be applied to something as simple as a water bottle and a coffee cup. And it can be applied to thinking like, what's the future of humanity? And, why do you have a hedgehog on your desk? I don't know.
Nobody knows. Well,
I think it's a hedgehog.
That's right. It's a hedgehog in the fog. It's a rush. All right. So that was an incredible experience. Can you maybe speak to what kind of opportunities that opens up that stream of data, that rich stream of data from the brain?
First, I'm curious, what is your reaction? What comes to mind when you put that on your head? What does it mean to you? And what possibilities emerge? And what significance might it have? I mean, I'm curious where your orientation is at.
Well, for me, I'm really excited by the possibility of various information about my body, about my mind being converted into data such that data can be used to create products that make my life better. So that to me is really exciting possibility. Even just like a Fitbit that measures, I don't know, some very basic measurements about your body is really cool. But it's the bandwidth of information the resolution of that information is very crude, so it's not very interesting. The possibility of recording, of just building a data set coming in a clean way, in a high bandwidth way from my brain, opens up all kinds of, at the very, I was kind of joking when we were talking, but it's not really, is like I feel heard in the sense that it feels like the full richness of the information coming from my mind is actually being recorded by the machine. I mean, I can't quite put it into words, but there is genuinely, for me, this is not some kind of joke about me being a robot. This just genuinely feels like I'm being heard in a way that that's going to improve my life, as long as the thing that's on the other end can do something useful with that data. But even the recording itself is like, once you record, it's like taking a picture. That moment is forever saved in time. Now, a picture cannot allow you to step back into that world, but perhaps recording your brain is a much higher resolution thing, much more personal recording of that information than a picture, that would allow you to step back into that where you were in that particular moment in history, and then map out a certain trajectory to tell you certain things about yourself. That can open up all kinds of applications. Of course, there's health that I consider, but honestly, to me, the exciting thing is just being heard. My state of mind, the level of focus, all those kinds of things being heard.
What I heard you say is you have an entirety of lived experience, some of which you can communicate in words and in body language, some of which you feel internally, which cannot be captured in those communication modalities. And that this measurement system captures both the things you can try to articulate in words, maybe in a lower dimensional space, using one word, for example, to communicate focus, when it really may be represented in a 20-dimensional space of this particular kind of focus, and that this information is being captured. So it's a closer representation to the entirety of your experience, captured in a dynamic fashion that is not just a static image of your conscious experience.
That's the promise. That's the hope. That was the feeling, and it felt like the future. So it was a pretty cool experience. And from the sort of mechanical perspective, it was cool to have an actual device that feels pretty good. That doesn't require me to go into the lab. And also the other thing I was feeling, there's a guy named Andrew Huberman. He's a friend of mine. Amazing podcast. People should listen to it. Huberman Lab podcast. We're working on a paper together about eye movement and so on. And he's a neuroscientist and I'm a data person, a machine learning person. And we're both excited by how much the data measurements of the human mind, the brain, and all the different metrics that come from that can be used to understand human beings, and in a rigorous scientific way. So the other thing I was thinking about is how this could be turned into a tool for science, sort of not just personal science, not just like Fitbit style, like how am I doing on my personal metrics of health, but doing larger scale studies of human behavior and so on. So like data, not at the scale of an individual, but data at the scale of many individuals or a large number of individuals. So science, so it's personal, being heard was exciting, and also just for science is exciting. It's very easy. There's a very powerful thing to it being so easy to just put on that you can scale much easier.
If you think about that second thing you said about the science of the brain, we've done a pretty good job, the human race has done a pretty good job figuring out how to quantify the things around us, from distant stars to calories and steps and our genome. So we can measure and quantify pretty much everything in the known universe except for our minds. And we can do these one-offs if we're going to get an fMRI scan or do something with a low-res EEG system, but we haven't done this at population scale. And so if you think about human thought or human cognition is probably the single largest raw input material into society at any given moment. It's our conversations with ourselves and with other people, and we have this raw input that we haven't been able to measure yet.
Yeah.
And when I think about it through that frame, it's remarkable. It's almost like we live in this wild, wild west of unquantified communications within ourselves and between each other, when everything else has been grounded. I mean, for example, I know if I buy an appliance at the store or on a website, I don't need to look at the measurements on the appliance and make sure it can fit through my door. That's an engineered system of appliance manufacturing and construction. Everyone's agreed upon engineering standards. And we don't have engineering standards around cognition. It has not entered as a formal engineering discipline that enables us to scaffold in society with everything else we're doing, including consuming news, our relationships, politics, economics, education, all the above. And so to me, the most significant contribution that kernel technology has to offer would be the introduction to the formal engineering of cognition as it relates to everything else in society.
I love that idea that you kind of think that there is just this ocean of data that's coming from people's brains as being in a crude way reduced down to like tweets and texts and so on. So it's a very hardcore, many-scale compression of the raw data. But maybe you can comment, because you're using the word cognition. I think the first step is to get the brain data.
Mm-hmm.
But is there a leap to be taken to sort of interpreting that data in terms of cognition?
Mm-hmm.
So is your idea is basically you need to start collecting data at scale from the brain, and then we start to really be able to take little steps along the path to actually measuring some deep sense of cognition, because it's, as I'm sure you know, we understand a few things, but we don't understand most of what makes up cognition.
Mm-hmm. This has been one of the most significant challenges of building kernel, and kernel wouldn't exist if I wasn't able to fund it initially by myself. Because when I engage in conversations with investors, the immediate thought is, what is a killer app? And of course, I understand that heuristic. That's what they're looking at, is they're looking to de-risk. Is the product solved? Is there a customer base? Are people willing to pay for it? How does it compare to competing options? And in the case with brain interfaces, when I started the company, there was no known path to even build a technology that could potentially become mainstream.
Yes.
And then once we figured out the technology, we could commence having conversations with investors, and it became, what is a killer app? And so I funded the first $53 million of the company. And to raise the round of funding, the first one we did, I spoke to 228 investors. One said yes. It was remarkable. And it was mostly around this concept around what is a killer app. And so internally, the way we think about it is we think of the go-to-market strategy much more like the Drake equation, where if we can build technology that has the characteristics of, it has the data quality is high enough, it meets some certain threshold, cost, accessibility, comfort, it can be worn in contextual environments. If it meets the criteria of being a mass market device, then the responsibility that we have is to figure out how to create the algorithm that enables humans to then find value with it.
Okay.
So the analogy is like brain interfaces are like early 90s of the internet. Is you want to populate an ecosystem with a certain number of devices. You want a certain number of people who play around with them, who do experiments of certain data collection parameters. You want to encourage certain mistakes from experts and non-experts. These are all critical elements that ignite discovery. And so we believe we've accomplished the first objective of building technology that reaches those thresholds. And now it's the Drake equation component of how do we try to generate 20 years of value discovery in a 2 or 3 year time period? How do we compress that?
So just to clarify, so when you mean the Drake equation, which for people who don't know, I don't know why if you listen to this, I bring up aliens every single conversation. So I don't know how you would know what the Drake equation is, but you mean like the killer app, it would be one alien civilization in that equation. So meaning like this is in search of an application that's impactful,
that's
transformative.
Right.
By the way, it should be we need to come up with a better term than killer app as a
it's also violent, right?
Very violent. You can go like viral app. That's horrible too, right? It's some very inspiringly impactful application. How about that? No.
Yeah.
Okay. So, but let's stick with killer app. That's fine. Nobody's.
But I concur with you. I dislike the chosen words in capturing the concept.
You know, it's one of those sticky things that is as effective to use in the tech world, but when you're now become a communicator outside of the tech world, especially when you're talking about software and hardware and artificial intelligence applications, it sounds horrible.
Yeah, no, it's interesting. I actually regret, now having called attention to this, I regret having used that word in this conversation because it's something I would not normally do. I used it in order to create a bridge of shared understanding of how what terminology others would use.
Yeah.
But yeah, I concur.
Let's go with impactful application.
Or just value creation.
Value creation. Something people love using.
There we go. That's it.
Love app. Okay. So what, do you have any ideas? So you're basically creating a framework where there's the possibility of a discovery of an application that people love using.
Mm-hmm.
Do you have ideas?
We've begun to play a fun game internally where when we have these discussions and we begin circling around this concept of, does anybody have an idea? Does anyone have intuitions? And if we see the conversation starting to veer in that direction, we flag it and say, human intuition alert, stop it. And so we really want to focus on the algorithm of there's a natural process of human discovery. That when you populate a system with devices and you give people the opportunity to play around with it in expected and unexpected ways, we are thinking that is a much better system of discovery than us exercising intuitions. And it's interesting, we're also seeing a few neuroscientists who have been talking to us, where I was speaking to this one young associate professor, and I approached a conversation and said, hey, we have these 5 data streams that we're pulling off. When you hear that, what weighted value do you add to each data source? Like, which one do you think is going to be valuable for your objectives and which one's not?
Yeah.
And he said, I don't care. Just give me the data. All I care about is my machine learning model.
Yeah.
But importantly, he did not have a theory of mind. He did not come to the table and say, I think the brain operates, in this way and these regions have these functions. He didn't care. He just wanted the data. And we're seeing that more and more, that certain people are devaluing human intuitions for good reasons, as we've seen in machine learning over the past couple of years. And we're doing the same in our value creation market strategy.
So collect more data, clean data, make the product such that the collection of data is easy and fun, and then the rest will just spring to life.
That's right.
Through humans playing around with it. And so
our objective is to create the most valuable data collection system of the brain ever. And with that, then applying all the best tools of machine learning and other techniques to extract out, to try to find insight. But yes, our objective is really to systematize the discovery process, because we can't put definite timeframes on discovery. The brain is complicated, and science is not a business strategy. And so we really need to figure out how to. This is the difficulty of bringing technology like this to market. It's why most of the time it languishes in academia for quite some time. But we hope that we will cross over and make this mainstream in the coming years.
The thing was cool to wear, but are you chasing a good reason for millions of people to put this on their head and keep on their head regularly? Is there like, who is going to discover that reason? Is it going to be people just kind of organically, or is there going to be Angry Birds style application that's just too exciting to not use?
if I think through the things that have changed my life most significantly over the past few years, when I started wearing a wearable on my wrist that would give me data about my heart rate variability, respiration rate, metabolic approximations, etc. For the first time in my life, I had access to information, sleep patterns that were highly impactful. They told me, for example, if I eat close to bedtime, I'm not going to get deep sleep. And not getting deep sleep means you have all these follow-on consequences in life. And so it opened up this window of understanding of myself that I cannot self-introspect and deduce these things. This is information that was available to be acquired, but it just wasn't. I would have to get an expensive sleep study, then it's like one night, and that's not good enough to run all my trials. And so if you look just at the information that one can acquire on their wrist, and now you're applying it to the entire cortex on the brain, and you say, what kind of information could we acquire? It opens up a whole new universe of possibilities. For example, we did this internal study at Kernel where I wore a prototype device, and we were measuring the cognitive effects of sleep. So I had a device measuring my sleep. I performed with 13 of my coworkers. We performed 4 cognitive tasks over 13 sessions. And we focused on reaction time, impulse control, short-term memory, and then a resting state task. And with mine, we found, for example, that my impulse control was independently correlated with my sleep, outside of behavioral measures of my ability to play the game. The point of the study was the brain study I did at Kernel confirmed my life experience. Yeah. That if my deep sleep determined whether or not I would be able to resist temptation the following day. And my brain data showed that as one example. And so if you start thinking, if you actually have data on yourself, on your entire cortex, and you can control the settings, I think there's probably a large number of things that we could discover about ourselves, very, very small and very, very big. Just for example, like when you read news, what's going on?
Like when you use social media, when you use news, all the ways we allocate attention.
That's right.
With the computer. I mean, that seems like a compelling place to where you would want to put on kernel. By the way, what is it called? Kernel Flux? Kernel? Like what?
Flow. We have two technologies, you or Flow.
Flow. Okay. So when you put on the kernel Flow, it seems like to be a compelling time and place to do it is when you're behind a desk, behind a computer, because you could probably wear it for prolonged periods of time as you're taking in content. And there could because so much of our lives happens in the digital world now, that kind of coupling the information about the human mind with the consumption and the behaviors in the digital world might give us a lot of information about the effects of the way we behave and navigate the digital world to the actual physical space effects on our body. It's interesting to think. So in terms of both, like for work, I'm a big fan of Cal Newport, his ideas of deep work, that I spend with few exceptions, I try to spend the first 2 hours of every day. Usually if I'm like at home and have nothing on my schedule, is going to be up to 8 hours of deep work, of focus, zero distraction. And for me to analyze I'm very aware of the waning of that, the ups and downs of that. And it's almost like you're surfing the ups and downs of that as you're doing programming, as you're doing thinking about particular problems. You're trying to visualize things in your mind. You start trying to stitch them together. You're trying to, when there's a dead end about an idea, you have to kind of calmly like walk back and start again. All those kinds of processes. It'd be interesting to get data on what my mind is actually doing. And also recently started doing, I just talked to Sam Harris a few days ago and been building up to that. I started meditating using his app, Waking Up. I very much recommend it. It'd be interesting to get data on that, because it's like you're removing all the noise from your head, and it's an active process of active noise removal. active noise canceling, like the headphones, and it'd be interesting to see what is going on in the mind before the meditation, during it, and after, all those kinds of things.
In all of your examples, it's interesting that everyone who's designed an experience for you, so whether it be the meditation app or the deep work or all the things you mentioned, they constructed this product with a certain number of knowns.
Yeah.
Now, what if we expanded the number of knowns by 10x or 20x or 30x? They would reconstruct their product to incorporate those knowns. So it'd be, and so this is the dimensionality that I think is the promising aspect, is that people will be able to use this quantification, use this information to build more effective products. And this is, I'm not talking about better products to advertise to you or manipulate you. I'm talking about our focus is helping people, individuals, have this contextual awareness and this quantification, and then to engage with others who are seeking to improve people's lives. That the objective is betterment across ourselves individually and also with each other.
Yeah, so it's a nice data stream to have if you're building an app. Like if you're building a podcast listening app, it would be nice to know data about the listener so that like if you're bored or you fell asleep, maybe pause the podcast.
That's right, yeah. Or
it's like really dumb, just very simple applications that could just improve the quality of the experience of using the app.
I'm imagining if you have your neuron, this is Lex, and there's a statistical representation of you, and you engage with the app, and it says, Lex, you're best to engage with this meditation exercise in the following settings. At this time of day, after eating this kind of food or not eating, fasting, with this level of blood glucose and this kind of night's sleep.
Yep.
But all these data combined to give you this contextually relevant experience, just like we do with our sleep. You've optimized your entire life based upon what information you can acquire and know about yourself. And so the question is, how much do we really know of the things going around us? And I would venture to guess, in my life experience, my self-awareness captures an extremely small % of the things that actually influence my conscious and unconscious experience.
Well, in some sense, the data would help encourage you to be more self-aware, not just because you trust everything the data is saying, but it'll give you a prod to start investigating. Like I would love to get a rating, like a ranking of all the things I do and what are the things. This is probably important to do without the data, but the data will certainly help. It's like rank all the things you do in life and which ones make you feel shitty, which ones make you feel good. Like you're talking about evening, Brian. Like this is a good example. Somebody like I do pig out at night as well, and it never makes me feel
you're
good.
In a safe space.
This is a safe space. It's never.
Let's hear it.
No, I definitely have much less self-control at night, and it's interesting. And the same, people might criticize this, but I know my own body. I know when I eat carnivore, just eat meat, I feel much better than if I eat more carbs. The more carbs I eat, the worse I feel. I don't know why that is. There is science supporting it, but I'm not leaning on science. I'm leaning on personal experience, and that's really important. I don't need to read. I'm not going to go on a whole rant about nutrition science, but many of those studies are very flawed. They're doing their best, but nutrition science is a very difficult field to study because humans are so different, and the mind has so much impact on the way your body behaves, and it's so difficult from a scientific perspective to conduct really strong studies that you have to be almost like a scientist of one. You have to do these studies on yourself. That's the best way to understand what works for you and not. And I don't understand why, because it sounds unhealthy, but eating only meat always makes me feel good. Just eat meat. That's it. And I don't have any allergies, any of that kind of stuff. I'm not full like Jordan Peterson, where like if he like deviates a little bit, that he goes off, like deviates a little bit from the carnivore diet, he goes off like the cliff. No, I can have like chocolate. I can go off the diet. I feel fine. It's a gradual worsening of how I feel. But when I eat only meat, I feel great. And it'd be nice to be reminded of that. Like, it's a very simple fact that I feel good when I eat carnivore. And I think that repeats itself in all kinds of experiences. Like, I feel really good when I exercise. Not, I hate exercise, okay? But in the rest of the day, the impact it has on my mind, on the clarity of mind, on the experiences and the happiness and all those kinds of things, I feel really good. And to be able to concretely express that through data would be nice. It would be a nice reminder, almost like a statement, like remember what feels good and what not. And there could be things like that I'm not, many things like you're suggesting that I could not be aware of. There might be sitting right in front of me that make me feel really good and make me feel not good, and the data would show that.
I agree with you. I've actually employed the same strategy. I fired my mind entirely from being responsible for constructing my diet. And so I started doing a program where I now track over 200 biomarkers every 90 days. And it captures, of course, the things you would expect, like cholesterol, but also DNA methylation and all kinds of things about my body, all the processes that make up me. And then I let that data generate the shopping list. And so I never actually ask my mind what it wants. It's entirely what my body is reporting that it wants. And so I call this goal alignment within Bryan. And there's 200 plus actors that I'm currently asking their opinion of. And so I'm asking my liver, how are you doing? And it's expressing via the biomarkers. And so then I construct that diet, and I only eat those foods until my next testing round. And that has changed my life more than I think anything else, because in the demotion of my conscious mind that I gave primacy to my entire life, it led me astray because, like you're saying, the mind then goes out into the world and it navigates the dozens of different dietary regimens people put together in books, and it all has their supporting science in certain contextual settings, but it's not N of one. And like you're saying, this dietary really is an N of one. What people have published scientifically, of course, can be used for nice groundings, but it changes when you get to an N of one level. And so that's what gets me excited about brain interfaces is if I could do the same thing for my brain, where I can stop asking my conscious mind for its advice or for its decision-making, which is flawed. And I'd rather just look at this data I've never had better health markers in my life than when I stopped actually asking myself to be in charge of it. And
the idea of demotion of the conscious mind is such a sort of engineering way of phrasing like meditation with
I mean, that's what we're doing, right?
Yeah, that's beautiful. That means really beautifully put. By the way, testing round, what does that look like? What's that? Well, you mentioned
the test I do.
Yes.
So it includes a complete blood panel. I do a microbiome test. I do a food inflammation, a diet-induced inflammation. So I look for cytokine expressions, so foods that produce inflammatory reactions. I look at my neuroendocrine system. So I look at all my neurotransmitters. I do, there's several micronutrient tests to see how I'm looking at the various nutrients.
What about like self-report of like how you feel, almost like you can't demote you still exist within your conscious mind, right? So that lived experience is of a lot of value. So how do you measure that?
I do a temporal sampling over some duration of time. So I'll think through how I feel over a week, over a month, over 3 months. I don't do a temporal sampling of if I'm at the grocery store in front of a cereal box and be like, you know what, Captain Crunch is probably the right thing for me today because I'm feeling like I need a little fun in my life.
Yeah.
And so it's a temporal sampling. If the data set's large enough, then I smooth out the function of my natural oscillations of how I feel about life, where some days I may feel upset or depressed or down or whatever. And I don't want those moments to then rule my decision making. That's why the demotion happens. And it says, really, if you're looking at health over a 90-day period of time, all my 200 voices speak up on that interval. And they're all given voice to say, this is how I'm doing and this is what I want. And so it really is an accounting system for everybody. So that's why I think that if you think about the future of being human, there's two things I think that are really going on. One is the design, manufacturing, and distribution of intelligence is heading towards zero on a cost curve over a certain time frame. But our ability to, evolution produced us a form of intelligence. We are now designing our own intelligent systems. And the design, manufacturing, and distribution of that intelligence over a certain time frame is going to go to a cost of zero.
Design, manufacture, distribution of intelligent cost is going to zero.
For example.
Again, just give me a second.
Okay.
That's brilliant. Okay. And evolution is doing the design, manufacture, and distribution of intelligence. And now we are doing the design, manufacture, and distribution of intelligence. And the cost of that is going to zero.
Yes.
That's a very nice way of looking at life on Earth.
So if that's going on, and then now in parallel to that, then you say, okay, what then happens when that cost curve is heading to zero? Our existence becomes a goal alignment problem, a goal alignment function. And so the same thing I'm doing where I'm doing goal alignment within myself of these 200 biomarkers, where I'm saying when Bryan exists on a daily basis and this entity is deciding what to eat and what to do and et cetera, it's not just my conscious mind, which is opining, it's 200 biological processes, and there's a whole bunch of more voices involved. So in that equation, we're going to increasingly automate the things that we spend high energy on today because it's easier. And now we're going to then negotiate the terms and conditions of intelligent life. Now, we say conscious existence because we're biased, because that's what we have. But it will be the largest computational exercise in history because you're now doing goal alignment with planet Earth, within yourself, with each other, within all the intelligent agents we're building, bots and other voice assistants. You basically now have trillions and trillions of agents working on the negotiation of goal alignment.
Yeah, this is in fact true. And what was the second thing?
That was it. So the cost, the design, manufacturing, distribution of intelligence going to zero, which then means what's really going on? What are we really doing? We're negotiating the terms and conditions of existence.
You founded the payment system Braintree in 2007 that acquired Venmo in 2012. In that same year was acquired by PayPal, which is now eBay. Can you tell me the story of the vision and the challenge of building an online payment system and just building a large successful business in general?
I discovered payments by accident. When I was 21, I just returned from Ecuador, living among extreme poverty for 2 years. And I came back to the US and I was shocked by the opulence of the United States. And I just thought I couldn't believe it. And I decided I wanted to try to spend my life helping others. Like that was the life objective that I thought was worthwhile to pursue versus making money and whatever the case may be for its own right. And so I decided in that moment that I was going to try to make enough money by the age of 30 to never have to work again. And then with some abundance of money, I could then choose to do things that might be beneficial to others, but may not meet the criteria of being, a standalone business. And so in that process, I started a few companies, had some small successes, had some failures. In one of the endeavors, I was up to my eyeballs in debt. Things were not going well, and I needed a part-time job to pay my bills. Mm-hmm. And so one day I saw in the paper in Utah where I was living, the 50 richest people in Utah. And I emailed each one of their assistants and said, I'm young, I'm resourceful, I'll do anything. I'm entrepreneurial. I tried to get a job that would be flexible and no one responded. And then I interviewed at a few dozen places. Nobody would even give me the time of day. No one would take me seriously. And so finally, it was on monster.com that I saw this job posting for credit card sales door to door. Commission.
I did not know this story. This is great.
I love the head drop. That's exactly right. So it was
the low points to which we go in life.
So I responded, and the person made an attempt at suggesting that they had some kind of standards that they would consider in hiring. But it's kind of like, if you could fog a mirror, like, you come and do this because it's 100% commission. And so I started walking up and down the street in my community selling credit card processing. And so what you learn immediately in doing that is, if you walk into a business, first of all, the business owner is typically there. And you walk in the door and they can tell by how you're dressed or how you walk, whatever their pattern recognition is. Mm-hmm. And they just hate you immediately. It's like, stop wasting my time. I really am trying to get stuff done. I don't want to listen to a sales pitch. And so you have to overcome the initial get out. And then once you engage, and when you say the word credit card processing, the person's like, I already hate you because I have been taken advantage of dozens of times because you all are weasels. And so I had to figure out an algorithm to get past all those different conditions, because I was still working on my other startup for the majority of my time. So I was doing this part-time. And so I figured out that the industry really was built on people, on deceit. Basically, people promising things that were not reality. And so I'd walk into a business and I'd say, look, I will give you $100. I'd put out a $100 bill and say, I'll give you $100 for 3 minutes of your time. If you don't say yes to what I'm saying, I'll give you $100. And then he'd usually crack a smile and say, okay, what do you got for me, son? And so I'd sit down and I'd just open my book and I'd say, here's the credit card industry. Here's how it works. Here are the players. Here's what they do. Here's how they deceive you. Here's what I am. I'm no different than anyone else. It's like, you're going to process your credit card. You're going to get the money in the account. You're just going to get a clean statement. You're going to have someone who answers the call when someone asks, and, just like the basic, like, you're okay. Yeah. And people started saying yes. And then, of course, I went to the next business and be like, Joe and Susie and whoever said yes too. And so I built the social proof structure, and I became the number one salesperson out of 400 people nationwide doing this. And I worked, half time still doing this other startup. And
that's a brilliant strategy, by the way. It's very well strategized and executed.
So I did it for 9 months. And at the time, my customer base was generating around, I think it was, if I remember correctly, $62,504 a month were the overall revenues. I thought, wow, that's amazing. If I built that as my own company, I would just make $62,000 a month of income passively with these merchants processing credit cards. So I thought, And so that's when I thought, I'm going to create a company. And so then I started Braintree. And the idea was the online world was broken because PayPal had been acquired by eBay around, I think, 1999 or 2000. And eBay had not innovated much with PayPal. So it basically sat still for 7 years as the software world moved along. And then Authorize.net was also a company that was relatively stagnant. So you basically had software engineers who wanted modern payment tools, but there were none available for them. And so they just dealt with software they didn't like. And so with Braintree, I thought the entry point is to build software that engineers will love. And if we can find the entry point via software and make it easy and beautiful and just a magical experience, and then provide customer service on top of that was easy, that would be great. What I was really going after for, though, was PayPal. They were the only company in payments making money because they had the relationship with eBay early on. People created a PayPal account. They'd fund their account with their checking account versus their credit cards. And then when they'd use PayPal to pay a merchant, PayPal had a cost of payment of 0 versus if you have coming from a credit card, you have to pay the bank the fees. So PayPal's margins were 3% on a transaction versus a typical payments company, which may be a nickel or a penny or a dime or something like that. And so I knew PayPal really was the model to replicate, but a bunch of companies had tried to do that. They tried to come in and build a two-sided marketplace. So get consumers to fund the checking account and the merchants to accept it. But they'd all failed because building a two-sided marketplace is very hard at the same time. So my plan was, I'm going to build a company and get the best merchants in the whole world to use our service. Then in year 5, I'm going to acquire a consumer payments company, and I'm going to bring the two together.
Wow.
And
so focus on the merchant side.
Exactly.
And then get the payments company that does the customer, the whatever. So the other side of it.
Yeah, this is the plan I presented when I was at the University of Chicago. And weirdly, it happened exactly like that. So 4 years in, our customer base included Uber, Airbnb, GitHub, 37 Signals, now Basecamp. We had a fantastic collection of companies that represented the fastest growing some of the fastest growing tech companies in the world. And then we met up with Venmo, and they had done a remarkable job in building product. There's then something very counterintuitive, which is make public your private financial transactions, which people previously thought were something that should be hidden from others. And we acquired Venmo. And at that point, we replicated the model, because now people could fund their Venmo account with their checking account, keep money in the account, and then you could just plug Venmo in as a form of payment. And so I think PayPal saw that we were getting the best merchants in the world. We had people using Venmo. They were both the up-and-coming millennials at the time who had so much influence online. And so they came in and offered us an attractive number. And my goal was not to build the biggest payments company in the world. It wasn't to try to climb the Forbes billionaire list. The objective was, I want to earn enough money so that I can basically dedicate my attention to doing something that could potentially be useful on a society-wide scale. And more importantly, that could be considered to be valuable from the vantage point of 2050, 2100, and 2500. So thinking about it on a few 100-year time scale. And there was a certain amount of money I needed to do that, so I didn't require the permission of anybody to do that. And so what PayPal offered was sufficient for me to get that amount of money to basically have a go. And that's when I set off to survey everything I could identify in existence to say, of anything in the entire world I could do, what one thing could I do that would actually have the highest value potential for the species? And so it took me a little while to arrive at brain interfaces, but
payments in themselves are revolutionary technologies that can change the world. Like, let's not let's not forget that too easily. I mean, obviously you know this, but there's quite a few lovely folks who are now fascinated with the space of cryptocurrency. And payments are very much connected to this, but in general, just money. And many of the folks I've spoken with, they also kind of connect that to not just purely financial discussions, but philosophical and political discussions. And they see Bitcoin as a way, almost as activism, almost as a way to resist the corruption of centers of power. And sort of basically in the 21st century, decentralize and control, whether that's Bitcoin or other cryptocurrencies. They see that's one possible way to give power to those that live in regimes that are corrupt or are not respectful of human rights and all those kinds of things. What's your sense, just all your expertise with payments and seeing how that changed the world, what's your sense about the lay of the land for the future of Bitcoin or other cryptocurrencies in the positive impact it may have in the world?
Yeah, and to be clear, my communication wasn't meant to minimize payments or to denigrate it in any way. It was an attempted communication that when I was surveying the world, it was an algorithm of what could I individually do. So there are things that exist that have a lot of potential that can be done. And then there's a filtering of how many people are qualified to do this given thing. And then there's a further characterization that can be done of, okay, given the number of qualified people, will somebody be a unique outperformer of that group to make something truly impossible to be something done that otherwise couldn't get done? So there's a process of assessing where can you add unique value in the world.
And some of that has to do with you being very, very formal and calculative here, but some of that is just like, what do you sense? Like, part of that equation is how much passion you sense within yourself to be able to drive that through, to discover the impossibilities and make them possible.
That's right. And so we were at Braintree, I think we were the first company to integrate Coinbase into our, I think we were the first payments company to formally incorporate crypto, if I'm not mistaken.
For people who are not familiar, Coinbase is a place where you can trade cryptocurrencies.
Yeah, which was one of the only places you could. So we were early in doing that. And of course, this was in the year 2013. So an eternity ago in cryptocurrency land. I concur with the statement you made of the potential of the principles underlying cryptocurrencies, and that many of the things that they're building in the name of money and of moving value is equally applicable to the brain and equally applicable to how the brain interacts with the rest of the world, and how we would imagine doing goal alignment with people. So to me, it's a continuous spectrum of possibility. And your question is isolated on the money. And I think it just is basically a scaffolding layer for all of society.
So you don't see this money as particularly distinct from.
I don't. I think we at Kernel, we will benefit greatly from the progress being made in cryptocurrency, because it will be a similar technology stack we will want to use for many things we want to accomplish. And so I'm bullish on what's going on, and think it could greatly enhance brain interfaces and the value of the brain interface ecosystem.
I mean, is there something you could say about, first of all, bullish on cryptocurrency versus fiat money? So do you have a sense that in 21st century, cryptocurrency will be embraced by governments and change the face of governments, the structure of governments?
It's the same way I think about my diet, where previously it was conscious Bryan looking at foods in certain biochemical states. Am I hungry? Am I irritated? Am I depressed? And then I choose based upon those momentary windows. Mm-hmm. Do I eat at night when I'm fatigued and I have low willpower? Am I going to pig out on something? And the current monetary system is based upon human conscious decision-making and politics and power and this whole mess of things. And what I like about the building blocks of cryptocurrency is it's methodical, it's structured, it is accountable, it's transparent. And so it introduces this scaffolding, which I think, again, is the right starting point for how we think about building next generation institutions for society. And that's why I think it's much broader than money.
So I guess what you're saying is Bitcoin is the demotion of the conscious mind as well. In the same way you were talking about diet, it's like giving less priority to the ups and downs of any one particular human mind, in this case your own, and giving more power to the sort of data-driven.
Yes. Yeah. I think that is accurate, that cryptocurrency is a version of what I would call my autonomous self that I'm trying to build.
Yeah.
It is an introduction of an autonomous system of value exchange and value and the process, of value creation in society. Yes. So there's similarities.
So I guess what you're saying is Bitcoin will somehow help me not pig out at night, or the equivalent of. Elon Musk describes human beings as potentially what he calls the biological bootloader for artificial intelligence, or artificial general intelligence is used as the term. It's kind of like super intelligence. Do you see superhuman level intelligence as potentially the next step in the evolutionary process?
Yes, I think that if superhuman intelligence is to be found, it will be artificial. I don't have any hope that we ourselves, our brains will go on getting larger in ordinary biological evolution. I think that's probably come to an end. It is the dominant trend, or one of the dominant trends in our fossil history for the last 2 or 3 million years.
Brain size?
Brain size, yes. So it's been swelling rather dramatically over the last 2 or 3 million years. That is unlikely to continue. The only way that happens is because natural selection favors those individuals with the biggest brains, and that's not happening anymore.
Right. So in general, in humans, the selection pressures are not. Are they active in any form anymore?
Well, in order for them to be active, it would be necessary that the most let's call it intelligence. Not that intelligence is simply correlated with brain size, but let's talk about intelligence. In order for that to evolve, it's necessary that the most intelligent beings have individuals have the most children. So intelligence may buy you money, it may buy you worldly success, it may buy you a nice house and a nice car and things like that if you're a successful career. It may buy you the admiration of your fellow people, but it doesn't increase the number of offspring that you have. It doesn't increase your genetic legacy to the next generation. On the other hand, artificial intelligence, computers and technology generally is evolving by a non-genetic means, by leaps and bounds, of course.
And so what do you think, I don't know if you're familiar, there's a company called Neuralink, but there's a general effort of brain-computer interfaces, which is to try to build a connection between the computer and the brain, to send signals both directions. And the long-term dream there is to do exactly that, which is expand the size of the brain, expand the capabilities of the brain. Do you see this as interesting? Do you see this as a promising possible technology, or is the interface between the computer and the brain, like the brain is this wet, messy thing that's just impossible to interface with?
Well, of course it's interesting. Whether it's promising, I'm really not qualified to say. What I do find puzzling is that the brain being as small as it is compared to a computer and the individual components being as slow as they are compared to our electronic components, it is astonishing what it can do. I mean, imagine building a computer that fits into the size of a human skull, and with the equivalent of transistors or integrated circuits which work as slowly as neurons do. There's something mysterious about that. Something must be going on that we don't understand.
So I've just talked to Roger Penrose. I'm not sure if you're familiar with his work, and he also describes this kind of mystery in the mind, in the brain, that so he's a materialist. So there's no sort of mystical thing going on, but there's so much about the material of the brain that we don't understand. That might be quantum mechanical in nature and so on. So there are the ideas about consciousness. Do you ever think about ideas of consciousness, or a little bit more about the mystery of intelligence and consciousness that seems to pop up, just like you're saying, from our brain?
I agree with Roger Penrose that there is a mystery there. I mean, he's one of the world's greatest physicists, so I can't possibly argue with his.
But nobody knows anything about consciousness, and in fact, if we talk about religion and so on, the mystery of consciousness is so awe-inspiring, and we know so little about it that the leap to sort of religious or mystical explanations is too easy to make.
I think that it's just an act of cowardice to leap to religious explanations, and Roger doesn't do that, of course. Right. But I accept that there may be something that we don't understand about it.
Do you think there's something interesting, valuable to consider about the difference in the computational power of the human brain versus the computers of today in terms of instructions per second?
Yes. So if we go back, so this is a point I've been making for 20 years now.
Yeah.
And I think once upon a time, the way I used to argue this was that we just didn't have the computing power of the human brain. Our computers were not quite there. And I mean, there is a well-known trade-off, which we know that that neurons are slow compared to transistors, but we have a lot of them, and they have a very high connectivity. Whereas in silicon, you have much faster devices. Transistors switch on the order of nanoseconds, but the connectivity is usually smaller.
Right.
At this point in time, I mean, we are now talking about 2020. We do have, if you consider the latest GPUs and so on, amazing computing power. And if we look back at Hans Morowicz's type of calculations, which he did in the 1990s, we may be there today in terms of computing power comparable to the brain, but it's not of the same style.
Right.
It's of a very different style. So I mean, for example, the style of computing that we have in our GPUs is far, far more power hungry than the style of computing that is there in the human brain or other biological entities.
Yeah, and that the efficiency part is we're going to have to solve that in order to build actual real world systems of large scale from now. How promising in the near term, in your view, is brain machine interfaces? So starting to allow computers to talk directly to the brains. Elon Musk is working on that with Neuralink, and there's other companies working on this idea. Do you see promise there? Do you see hope for near-term impact?
Well, every technology has pluses and minuses. Already, we can record memories. I have a book, The Future of the Mind, where I detail some of these breakthroughs. We can now record simple memories of mice and send these memories on the internet. Eventually, we're going to do this with primates at Wake Forest University and also in Los Angeles. And then after that, we'll have a memory chip for Alzheimer's patients. We'll test it out in Alzheimer's patients because, of course, when Alzheimer's patients lose their memory, they wander. They create all sorts of havoc, wandering around, oblivious to their surroundings. And they'll have a chip. They'll push the button and memories will come flooding into their hippocampus and the chip, telling them where they live and who they are. And so a memory chip is definitely in the cards. And I think this will eventually affect human civilization. What is the future of the internet? The future of the internet is BrainNet. BrainNet is when we send emotions, feelings, sensations on the internet, and we will telepathically communicate with other humans this way. This is going to affect everything. Look at entertainment. Remember the silent movies? Charlie Chaplin was very famous during the era of silent movies, but when the talkies came in, nobody wanted to see Charlie Chaplin anymore because he never talked in the movies. And so a whole generation of actors lost their job, and a new series of actors came in. Next, we're going to have the movies replaced by BrainNet. Because in the future, people will say, who wants to see a screen with images? That's it. Sound and image, that's called the movies. Our entertainment industry, this multi-billion-dollar industry, is based on screens with moving images and sound. But what happens when emotions, feelings, sensations, memories can be conveyed on the internet? It's going to change everything. Human relations will change because you'll be able to empathize and feel the suffering of other people. We'll be able to communicate telepathically. And this is coming.
You described BrainNet in Future of the Mind. It's such an interesting concept. Do you think, so you mentioned entertainment, but what kind of effect would it have on our personal relationships?
Hopefully it will deepen it. You realize that for most of human history, for over 90% of human history, we only knew maybe 20, 100 people.
Yeah.
That's it, folks. That was your tribe. That was everybody you knew in the universe was only maybe 50 or 100. With the coming of towns, of course, it expanded to a few thousand. With the coming of the telephone, all of a sudden you could reach thousands of people with the telephone. And now with the internet, you can reach the entire population of the planet Earth. And so I think this is a normal progression.
And you think that kind of sort of connection to the rest of the world, and then adding sensations like being able to share telepathically emotions and so on, that would just further deepen our connection to our fellow humans.
Yeah, that's right. In fact, I disagree with many scientists on this question. Most scientists would say that technology is neutral, a double-edged sword. One side of the sword can cut against people. The other side of the sword can cut against ignorance and disease. I disagree. I think technology does have a moral direction. Look at the internet. The internet spreads knowledge, awareness, and that creates empowerment. People act on knowledge. When they begin to realize that they don't have to live that way, they don't have to suffer under a dictatorship, that there are other ways of living under freedom, then they begin to take power. And that spreads democracy. And democracies do not war with other democracies. I'm a scientist. I believe in data. So let's take a sheet of paper and write down every single war you had to learn since you were in elementary school. Every single war, hundreds of them, kings, queens, emperors, dictators, all these wars were between kings, queens, emperors, and dictators. Never between two major democracies. And so I think with the spread of this technology, and which will accelerate with the coming of BrainNet, it means that, well, we will still have wars. Wars, of course, is politics by other means, but they'll be less intense and less frequent.
Why do we prefer to watch, the question goes, why do we prefer to watch a film we haven't watched before, but we want to listen to songs that we have heard hundreds of times? This question and your answer really started to make me think, like, yeah, that's true. That's really interesting. Like, we draw that line somehow. So what's the answer?
So I think, let's use these two minds again. I think that when your higher mind is the one who's taking something in and they're really interested in, what are the lyrics? Or I'm going to learn something, or what, reading a book or whatever. And the higher mind is trying to get information. And once it has it, there's no point in listening to it again. It has the information. Your rational brain is like, I got it. But when you eat a good meal or have sex or whatever, that's something you can do again and again because it actually, your primitive brain loves it. Right. And it never gets bored of things that it loves. So I think music is a very primal thing. I think music goes right into our primitive brain a lot. I think it's a collaboration. Your rational brain is absorbing the actual message. But I think it's all about emotions and even more than emotions. It literally music taps into like some very, very deep, primal part of us. And so when you hear a song once, even some of your favorite songs, the first time you heard it, you were like, I guess that's kind of catchy. Yeah. And then then you end up loving it on the 10th listen. But sometimes you don't even like a song. You're like, oh, this song sucks. But you find yourself on the 40th time, because it's on the radio all the time, just kind of being like, oh, I love this song. And you're like, wait, I hated this song. And what's happening is that the sound is actually, the music's actually carving a pathway in your brain. And it's a dance. And when your brain knows what's coming, it can dance. It knows the steps. So your brain is your internal kind of, your brain is actually dancing with the music, and it knows the steps, and it can anticipate. And so there's something about having memorized the song that makes it incredibly enjoyable to us. But when we hear it for the first time, we don't know where it's going to go. We're like an awkward dancer. We don't know the steps, and your primitive brain can't really have that much fun yet. Mm-hmm. That's how I feel.
And in the movies, that's less primitive. That's a story. You're taking in.
But a really good movie that we really love, often we will watch it like 12 times, and still like it. Not that many, but versus if you're watching a talk show, right? If you're listening to one of your podcasts, as a perfect example. There's not many people that will listen to one of your podcasts, no matter how good it is, 12 times, because it's you. Once you got it, you got it. It's a form of information that's very higher mind focused. That's how it.
Well, the funny thing is there is people that listen to a podcast episode many, many times, and often I think the reason for that is not because of the information, is the chemistry, is the music of the conversation.
Yeah.
So it's not the actual.
It's the art of it they like.
Yeah. They'll fall in love with some kind of person, some weird personality, and they'll just be they'll be captivated by the beat of that kind of person.
Or like a stand up comic, I've watched like certain things, like episodes, like 20 times. Yeah. Even though